Okay. All right. So good morning and welcome to class. And this is our ham radio class. And as you can see, we have a good number of people who showed up, and I'm very happy that there was room for all of you and that everyone was able to make it. Again, if you didn't get the zip file attached to the email that I sent, which had the link to this class, that zip file has something in there called the No Nonsense Technician Class Radio Guide, Radio Study Guide, the technician version, and it's about 127 pages long. And this sort of makes a framework by which we're going to do this class. Now, I will say that in some ways I stick with it.
No, I cannot hear you.
I think you muted yourself, Scott.
Yep, we lost his audio.
And he can't hear us either.
I like the head hit.
Can't hear you. Cannot hear you. Cannot hear
I
you.
thought I hit something wrong.
Can't hear you. Just put him in a chat. Can hear. Oh yeah. There you go. There he goes.
There we go.
There you go.
I got
Lost you there.
Okay, I got to make sure that I don't accidentally hit the little mute button that I have on my headset, which I have now moved away from my arm. So
I'm just glad you recorded that head slap.
yeah, Scott Sterling. He's a fabulous goalie and volleyball player.
Oh yeah.
If you can repeat all you just said, so.
Oh yeah, well I was just saying I like the Scott Sterling shirt. Scott Sterling he's a fabulous soccer goalie, and let's just say he uses his head and he uses his face quite well. So it's worth looking. It's worth looking him up online.
No, I'm at the part you were saying. You were getting ready to say something on that 120-page document.
Oh, the 120-page document. Okay, the fact that the book that we're doing is 127 pages long, and it contains every one of the questions that we could possibly ever see on an exam. So
Wow.
That's why I like it. It's written in such a way that it actually flows pretty well. But I will also say that I tend to break from that book quite a bit. I tend to do things, at least at the beginning, a little bit out of order, because while it's laid out in a way that makes kind of sense, it's not laid out in the order that I like to do it. I like to do more of a story, and I think that it's important to do the story at the very beginning. So the first thing I'm going to do is give you kind of a little bit of background and say that no, I'm not going to teach you how to use a radio. If you came to the class expecting me to actually teach you how to use a radio or a particular radio or how to program a particular radio, you're going to be sorely disappointed. I once had somebody tell me that this class was the biggest waste of time in his entire life, which I found interesting and a little bit insulting, but it's the only time I've ever heard it in 43 times that I've done this.
Wow.
So this is a nice big class. I love the fact that you guys are all here. I love the fact that you guys are optimizing my use of time. I will say that it's a big class. If you're not talking or asking a question, you've got the ability to mute yourself. I don't typically mute anyone unless there's like a dog barking in the background or something. So I'm going to ask you to be judicious in your use of your mute button. Feel free to cut in at any time with a question that you might have, just by unmuting yourself and saying, "Hey, Scott," or something like that. I don't typically see hands up on the screen or, the little hand up icon. The easiest way to get my attention is just to get my attention. So even though that's not what they taught you in school, that's how we're going to do it here. So that being said, why are we here? Why do you need to take a radio licensing class? Let's hear your opinions, everyone. And this is where you unmute yourself and don't be shy.
Well, I'm going to
The
give you
FCC
mine
told us
first.
to.
Okay, sorry. This is Hydro Vladimir.
Vladimir, go.
Yeah, I'm retired military, so I've done a lot of stuff with military radios, but never with ham radios. So I'm right now the liaison for the ham radio operator here in Fort Bend County, and they keep asking me to get the license. So
Good.
I want to know more about the technical part side, like the words, the tests, all the how the test is composed, and all that stuff before taking the test and be able to be understanding the test, right? So
Okay, good.
I'm not here to learn about the radio. I'm here to learn about the study guide and why they made it like the way it is. in the
Okay.
test.
Other opinions.
I think it's also something that it forces you to to really go underneath and study the tenets of ham radio, so that
Okay.
you can be competent. And I think that in itself is it's quite a journey.
Okay. Other thoughts.
I
Yeah,
think that they-
Me, oh, I'm sorry. Yeah.
Oh, never mind. Go ahead. Sorry.
Misael, go ahead.
Oh, thank you. And my apologies for doubling up there. For me, it's understanding the complexity of ham radio, but also maintaining compliance with the FCC so they don't take away my equipment.
Okay. That's a good
I'm
one.
here to learn about antennas, and I find that propagation very difficult.
Okay.
But there's a lot of useful information in the test, like I don't want to say troubleshooting steps, but a few troubleshooting steps to, I guess try and figure out what's going on.
Okay. Other
Like
ones?
why is this, and why am I not getting my signal out when I'm in this forest or heavy vegetative area? Because it absorbs the signal.
Right. Okay. Other ones?
I would say that the reason why they got the law, or if I understood the question correctly, it's because you need to get your license because it shows that you have at least a basic understanding of two important things: the laws regulating the activity and the safety regulations that are involved. Because sometimes if you got a lot of these handhelds or whatever, you're kind of okay. But when you start getting into the desktops and antennas and all that, you can take a hell of a shock if you didn't know what you're doing. And then if you get it all set up with a friend that knows what they're doing, you can be on channels that you're not supposed to be on or frequencies you're not supposed to be on. So having a license shows that at least at that level, you know the safety and the law, and that should cover you.
Yep. Okay. And actually, notice what I just wrote. So you don't kill yourself or anyone else. Okay. That's number one. And number two is okay, this is serious. This is true. You don't kill yourself or anyone else, and you don't crash a plane. Now, the reason is that, okay, let's take a look at, we're gonna look at a frequency spectrum here, and this will make more and more sense the further we go in. So I'm going to hopefully open this up, and I'm going to share my screen. Here we go. Can everybody see this screen?
Yes.
Big, pretty picture, right?
Yep.
Okay. So this is a good chance for everybody to get used to their different views. Up at the right-hand side of the right-hand corner, upper corner of the screen, you will have like gallery view, side by side, et cetera, et cetera. I'm doing a share of this screen. Notice this says United States frequency allocations. Notice that it's this monstrous patchwork of stuff, right? And
Yeah.
everywhere you go to zoom into something, you will see that they actually all mean something. Every one of these areas is associated with something. So anywhere that you see, for instance, this teal section between, let's say, 420 and 450 megahertz, This stuff will make sense sometime in the next 8 hours or so. Here's another one between 50 and 54 megahertz. Here's another one between 144 and 148. Notice this teal that says amateur, amateur satellite, etc. We also have all this other stuff around it: radio nav satellite, mobile satellite, fixed, space operations, etc. So we are essentially given these lanes. We have these lanes to operate in, right? That's no big deal. Okay. I mean, everybody has that. That's how the radio spectrum is laid out. Now, beyond that, however, we have, for instance, up here, this area that says land mobile fixed right here. This is also known as the Family Radio Service and GMRS. You might, if you are familiar with these, you might notice frequencies that look like this. These are the General Mobile Radio Service, which is GMRS, and Family Radio Service, which are the little blister pack handheld radios that you can go to the store and buy and use without a license. So, what is the difference fundamentally between those and what we are doing?
Wow.
Let's hear it.
That's a good question.
Yes.
G-
Okay.
GM I'm sorry.
But-
GMRS does not require a test. It does require licensing.
Yep.
It's 10 years and $35. The license covers yourself and your immediate family,
Yep. Okay.
including uncles, aunts, grandparents, and so on.
Right. Okay. So here's a radio. Let's talk about the fundamentals of a radio.
That is a beautiful radio.
Isn't it though?
Mhm.
Here's display, here's some buttons.
Yeah,
Okay.
I'm very impressed.
Thank
Yeah.
you. Okay. So this is an FRS radio that you go to buy. This has a transmit power of about 0.8 watts,
Yeah.
depending on what you're doing. This could be more. It could be up to 2 watts. So this right here has an antenna that is permanently attached. You can't take it out. You can't take it off. Everybody see this okay? I'm
Mhm.
still getting used to this
Yes.
slightly new whiteboard where I can zoom in and stuff.
Mhm.
That's actually something that they added that I do like. Okay, so
I cannot see your whiteboard.
then you have to look at your different views because I'm sharing a whiteboard.
Yeah, it
So-
says connection error. It will pop up for a split second and then gives me a connection error.
That I can't explain.
You might need to check your version of Zoom, and you might have to do an update.
Yeah.
Okay, I just
Just-
downloaded this for the first time this morning, so I may have done something wrong.
Okay. Okay, so notice we have our antenna that's permanently attached, which means you can't, for instance, take that antenna off and hook it up to an antenna that looks like this, which is on top of a 50-foot tower. Right? So this is also channel 1 up to channel 22. You have no frequency agility other than selecting those individual channels. That's all you get. So let's move up to something called GMRS, which is a General Mobile Radio Service. You could actually take off the antenna in GMRS and hook it up to a beam antenna. Right? This is a licensed thing. You're still limited in the number of channels you use. They're actually shared. But the fact that now you are not limited to 2 watts, you can actually have a mobile radio that can be a 50-watt radio because you need to get a license. It needs to be approved, but you still don't have any frequency agility. You can choose channel 1, channel 2, channel 3. The radio is pre-programmed, and that's what you get. So now what we're going to do is look at what makes amateur radio different. So we're going to look at what we call the 2-meter band, which we're going to get to in a second. 2-meter band goes from 144 to 148 megahertz. Okay, that is our frequency allocation. Here is a radio again. Sorry, the antenna is a little wonky on this one. Okay. What is our ability to select a frequency between that 144 and 148 band? Those are different frequencies. How many different frequencies are there to choose from that we can do that with? We can go anywhere. We can actually take our radio and tune it anywhere in that band, so long as our entire signal falls inside the goalposts. So
And that's the tricky part, yeah.
So we have frequency agility. We can program our stuff anywhere we want. We can set our radio to any frequency we want, so long as we're following the FCC rules and it stays completely within the goalpost. Other things we can do. We can, for instance, take off our antenna and hook it up to a big beam antenna on top of a tower. So our small radio now becomes a big radio that can change frequencies. The other thing about it is that this radio right here, is there any requirement that this radio is something that we buy somewhere? If we want to build something that looks like this, with a bunch of knobs and dials that we built ourselves, we are allowed to do that. We are actually licensed to build our own stuff. When you go and buy a radio, it is pre-certified to do something. When you build a radio, it is not pre-certified to do something. You are assumed to have gone through the licensing process to know what works and what doesn't, and to verify and be able to verify that what you built actually follows all the rules. And that is part of why we get licensed, whereas, for instance, Family Radio Service, etc., GMRS, the licensing process is much more simple. So the question then becomes, well, let's say that I don't really care. I just want to operate a handheld radio. That being said, why do you have to get licensed?
So that you understand and respect the different frequencies, and I believe.
Because your license permits, even if you're never going to build your own stuff, your license permits you to do it.
Okay.
So because your license permits you to do it, you have to go through the process. So the other thing we can do is we can hook up our radio right here, which we built ourselves. And we can hook it up to a box. We can hook it up to an amplifier. We are legally permitted, depending on the frequency band, even with a technician license, which is if you'll remember, you all are studying for the technician license, right? That's the first level license. There's also a general, which has more privileges, and an extra class, which has even more privileges. You are going for the very first license class, right? The very first license out of 3. How much power are we allowed to transmit with, even with a technician class license? Does anybody know this yet in the studying that you've done?
200.
1200.
One,
Yeah,
1500.
1,500 watts.
Yep.
Okay. And now, is there any limit on what you can build for an antenna?
No.
No. You are allowed to hook it up to an antenna with, let's say, 30 decibels of gain. 30 decibels is a lot. We're going to cover decibels in a little bit. Decibels are a logarithmic scale. So 30 decibels is a lot of gain in the forward direction, pointing that direction. So let's say you operate a system that uses 1,500 watts and you have 30 decibels of gain. So an antenna, for instance, that would have 30 decibels of gain, you might recognize, oh God, this is, go away, go away. Okay, an antenna that has 30 decibels of gain might look something like this.
A satellite?
Satellite dish, yeah. So, can we repurpose a satellite dish?
Sure.
Sure.
Yes.
We can
Yes.
do anything we want because we have a ham license. We're allowed to do that kind of stuff. Can this satellite dish be 10 meters across?
Yes.
Sure.
Yep. That satellite dish can be 10 meters across. That could have enough power to have enough gain to have, let's say, 30 decibels of gain. And we're putting 1500 watts into this, which means that we have the equivalent pointing upward or wherever we're pointing it of 1,500,000 watts of RF energy.
Wow.
Wait, there's not a limit. We can do that.
That's a
That's
lot.
why, yes, exactly. That's why it is important to understand why you're getting licensed. Because if you aim that at somebody or something, you can actually do some serious damage. So, that being said, that is why you're in a licensing class. It's like essentially you're getting a license to drive a Ferrari. Not only drive a Ferrari, you're getting a license to build your own Ferrari and then put it on the road legally. So, so that and the fact that, okay, well, let's say that you build you build a transmitter and it's operating on, oh, let's pick this frequency right here. Let's go to 1296. There we go, right up here. This is a very popular moon bounce frequency where we aim our antennas at the moon. Right? So you've built your own radio, you built your own antennas, you built your own amplifier. What's this aeronautical radio navigation? Anyone know what that is?
Would that be
Something
like
to the FAA, I guess. I don't know.
Yeah, that's the
Is that
FAA.
Is that airport?
That is, yeah. And notice that our signals are right near theirs, right? So what happens if your transmitter is a little bit off frequency?
Ooh, not good.
Not
Yeah.
good.
over.
You're talking to a tower, hopefully.
Well, you're interfering with tower communications and
yeah, but-
radar. So that's why we need to know what we're doing, because your license, even the very first license, the 35 question test that you hope to take and pass, covers the ability to do this stuff. You can get into a lot of trouble, which means that it's my job to make sure that you understand all of this stuff before you get to that point. All right. Everybody ready?
Yeah, it's interesting.
Okay. So we are covered by amateur radio is covered by Jennifer. It looks like you got your hand up. I actually
Yeah,
saw that.
sorry. Do you have a PDF of that last page that you had on your
That's actually in the it's in the
materials I didn't
And
print?
in the
Okay,
zip
that-
file that I sent.
Frequency chart. Somebody just shared a link, 9:13 a.m. So go to the chat and you'll find the link there.
Okay, you're awesome. Thank you.
And it's also one of the things that I sent in the zip file.
And that I probably ignored. Thank you.
Okay. All right. Okay. So that being said, now you understand kind of why you're here. The fact that you're basically given a lot of leeway when it comes to getting on the air that most other services, this is actually a licensed service, do not have the ability to do. They're not given this freedom. So, all right. So the next thing I'm going to put up, I hope everybody can see this, is the electromagnetic spectrum. And you might all notice the fact that way over here on the right-hand side of this, you see these things, right? Does that look familiar to anyone?
Yeah, IR, UV,
Yes.
and X-ray.
Yeah, but
Yeah.
what's right in the middle? What's right in the
That's your
that's
color
all,
spectrum.
The green band or the
Visible light.
yeah, that's
visible light. Yeah.
that's all of our visible light. It's this tiny little part of the electromagnetic spectrum. The electromagnetic spectrum also contains X-rays, ultraviolet, infrared, and then way down here on the left-hand side, this is all radio.
Wow.
Radio is actually just a different color of light, which we're going to get to right now. They are indistinguishable from each other with the exception of one being visible because our eyes are designed to see it, one being X-rays that can go through our skin, so we can use photographic film to see what it looks like. Look at our bones. And then at the far end of it, radio waves, which we can't see and we can't sense, so we have to build equipment to pick them up. Okay, so here we go. Whoops, that's not what I wanted. We want this, and there we go. Whiteboard, new whiteboard. Okay. It keeps telling me that I want communicate with comments, blah, 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 and keeps putting up all these annoying messages. Okay. So now we're going to start with math. If I were to draw this properly, what is that?
Looks like a crosshair.
Yep, looks like a crosshairs. All right, but what goes around the crosshair?
Degrees.
That would be a circle. Yeah, okay.
Degrees.
So, how many degrees are in a circle?
360.
360 degrees. What's the mark all the way at the right-hand side? How many degrees? By
90.
default, that is actually 0.
Oh, 0. Sorry.
Yep, all the way on the x-axis is defined as our 0. We add our angle up and around and counterclockwise direction. This is 90 degrees. This is 180, 270. And how about when we get back to the start?
That's 360 or 0.
360. Yeah, it has a lot of different names. This could also be 720. Could also be 1080. Now, we could have also gone the other way. And this would be minus 360.
Can I ask you, why does it start at the horizontal, at the X, and not up towards the top? I'm just curious.
Because that is the way it was defined.
No, there's ways to find. Okay.
Yep.
I never saw that.
Yep. This is all of math, all of trig. It always starts on the x-axis.
Ah, okay. Okay.
All right. So this is the y-axis. All right. So what we have to do now is say that we're going to be okay, this thing is going to piss me off again. It says follow Brandon. I have no idea why it's saying that.
Maybe Brandon likes you.
Yeah,
I apologize. I don't know. I touched the screen and it did something. I apologize.
see, this is what it's not supposed to do, and this drives me crazy. This is something that Zoom added, and now I don't know what to do.
You'll be okay.
Deep breath, you're good. Move forward.
Yeah. Well, the problem is I can't see my whiteboard now. Damn it.
Yeah, on this side, it looks like you have it set at view only.
Yeah, I'm sure I do. But
Okay.
It's asking everyone to go ahead and sign on in, which I would say avoid that at this point. Just do the view only.
Yeah. Gonna be the end of me. This is really gonna be the end of me. Okay, can everybody see this whiteboard?
Yes.
Yeah.
Okay. Don't touch the screen. Okay. So because I use the whiteboard a lot. So what we're gonna do now is I'm going to draw the circle again, like this. And we start at 0 degrees and we go around this way. So when we get up to the top, we're at 90 degrees. This is 180. This is 270. And now we're going to look and see how far above this line, the horizontal line, we are. When we get up to the top, if this is a unit circle, which means it has a radius of 1 unit, how far above the line are we?
45 degrees?
No, when we're all the way at the top.
Oh, 90.
Yeah, and so how many units above the line are we?
I'm
If
gonna say
it-
1 unit.
1 unit.
One.
Yeah. So
1
we.
unit.
Yep. Okay.
Okay.
We started at 0, and at 90 degrees, we're at 1 unit above. How about at 180?
We're 2 units.
No.
Oh, no?
How
One.
about,
We're
how
back.
many?
We're back to 0.
We're back to
0 and
0.
90 is 1 unit, so I
Yeah.
figured 90 and 180 is a second unit.
No, I'm asking how far above or below.
Oh,
Okay.
1 unit.
Okay. How about a 270?
Um,
-1.
This one,
-1. How about a 360?
0.
0.
0. Connect the dots. That has a name. Anyone know?
sine wave.
That's a
Sine
sine
wave.
wave. Okay. So a
Sine
sine wave is a representation of what happens when we go around a circle. This is known as a sine wave. Actually, to be accurate, this is actually not a sine wave. This is a cosine wave because, well, actually, no, it isn't. This is a sine wave. Sorry, my bad there. This is actually a sine wave. If we were to look at how far left or right we are using a different color pen, let's use this one. If we were to look at how far left or right of the vertical y-axis we are, then at 0, we would be at 1, right? Because we're looking left and right. And then we'd be at 0, and we'd be at -1, and we'd be up there, and then we'd be up there, and we connect the dots, and we go like that. That's a cosine wave. And what's the difference between the two?
Not sure.
One is just shifted in time.
Oh, shift in time.
So will that fall into like in phase and out of phase?
That falls into in phase and out of phase. So this is actually a 90-degree phase shift. One is shifted 90 degrees from the other one. That's exactly right. And if you think about it, where this starts off at 0 and here, it makes sense that one is shifted 90 degrees from the other one. They start this axis here and this vertical axis here. Did I do that? Oh, geez, come on. Yeah, I did do
See
that.
it. There you go.
Okay. I'm sorry. This is a mess. You guys can see it, but my screen is an absolute mess. That's awesome.
That's because Zoom hates us.
It does. It didn't used to. Okay. So now what we're left with is these things that are shifted 90 degrees apart. And what we can do now is we can say that since they're shifted 90 degrees apart, we can look at this down here and see that they are actually shifted 90 degrees. Now,
Yeah, when we first got here.
so one thing that's important is to note that if we were to continue going around and around the circle, we would have this. And if we were to go back the other way, we would have this. So that means that these waves actually don't really have a start and end point, do they? They actually don't begin or end. They go on all the way to the left and all the way to the right. So let me see if I can do that. Okay, there we go. So they go all the way to the left and all the way to the right. That means they actually go on forever, and we're actually just viewing a portion of it. To make it simple, we just usually look at one complete rotation. Okay, so now I'm going to erase this one. Clear page. We're going to start again. We're going to say that we're going to now draw that circle again. Circle again. Goes around in this direction. Starts at 0 degrees. It maps out this pattern. Okay, what do we call that?
Cycle.
Yep, also known as a wave. We call that one cycle. And now what we're going to do is we're going to look at that. And we're now going to say, we're going to add a speed to this. We're going to say that we go around this thing once per second. One time per second. So how long does it take to map out this entire pattern?
1 second.
It takes 1 second. If we do this 2 times per second, how long does it take? Don't say 2 seconds.
2 cycles.
0.5.
Yeah, it takes a half of a second because we're going around twice per second. If we go around
twice per second. Okay. All right.
if we go around 12 times per second, how long does it take to make that pattern?
1/12 of a second.
A 1/12 of a second. Yeah. Okay. So we can also now look at this and say, if it takes a 1/12 of a second and we're going around 12 times per second, how many of those patterns will this make in 1 second? It'll make 12. Okay, so a unit of a thing per second, this has a name that's called a hertz, named after Heinrich Hertz. Whatever that thing is, it could be a clap, it could be somebody tapping the table, it could be any number of different things. A number of things that happen per second is a frequency. And that's measured in hertz. Number of things that happen per second. Okay. So, since we now have a frequency that is relating this circle, think of it as a merry-go-round, and it's also making this map, and we also have something known as a period. Period is just actually the inverse of the frequency. So if we have 12 hertz, it takes a 1/12 of a second to make one full circle, or one map, one cycle, one time around on the merry-go-round. So now we have related this thing called frequency to this thing called period. And because this is time in seconds, this is 1 divided by time, also known as hertz. Okay. So now what we're going to do with this is we're going to take the thing that we've just done and say we're going to take this circle, and instead of the merry-go-round looking like this, we're going to change how it looks. We're going to look at it edge on. We're going to stand it up on its side and look at it edge on.
Oh, wow.
And that is drawn really badly. Let's try again. We're looking at it edge on. As you are sitting on this merry-go-round, you are going up and down and up and down and up and down and up and down and up and down. If we were to just look at your position, the distance from on the up and down, we would see this dot going up, that's you, and then going down. And it would just go up and down and up and down and up and down and up and down. What we're now going to do is take this merry-go-round and we're going to move it slowly that way. By doing this, what happens to that picture? Instead of just going up and down, it's now moving this way. What is that a picture of again?
Sine wave.
That's a sine wave, yeah. Okay. So the question that you probably have is, why are we bothering to do this? Well, what it turns out is that we now have a velocity, and that's usually measured in meters per second. And we also have a frequency. of how fast of essentially what's happening to that merry-go-round. And that is measured in cycles or things, full times around per second. So we have these two things, meters per second and cycles per second. And we now have this thing that's moving to the right. Well, due to math, we can do certain cool things. We can decide arbitrarily that we're going to divide something by something else. For those of you who haven't done a lot of math yet, math is really cool because so long as you remain consistent, you can pretty much do whatever you want with it. We're going to divide, for fun, velocity by frequency. And what do we get if we divide velocity by frequency? We get meters per second divided by cycles per second. We divide those, the per seconds cancel out, and we get meters per cycle. So what is that now? Somebody chime in. When we get meters per cycle, what do we now have?
A band.
Well,
Wavelength.
a wavelength.
Yeah, you have a wavelength.
Because it's plotting out a physical distance between identical points on that wave of how far it traveled.
So Scott, to clarify, that is the bandwidth.
That's a wavelength.
Okay,
That is a wavelength.
thank you. Thank you.
So by dividing velocity by frequency, we now have something called a wavelength. So this is actually very important because now what we're going to do is take this thing as we erase all of this, and we're going to start with a circle that's going around and around and around with a frequency. So you're sitting on this circle, you're spinning around the circle at a certain frequency. All right, so you're on the merry-go-round. We then turn the merry-go-round on its side. So now it just looks like you're going up and down. And now we're going to move this sideways. If you're moving very, very slowly, what's this wave going to look like?
Narrow, yeah.
Very compressed. Your wavelength is going to be very small. However, if you move this wave really, really fast, what's going to happen to it? It's going to stretch out a lot. So this is a very small wavelength, and this is a very large wavelength. For wavelength, we use the Greek letter lambda. That is our wavelength. We measure it because we follow the meters, kilograms, and seconds, MKS units. We measure that in meters. So our wavelength, we measure in meters. So remember what the only difference was right here. This is a low velocity, and this is a high velocity. And what did it do when we increased our velocity?
It stretched it out.
It made a larger wavelength. When we shrunk our velocity, it made a smaller wavelength.
So when you say velocity, is there another like the speed of the wavelength? Is what
It's the
you're saying?
speed that the thing that's making the disturbance, which is the merry-go-round, is traveling through space.
So the cycles per second, or is that, or no?
That's part of it, but then you also have the thing that's moving. And here, let me demonstrate this by, we're going to, are there any musicians here?
Yes.
Yeah, okay. So does anyone know
Yeah.
what what an A is? A tuning A, how many hertz?
440.
440. Okay, well, did you ever think and did you ever, you ever stop and think what's 440 hertz? Other than an A. What is 440 hertz? What does it mean?
It's in the
A
70
wiggly
millimeter
line.
band, ain't it?
It's
No.
440 hertz per second of a vibration.
Right. Here we go. That means that if we were to draw this circle, that means that we are going completely around how many times per second?
440.
440 hertz.
440.
440 times per second. 440 revs per second. Okay. So this is our vibrating guitar string. 440 hertz per second, or 440 cycles per second. Going up and down, 440 per second.
Oh, I see. Okay.
Okay, so ready? How fast does sound travel through space, through our atmosphere? What's the speed of sound?
760 something miles per.
Yeah, it's about 330. No, it does not travel at the speed of light. Who said that?
I didn't say light. No, sound. Is,
No, somebody said the speed of light. We're talking
No.
about sound.
Yeah, no, they're
330
not the
miles per
same.
second.
330 meters per second. Right? And what is the definition of a hertz? It's a cycle per second. So we can now divide one by the other. We can say we want to divide our speed divided by our frequency and get 330 meters per second divided by 440 cycles per second. These cancel out and we get there we go. At the speed of sound, that A that you're using to tune makes a wave that's how long?
0.75 meters.
0.75 meters as it's traveling through the air. That is how far apart the wave crests are. That is how long one wave is. As that
So
note
it's not
is
quite a meter. It's
Right.
3/4 of a meter long.
Yep. That is how long it is between successive wave crests,
I see.
75 centimeters.
So
That
the
is
sine,
one wave.
sine wave would be like 0.75 from start to finish, 3/4 of a meter per second.
No, 3/4 of a meter, period.
Oh, okay.
It's not time based.
Oh, okay. Just
It's just
all right.
distance. So that's 75 centimeters in length. So what does that mean? Is there anybody here like myself who plays a wind instrument?
Yes.
Okay. How do you tune a wind instrument?
Wind instrument.
Play a clarinet. How do you tune? What do you play?
A C.
No, I mean, what instrument do you play?
Oh, saxophone.
Saxophone.
You
Okay.
adjust the reed.
You adjust the reed.
Yeah.
Yeah. So that changes the frequency. What else could you? Does anyone play a woodwind? Flute.
Your
Yeah.
throat's
Clarinet.
another way of adjustment.
Yeah, you have to adjust the positioning of the mouthpiece to.
You have to
Yeah, you're
adjust. That's right. You have to
Lengthening the tube.
You're
or
lengthening the
shortening it.
tube. That's right. So
Shortening the
how do you lower a note?
Pull out.
You lengthen the tube. That changes the frequency. That changes the resonant frequency of the column. So longer wavelengths are lower frequency and vice versa. Now we're dealing with sound in that case. But now we're going to take that sound and we're going to use another medium. We're going to take that circle again and have it going around in around counterclockwise direction. Then we're going to turn it on its side. So it's just moving up and down. And now we're going to have it moving at a different speed. And now we're going to use the speed of light. That is C. That is 3 times 10 to the 8th meters per second. Remember, we said the speed of sound was 330 meters per second?
Yes.
3 times 10 to the 8th meters per second is the speed of light, or 300 million meters per second. They're not really comparable, are they? This is it's basically a million times faster. Light travels at the speed of light. Okay, and since light travels at the speed of light, does everybody remember that we showed
Oh, you're off again.
there we go. Can everybody see that?
I couldn't hear you
Yes.
there for a bit.
Okay.
You went mute.
Yep. Can everybody
Yeah, we can
okay.
see.
Okay,
Yes.
so light travels a million times faster than sound does. Sound also requires a medium, that being air or water or any other solid or gas to travel. Through air, it's about 330 meters per second. How about light? Light is an electromagnetic wave. How fast does light travel?
186,000 miles per second.
Or you can forget that, 300 million meters per second. We're going to only work in meters per second.
Okay.
And okay, so we're going to work in meters per second. Light travels at 300 million meters per second. But what's important to note about radio waves? If you look at that picture there, what do you see on this electromagnetic spectrum? Radio waves are
High
How-
frequency, very high frequency, and ultra high frequency.
yeah, but what about radio waves?
They're long.
They're long. That's right. They inhabit
Mhm.
the same space as light. Radio
Are you drawing a
waves.
picture, sir? It's Scott, because I don't. My screen's blank. I don't know what happened there. I'm not seeing anything on the screen. I'm just wondering if you're drawing. That's all.
I'm not yet.
Okay, I just want to make
There's
sure.
there's tabs across the top of your screen that have his screen share. He's sharing his screen.
Okay, I just want to make sure because you just went. All right, sorry. Go ahead, please.
Okay, so I'm going to
Here we go.
make sure that I unshare this. Okay, can everybody see that?
Yep.
Radio is light. It's just a longer wave. A much longer wave. Radio is the same as light. It's just a longer wave. So light is typically going to be, let's say, 480 nanometers. Radio is typically measured in the meters. Nano is 10 to the is 0.000000001. So this would be 0.0000048 meters long. That would be like a blue light. A radio wave might be 1 meter long. That's the only difference between all this stuff. So what we're going to do is say we're going to take a circle again. We're going to spin it around. We're going to have you sitting on that merry-go-round, and we're going to spin you around 150 million times per second. Don't worry, you're probably not conscious at this point. And we're going to take that and rotate it on its side. And how fast will that dot be going up and down? How many times per second?
150 million.
150 million times per second. So our frequency is 150 million hertz. But now, what is the speed of light in meters per second?
300 million.
Yep. $300 million meters per second. So we're going to take our frequency, which is F, and our wavelength, or sorry, our speed of light, which is the letter C, which is 300 million meters per second. We're going to divide C divided by F. 300 million divided by 150 million equals what?
2.
Yep.
2.
All that, and we get a 2-meter wavelength. That's a wavelength. How big is 2 meters?
I think it's about 6 feet, give or take.
Yeah, 6.5 feet, 7 feet. So what that means is we actually have a physical thing that's in our realm of like physical lengths that we can understand that is being generated by a frequency that is 150 million times per second because it's traveling at the speed of light.
Oh, I see.
So, okay. So now what we're going to do is we're going to modify that a little bit. And instead of just having a circle, what we're going to now do is draw this in multiple dimensions. Okay, this is called an electromagnetic wave. So there are 2 parts to an electromagnetic wave. Anyone have any guess what the first one's called? Well, I heard electric. Yeah, okay. So we're going to draw our electrical portion of it, and it's going to look like this. Okay, and then what's the other part of it?
Magnetic.
It'd be magnetic. Yeah, okay, very good. Very good. Okay, so now we're going to draw our magnetic portion of it, and it's going to go like this. This is I'm trying to draw it so that it's at 90 degrees. So this axis is the magnetic axis, or the axis of motion of the magnetic portion of it. And this axis, the vertical axis, is the electrical portion of it. The wave, the energy of the wave, travels to the right.
Okay. Hey, Scott, so
Uh-huh.
that magnetic whatever axis, can we call that a z-axis?
That's actually let's see, X, Y, Z. Yeah. Usually in this case, I mean the z-axis, I would actually call the magnetic in this case the x-axis. Let's make sure I got that right. Let's see. X, Y, Z. Oh, you know what? We're gonna change the names. Doesn't matter how long you're doing this, sometimes you still mess it up.
Sorry.
So, no. So, okay. My bad. Okay. And so we're going to make everything correct, we have to make this the electric. What is going on?
Oh.
Thank you, Zoom. My goodness.
Gremlins and everything.
Yeah. So this is the did it just turn it into a triangle? Yeah, it did. Good
That's
Lord.
affirmative.
What the heck, Zoom? Okay, we're gonna do it again. We're gonna just do it again. It says smart drawing. What the heck is smart drawing? It looks pretty dumb to me.
It looks like symbols.
It does.
It looks like it's trying to draw something like a flow chart or something.
Yeah.
It's in, okay, now it's gone. Never
Yeah,
mind.
we're gonna try again.
Symbology. It's giving you symbology, I guess.
Uh-huh. Okay. So we're gonna draw our electric, and we're gonna draw our magnetic, and then we're gonna draw our energy flow. So here's our electric axis. It's gonna go like this. And then we're gonna draw our magnetic axis, and it's gonna go like this. And the energy flow is going to be in this direction. Okay, so if I drew this correctly this time, and Zoom doesn't try to screw anything up, our magnetic field is going to oscillate in the y-axis, up and down. Our electric field is going to oscillate solely in the horizontal plane, like this. That's our x-axis. We're going to have it like that. Why do I see a dot moving? Okay. And then our energy again is going to be moving to the right. So that's the direction of travel. That's actually represented by the S, by the letter S with an arrow. That's called the pointing vector. This is our E field. And the magnetic field is known as the H field or the B field.
So is there a degree difference between the magnetic wave and the electrical wave?
They are always perpendicular to each other.
Okay.
And so the one thing that's really important about it is that, okay, everybody, you have to hold up your right hand, not your left hand. Has to be the right hand. Okay. Everyone stick up your thumb. Okay. Your thumb is your electric field. Now stick out your index finger, second finger. That is the magnetic field. Now, your middle finger, if it sticks out in a position that's comfortable, is the direction of travel of the energy. So it's always electric field, magnetic field, and your index finger is the direction of travel. And notice they're all perpendicular to each other if you hold up your hand properly. Each of those is at 90 degrees to each other, and that's called the right hand rule.
Oh.
Right. And that's why
it
it doesn't work with the left hand. Don't try it with the left hand because you'll be wrong.
You lefties out there, don't try it.
Nope. I'm sure there's things that the left hand rule follows, but this is not one of them. Okay. So now what do we have? We have basically combined a couple of different things. Okay, we've combined going around in circles. We've combined frequency. And we've combined velocity as we turn it up and down and moved it side to side. That is actually how fast energy travels through the speed of light is how fast energy travels or a wave travels through a vacuum. Air is actually not quite a vacuum for light waves, but it's almost indistinguishable. So, okay. So beyond that, we then have, that's our velocity. We have a frequency. And now we have a wave that is carving out a path as it travels through space. We can now relate these by saying C is equal to F times lambda. That's what that means.
I have a question.
Yep.
How come all these frequencies out there in space, how come they don't I mean they don't collide with each other and stuff like that?
They do. They do all the time.
But it doesn't affect them though?
Energy is energy. If it depends when they arrive.
Wow, that's interesting.
Well, yeah, and I mean basically then you start to look at the wave particle duality and the fact that sometimes a photon is a packet of energy that has a frequency associated with it. It can be viewed as a particle, and it can also be viewed as a wave traveling, depending on how you view it and when you view it. But I'm not going to get into that for this class.
Yeah, just was wondering. That's all.
Yeah. So yes, they do actually interfere with each other. They actually do. Another thing that's important to note is that, again, we have, what are the fields? We have our electric field.
Energy flow and magnetic flow.
Right. We have our magnetic field going this way, up and down. and that our energy flows that way. Again, that's the direction of travel. That's the S vector. The direction of the E field as it oscillates is known as the polarity of the wave by definition. So if this is the horizontal axis, because it's horizontal to something that you recognize, like the surface of the Earth, we call that wave that is making that pattern a horizontally polarized wave. If the electric field is going up and down, perpendicular to the Earth's surface, we call that vertical. That's, that's what we think of as vertical. We call that vertical polarization. If it is actually rotating in time, in addition to this, because there's nothing that says it has to always be one thing. If we have something that actually rotates, that's actually called circular or elliptical polarization. And it can be rotating clockwise or counterclockwise. So, but what's important to note is that polarization of a wave is defined by the direction that the electric field is going. If it's horizontal, we call it horizontal. If it's vertical, we call it vertical. Okay. Let's see. So now we're going to write out that equation again. And this is the easiest way to remember it. 300 F lambda. We make a circle like this because C is equal to F times lambda. Well, C is 300, F is F, and that is that. And one thing that we have done is we've substituted 300 for what was that 300? What should it be?
300 million, which is the speed
300
of light.
million, that's right. But now we just did away with a factor of a million. Why would we do that?
Simplify the math.
Simplify the math. And also, how do we usually measure frequencies? What frequencies are we dealing with?
Hertz.
Not just hertz, though. Let's take a look at our
kilohertz and megahertz.
Yeah, so let's take a look at our FM radio in your car. You tune to a frequency of 101.1. Let's go 102.1. Let's go to a frequency of 102.1. What does that actually mean?
Classic oldies music.
102.1 megahertz. If you look at the dial, it actually says megahertz.
Megahertz.
Which is actually 102,100,000 hertz. That's actually the frequency. To simplify things, we substitute a million. Mega means a million. Mega means a million. So by putting that M there, which indicates that there is a factor of a million taken out, we now can write it 102.1. So now, because we factored out a million there and we factored out a million out of the 300, this is in megahertz and this is in meters. And now we can do our math really easily because we have the circle, which you can regenerate anytime you like and say, okay, what is the wavelength of a frequency of 150 megahertz? Well, to do that, we draw our circle, 300, and then 150, and then our wavelength. Well, we don't know this one. Cross it out. And look, we're even left with a divisor bar. 300 divided by 150 is?
2.
2. Our wavelength is 2 meters. That is the wavelength that is carved out by a frequency of 150 megahertz in free space. Let's change it a little bit. Let's say we now have a frequency of 100 megahertz. Going to draw our circle again. 300 F lambda. We don't know our wavelength. We know our frequency. It's right there. Don't know this. 300 divided by 100 is 3 meters. Our FM radio has a frequency of about 100 megahertz. that has a wavelength in space of 3 meters. That's the wavelength of an FM radio signal in space. It's about 10 feet long. So now let's change this up again. We're going to take our AM radio station, which is, let's say, 1,000. Except how does our AM radio station identify itself?
Kilohertz.
It's in kilohertz. Kilo means 1,000. If we wanted to convert that to mega, we would have to mean that, oh, well, there's actually a factor of 1,000,000 thrown in there. So we're just going to take the kilo and we're actually going to get rid of it and multiply that by 1,000. We're going to replace it back with 1,000. All right. Well, how many millions is that? That is 1 million. That is 1 megahertz. Now we can draw our thing again. 1 lambda is equal to 300 divided by 1, which is how long?
300.
300 meters long. Right. How big is 300 meters?
Oh gosh, that's pretty damn long.
Yeah. Well, how long? It's 1,000 feet.
900.
It's 1,000 feet. It's 1,000 feet. So when you're driving down the road and you see an FM radio station, what will you expect to see for an antenna? The wavelength of an FM radio station is about 3 meters. What you'll see on the top of a tower is something that looks like this. A couple of loops that are a few feet apart. What you'll see with an AM radio station is you'll see a big tower and a big tower and a big tower and another big tower that are like 250 feet high. Because the only way to make a wavelength, the only way to make a wave with a certain wavelength is to have a piece of wire that is at least 1/10 of a wavelength long. Ideally, you're going for 1/4 of a wavelength or even a half a wavelength in length to actually intentionally make a signal or receive a signal at a given frequency.
Why is it 1/10? I mean, why 1/10?
Minimum of 1/10, just by experimentally.
Oh, okay. I'm just curious. I got that number. That's all.
It's I mean, a tenth of a wavelength antenna is going to be very, very, very poor, but it's better than nothing, especially if you're dealing with, let's say you need 1,000 feet of tower. Okay, that's not practical. So, all right, everybody ready for a 5-minute break?
Sure.
Okay. I hope everyone's doing okay.
Very good. Thank you.
Okay, and before we get going, I'm here to answer questions. So if you've got questions about what we've covered, now's a good time to talk about it.
You were talking about AM and FM bands, like
Yeah.
where I guess kind of going over it. So what's the difference between AM and FM?
We're going to get to that. It's they stand for modulation,
Okay.
amplitude modulation, frequency modulation. And it's modulation is how you put information on a signal. So
Sounds good. I appreciate it.
one is amplitude, one is frequency. There's also pulse width. There's also on-off keying. There's frequency shift modulation. There's phase shift modulation. And we're going to get to that. I think it's going to be today. I think. So if anyone is curious where we are in the book, we've kind of, again, we've sort of jumped around a little bit. If anyone's been, let's see, There's propagation modes. We're not doing propagation yet. So radio wave characteristics. I spend a long time on radio waves because I think it's really important to talk about radio waves. All right, let's get started again. Let's, oh, come on, here we go. So, do you have any other questions before we get going? I believe in building fundamentals because fundamentals are where all your understanding comes from. And the goal here is to get everybody a good level of understanding.
Can I ask a question?
Mm-hmm.
The last diagram that you did with the X, E, and Y axis with the electromagnetic field.
Yep.
How does that correlate with, darn it, dead key and modulation?
Not.
It
When you
doesn't.
say, when you say dead key, I
A
mean
carrier?
no, it has nothing to do with it.
Nothing at all. Okay. thank
Nothing
you.
at all. So x-axis, y-axis, and z. And I think Jennifer's in Canada, so we're gonna Jennifer, in honor of Canada, we're gonna call it the z-axis. Okay. I guess Jennifer didn't answer that. Okay. We're gonna call it the z-axis. All right. So again, here's our one. That's our E field, and up and down. That's our H field, and then this is our S direction, which is our direction of motion. And remember, it's very important. All of these have to be what in relation to each other?
Perpendicular.
Perpendicular. That's exactly right. If you remember that, you're in good shape. Okay, so now I'm going to go back to this chart here. And okay, here's that chart, or here's that little picture. And okay, so notice what we now have across the top of this chart. What does everybody see?
Frequency.
Frequency. That's right. And notice that every vertical bar has a mark on it. But what do you notice about those marks? Every one is what compared to the previous one?
Increased.
By a factor of what?
10.
By a factor of 10. Okay, we call these decades. And the reason we do that is because what is the actual space between 3 and 30 megahertz? How much room do we have in there? Between 3 and 30.
270?
27 megahertz.
Oh, 27.
Between 30 and 300?
270.
270. How about between 300 and 3000? 3000 megahertz is the same as 3 gigahertz. We have 2700 megahertz. Yeah. So notice that we call this range. By the way, you are going to be asked this on your test. I can guarantee it. So you need to remember which is which. High frequency, HF is 3 to 30 megahertz. VHF is 30 to 300. UHF is 300 to 3000 megahertz. And because it's a different prefix, we also call that 3 gigahertz. That takes into account an extra factor of 1,000. Okay, so this is very important because this means that on the entire high frequency spectrum, how much space do we have? Who's going to be the first to answer this? How many megahertz?
From 3 to 3 gigahertz.
27.
On the high frequency spectrum, HF, how much space do we have?
27.
27.
27 megahertz. On the VHF spectrum, how much space do we have?
207 megahertz.
And on the UHF spectrum?
2700 megahertz.
How about on the next one up? This is in shorter microwaves. Between 3 and 30 gigahertz. How much space do we have?
27,000.
27 gigahertz. Or
Gigahertz.
27,000
27
megahertz.
gigahertz. My bad.
These get 10 times bigger every time you go another step. Very importantly, does everybody remember this chart that I showed a minute ago? Right at the beginning of class. Remember, that was just like an hour ago. Does everybody remember this?
Yeah.
Yeah.
Okay. Notice, if I can figure out how to control it with my zooming commands. Okay, so notice, what do we have here on the left-hand side that I'm highlighting? How many megahertz?
3 megahertz.
3.
3 megahertz. If I go all the way to the right-hand side, what do you think it's going to say?
30.
30 megahertz. Oh, wow.
30 megahertz. That is the high frequency band. Okay, if I go down, the next decade is going to be 30 megahertz. And what's the right-hand side going to be?
300.
300.
300.
That's exactly right. So every time we go down another band on this chart, it also means not only is it the next frequency band down or frequency band bigger, it's got a lot more space. So on that high frequency band between 3 and 30 megahertz, we said we have 27 megahertz. On the 300 to 3000,
I see.
we have 2,700 megahertz, which is why we have so many other different services. But notice the kinds of things that we see here. Mobile satellite, space operations. Here's broadcast satellites. And we go even higher. What else do we see? Satellites, radio navigation, fixed satellites, broadcasting satellites. So I'm going to ask everybody here to think about that for a minute and tell me why you think you would see all those satellites, besides the fact that the frequencies get higher, so your antennas can get smaller and smaller, which means you can build more and more gain. What's a reason to put all those satellites on those really high frequencies where there's a lot of bandwidth available?
Distance and amount of information?
Not distance.
The velocity required to move.
Well, you said amount of information, right? So here's a question. Let's say that I am talking right now. What bandwidth is my voice taking up? My voice is probably going between, let's say, 100 hertz and 500 hertz, or 100 hertz and 700 hertz. That's like 600 hertz of bandwidth. Let's say we were listening to high fidelity music.
Yeah.
Right? It's still audio, but it takes between, let's say, 100 hertz and 20,000 hertz. So which one would physically take up more space? In order to go ahead.
Yeah, the high fidelity, because you have more of a more bandwidth than that.
Right. Bandwidth is bandwidth. Which one of those two, me talking or high fidelity music, which one contains more information?
High fidelity.
High fidelity does.
High fidelity, that's right. So does anybody use Wi-Fi Anyone here have Wi-Fi?
Everyone?
Yes.
Yes.
Okay.
Mhm.
How would you feel if your Wi-Fi had a bandwidth of 10 kilohertz? Does everyone know what the bandwidth of your Wi-Fi is?
2.5.
2.4 gigahertz
No,
up
that's the
to
frequency.
5.
That's the frequency it's at. But do you
Oh.
know
It's usually
what?
not in kilohertz.
No, it's the
Gigahertz?
bandwidth. If you ask your computer what is the bandwidth of my signal, it's about 100 megahertz of bandwidth.
I'm
That
just
is
happy it works.
well, but the reason it works is because there's that much space available for you to use it. So let's take a look at this frequency chart again. This is really significant. That signal that you are using to, on Zoom right now is 100 megahertz wide. What is the total amount of bandwidth between 3 and 30 megahertz?
27.
27. In other words, how about between 30 and 300?
270.
270. There is barely enough space on this entire swath of bandwidth of the band for you to put in one Wi-Fi signal at the kind of bandwidth that you want to use. So I'll ask, why do you think people use these frequencies way up here for satellite?
There's much more space that you can work with on that.
That's right. There's tons of space, and that 100 megahertz bandwidth is really fairly insignificant compared to the rest of it. The other advantage is that once you're at a particular frequency, let's say 3 gigahertz, you go from 3 to 3.1. Those frequencies are actually proportionally very close, and your antenna will probably work at both ends of it. Whereas if you were down in this range, let's say 30 to 300, right? So 30 to 300. We're going to go through and do our math again. I'm sorry, everybody. There's a lot of math in this stuff. New whiteboard. Yes, I know. Hello. Yes. Yes. I don't know why it keeps asking me all these things. Okay. So let's look at our frequency again. Everybody remember this that we did like 10 minutes ago? Okay. So we have, in this particular case, let's say we have 100 megahertz of bandwidth. And the bottom edge, we're going to draw our graph here. It goes from 30 to 300. And just for convenience, we're going to pick 100 to 200 megahertz. And we're going to put our Wi-Fi signal right here. This is physical space. It's virtual physical space, but you can think of it as actually filling up space, right? It actually fills up the frequency spectrum that we have available to us. Let's take a look at the antenna that we use at 100 megahertz. 300 divided by F. How many meters long is that?
3.
3 meters. How about at the other end? 300 divided by 200. The antenna that would work at one end of it does not work at the other end because these wavelengths are so radically different that you could not really build a good antenna that would work in that entire range. I mean, it would have to work and be resonant at 3 megahertz and another one at 1.5. Good luck building that. And it would also have to work everywhere in between. So good luck building that. That's why we don't, that's another reason we don't do that. Okay. Let's see. Next, we're going to go and we're going to break away from waves and we're going to move into basic electrical stuff. So if you're curious about the book, I believe this is where the book actually begins on electrical stuff. And so this is in the book. Let me open up the Open the book. Electrical principles. So we're on page 4. So this is a basic circuit. Circuit comes from the word circle. It basically means a closed loop. And there are certain things that we use to measure things that go around a circle in this particular case. So the first thing I'm going to do is stop my share and start up another. Y'all see why I really want this whiteboard thing to work properly, right? I use whiteboards a lot.
Yeah, you need it. It's, you gotta have it.
Yeah.
I get
So,
it.
okay, here we go with a circuit. Okay, this is a battery. And this is a resistor, which we're going to get to. And the battery has something called a voltage, also known as an electromotive force, can be represented by the letter E. The resistor has resistance, and it is measured in something called ohms, named after Georg Simon Ohm, one of the early scientists who worked on electricity. And now, if you think about let's think about I have to change the color. We're going to make it blue. Nice blue pool. All right, so there's a nice blue pool of water. All right, that blue pool of water is unfortunately on top of a hill. So
On top of the what?
on top of a hill.
Oh, okay.
So if you were to build a swimming pool, what would happen to that water? Hopefully
It'd
nothing.
roll down
right?
the hill.
Well, hopefully nothing, because you built walls around it, right? But let's say that you have the bottom of the hill here, and there's a big open gap. Okay, so what is preventing the water from flowing over the cliff and down to the bottom?
The walls.
The wall. The wall. Okay, so the water has energy associated with it. It has potential energy. It has the ability to try to push itself and knock the wall down. What is the wall doing?
It's resisting the water.
Resisting the water. Okay. Now, what would happen if we instead took this water and we could build the wall higher and higher and higher? It didn't flow over it, but let's say that there developed a small crack in the wall. What would happen?
Well, you would get some flow.
The
water would come down.
You'd get flow, and the water would eventually break down the wall. So this is our voltage. This is our resistance. The wall is the resistance, and the amount of water flowing is known as current. Just like current in a stream. So we have our volts, our voltage, and our electromotive force. Instead of water, it's actually electrons, which we're going to get to. Resistance, we measure that in a unit called ohms. And our current, which is the amount of stuff flowing, in this case, water, that's measured in amperes, named after Ampere. So what we're going to do instead is, now we have to look at something called an atom. And I'm going to draw a simplistic view of an atom.
I have one question real quick before you go on.
Uh-huh.
And the voltage in the former drawing you had with
Mhm.
the water, the voltage represents what? The amount of water in the
The amount of push. Voltage is push. Okay, this is the nucleus of our atom. What is in a nucleus of an atom? What things are, and don't say quarks, please.
Electrons.
Don't say neutrinos. No,
Yeah,
actually no.
Protons and neutrons.
Yep, protons. Protons are pluses, and
neutrons are
neutrons
negatives.
have 0 charges. Neutrons have no charge.
Electrons.
Electrons are not in the nucleus. So this is our
Not
atom.
paying attention.
So our atom is going to have a whole bunch of positive charges in the nucleus. To balance this out, we are going to have something zipping around the outside of the atom.
Balance.
in different shells, we're going to have a bunch of negatively charged electrons.
Okay, sorry.
We're going to have our electrons flying around the outside. They actually fill different valence shells. They actually fill, depending on their spin, they actually make up little clouds, but we're just going to basically assume that they orbit in some way. So an electron, for our simplistic viewpoint of an atom, balances out all the electrons. So that if you have 14 electrons, you're going to have 14 protons. If you have eight protons in the middle, you're going to have 8 electrons zipping around the outside. So, depending on the number of electrons that are flying around, notice that it always matches. The number of electrons matches the number of protons. That's how a neutral atom works. A neutral atom has 0 charge, 0 net charge. These electrons fill up shells. The shells, the inner shell has 2 electrons. The next shell has 8. The next has 8. The next has 18. And let me think, 2, 8, 8, 18, that's 36, 18, 32, etc. That is the capacity of each shell of electrons that can form around the atom. A complete shell is a very happy shell. It's completely full. So if we fill up an atom with 2 electrons and there are no additional electrons, we call that helium. Helium doesn't react with very much. If we have a 2 and an 8, that's neon. 2, 8, 18, that's argon. 2, 8, 8, 18, that's krypton. And that's xenon, and that's radon. And yes, radon is actually inert. These are noble gases. They don't react with anything to speak of because their electron shells are very happy. Now, we also have the ability to take an interesting number of electrons and mess with it just a little bit. So we have our nucleus right here, and we have our electrons flying around. And let's say we have a 2 and an 8, but now we also have 11 total. So we have 1 flying around out here. That one should be in a shell that has 8 and it's only 1, which means it's kind of flying off on its own. This actually has the ability, if it comes in contact with another atom nearby, to grab electrons, give electrons away. How it reacts determines what it's going to do, how it's going to react chemically. So it might be that instead of this one, we're going to draw an atom that has a whole bunch of electrons to give. So here's the nucleus again. And here's the electrons. And these electrons right here are very, very loosely held because of a whole bunch of stuff that's happening toward the inside. So these are far away from the nucleus. They're like, yeah, okay, I don't really need to be here. So let's say that another electron comes in from somewhere. Well, this one might just say, okay, I'm just going to go. Another electron comes in. This one says, yeah, I don't need to be here. The movement of electrons has a name, and that is current. The amount of force that it takes, that you are pushing electrons into something with, is known as electromotive force or voltage, or the letter E for electromotive force. So voltage is electromotive force. It's the amount of push that electrons are given to do their job, to try to push things around. The resistance, that's measured in ohms, is how hard this thing is trying to fight back. Say, no, I don't need an electron today. I'm perfectly happy. And remember, since current is the movement of electrons. In the case that we have an atom that doesn't need anymore, it's perfectly happy, it will fight very, very hard. That is a very high resistance. It is very resistant to the movement of electrons. Okay, so now we're going to take that and go from that microscopic scale to a macroscopic scale. Here's our E, electromotive force. We call this a battery. A battery has a plus and a minus. What is the charge on, everybody? What's the charge on an electron? Plus or minus?
I want to say it's minus.
It is minus. So where do the electrons come out of? What do you think? Which terminal?
The minus terminal.
They come out of the minus terminal. Okay, but if anyone here has ever taken a physics class, where does the current come from by definition?
The positive?
The positive, that's right. So our current comes out of the positive terminal. And why is that?
I never took a physics class though.
Is positive attracts negative?
Yeah, no, that's not it.
No.
This was called, oh man, come on. Why you gotta
I'm gonna do Ben Franklin.
This was called a mistake. That was an error that was made at the very, very beginning of the discovery of electricity and current, because they didn't know what an electron was. So they just said, well, this seems to be, we have a positive terminal and a negative terminal. They didn't know electrons were negative. We're just going to assume that the current comes out of the positive by convention. So that was over 150 years ago, closer to 200 years ago, and we are still living with that mistake. And we no longer consider it a mistake. We just accept the fact that they made the mistake, and then we never talk about it again. That's the truth. All through engineering, you know that the electrons come out of the minus, and you know that current is, by definition, flow of electrons, but they got it backwards. And then you just sort of accept that fact and move on. All right, so now we're going to draw our battery. A battery is a way to store electromotive energy. A battery is a chemical storage device for storing the ability to generate an electromotive force. Electromotive force is the ability of something to move electrons. So I have this thing called a resistor. This is measured in ohms. My battery is measured in volts, and I generate a current, which is measured in amps. Ohm's law, notice that ohm, that omega, Ohm's law is E equals I times R. That is Ohm's law. 90% of everything that you ever deal with in the real world, if you're trying to debug electrical stuff, comes down to applications of Ohm's law. E equals I times R. Solves 90% of problems. Okay, so this is really important to remember. We can do EIR. We can do the circle again. So we're going to assign some values to this just for the heck of it. We're going to say that we have a 10-volt battery and we have a 5-ohm resistor. Okay, so what is the unknown quantity? Somebody take me through it. Current. We don't know our current.
I equals E over R.
Right? And so we're left with this. There's our divisor bar. I equals E divided by R. R is 10 volts per 5 amps. Or sorry, 10 volts per 5 ohms is 2 amps. That is our current flow. Now, this is actually, just so you get some idea, 1 amp or 1 ampere, named after ampere. Notice there's actually a French accent grave on that. It's actually named after Ampere, who was a scientist. This is actually about 10 to the 19th electrons per second. That is 1 ampere. So what does 10 to the 19th mean? How many?
19. That's
It's an SI unit. Do you want the actual number?
Yep.
So 10 to 9. It's a lot of
There we
zeros,
go.
Scott.
There's the number. That many electrons flowing past 1 point every second, roughly, is. Oh, somebody's got something playing in the background. Okay. Anyway, it's a lot of electrons, and that's okay because electrons are really, really tiny, right? They're one of the smallest things that we could even measure in size. So that's a lot of electrons. All right. So we just figured out what our current is. All right. Now, what we're going to do with that is we're going to say, here's our voltage again. And now we're going to say that this is 100 volts. We're going to say that this is 1 ohm. We're going to do our current calculation again. What's Ohm's law, everyone? Come on, everybody.
E equals I times R.
E equals I times R. We're going to write it in our we're going to write it in our circle format so we don't have to worry about remembering which is which and screwing it up. We don't know our current. Cross it out. I equals E over R is equal to 100 volts divided by 1 ohm, which is 100 amps. So our current flow is 100 amps. Okay, so now what we're going to do with this is we're going to add the second part of Ohm's law. Yes, it's actually 2 parts. Here we go. Here we go, the second part of Ohm's law.
Pi.
Here we go. Oh, we hit that stupid thing again. P is equal to I times E.
Power wattage equals I.
That's power in watts. Named after James Watt.
100 watts.
P equals I times E.
Oh, it's wrong.
Okay. So now we can figure all kinds of cool stuff out. So let's say we don't know our power. We have, notice I, E. The battery is supplying 100 amps at 100 volts. This actually becomes multiplication down there. P is equal to I times E is equal to 100 times 100, which is 10,000 watts. That better be a pretty big battery, right?
Yeah.
So 10,000 watt battery delivering 10,000 watts. Okay. So now what we're going to say is we now have to have how much power generated by this, by the battery?
10,000 watts.
10,000 watts. Okay. So, okay. Does everyone know what a watt actually is?
No.
Okay.
Yes.
A watt is a unit of energy being dissipated over a period of time. So a watt is a joule per second. A joule is a unit of energy. It's an MKS unit of energy. That is 1 watt, a joule of energy per second. What's cool about this is that, for instance, if I am standing on a cliff, and I'm not moving, I have kinetic energy, but I'm not moving. My kinetic energy is 0. I have potential energy. What is potential energy in this case?
Oh.
Energy of motion.
Energy of not motion yet.
Not motion, not
It's
motion.
the potential for motion.
It's the potential for motion. That's right. So I have potential energy because I have climbed all the way up that cliff. Now, how could I reclaim that energy and turn it into something else? If I really wanted to, I could jump off the cliff, assuming that there was a big airbag there to catch me and I didn't die. I would have I'd basically be converting all my potential energy to kinetic energy. So my potential energy would be 0 down here, and my kinetic energy would be lots of exclamation points. I'd be moving really fast. So a battery is a way to store potential energy, except it's not 0 in this case. A battery stores energy. And what does it move when it converts it into kinetic energy?
Moves the electrons.
Moves electrons. Electrons, again, are really light, but they're not, they don't have infinitely small mass or anything like that. So it takes a little bit of energy to move an electron. A battery is a chemical storage device. If anybody has an electric car or a hybrid, you see this every day. So does anyone have a hybrid?
Yes.
Okay, so what happens when you hit the brakes?
It generates
Regenerates.
electricity.
Stops movement.
Yeah, what does it do?
Convert it to
It
the
converts
battery.
energy of
Potential energy.
it converts energy of your car moving. That's kinetic. And here's your
potential.
battery. It converts it to potential energy, which is recharging the battery. And instead of, what would it normally do in a car that wasn't a hybrid, that didn't convert it?
Converts it to heat and friction.
Converts it to heat. Okay, so energy can neither be created nor destroyed. It just changes form. So if I have a battery like this with a plus and a minus, and here's a resistor, and we said before that we are generating 10,000 watts of energy that's going somewhere, where does it go? This is 10,000 watts of power. It generates current, and then where does it go?
Well, it goes
The
back to the
converts it into heat.
Goes to the resistor and turns
Right.
into,
it dissipates wattage.
dissipates all that wattage, all that power as heat. And how much heat has to be made to balance this? How many watts?
The same amount.
Same
10,000.
amount. 10,000 watts.
Yeah.
Does anybody know of an example of a device like this in your home?
An oven.
Mm-hmm. Other one?
Microwave.
No, well, no, microwave actually uses RF.
10,000
A
watts.
furnace.
A furnace or
A radio antenna.
I don't run that much power.
A dryer.
A heat.
Dryer?
A hot water heater.
Hot water heater or an electric dryer. They generate a lot of heat. They are designed to convert input power into output power, and they are intentionally generating heat. Energy that is not used for something, but it's still delivered, comes out as what?
Wattage. Hot.
It comes out as heat.
Yeah, or thermal heat. I'm sorry.
Yep, the same way that when you stop a car, it has to go somewhere. That energy has to go somewhere. Okay. So now we know that a battery generates, a battery is a storage device, chemical storage of electromotive force. Its job is to move electrons. Electrons are tiny little things that are inside of atoms that have a negative charge. They move through resistors and such. Resistors resist the flow of current. Current is the movement of electrons. So what we're going to do now is I'm going to draw a resistor. and I'm going to draw a piece of wire. This is actually a block of carbon, and this is copper. Which of these has a higher resistance and which has a lower resistance?
Copper has lower resistance and the carbon has higher resistance.
Okay, why does copper have low resistance?
It has more electrons.
Well, it has
More free electrons.
it has more electrons that are free to be pushed
Right.
around.
Yeah, good point. Yeah, fair point.
Carbon does not have many. Okay, so this is actually called a conductor because it conducts current. This is a type of insulator. Something that does not conduct current well is known as an insulator. Carbon is not so-so. What can we use to make this a better insulator if we didn't want current to flow? What could we fill that with? I heard plastic, some sort of some plastic. Glass. Yeah, air is really good. Other
Ceramic.
ones?
Rubber.
Ceramic. Yeah, that's really good. Some
Wood.
rubbers. Wood is a good one. Yeah, other ones? How about water?
Mineralized water.
Water would be a conductor.
Water's a conductor.
Water is not a very good conductor, actually.
The minerals are, but the
That's right. Demineralized or deionized water is actually a pretty good insulator. What is a really good conductor with water?
What's it with water?
salt.
Salt water makes it a very good conductor.
I had to think about that one for a second.
It's the salt. It's the salt that adds ions. An ion is an atom that has either one extra electron or has an electron taken away. So it has a net charge of +1 or -1 or +2 or -2. And because of that, it can actually do a very good job conducting electricity. So those are known as ions. Ions
So it's
are
called electrolytes.
Yes, ions are going to be very, very important in just a little while. So remember that word, ions. An ion is an atom that has an extra electron or has one that's been removed. It's going to be really important. Okay, so we've got conductors and we've got insulators. How about conductors? Some really good conductors.
Gold.
Gold, good one.
Silver.
Silver, okay.
Aluminum.
Aluminum is actually an excellent insulator, or sorry, excellent conductor.
Copper.
Yep, copper is an excellent one. All right.
Mercury.
Most metals are actually really good at conducting electricity. Okay, very good. So which is better, gold or silver?
I think silver is.
Gold.
I think silver is actually. Gold is used frequently because it doesn't tarnish like ever.
Gold plate doesn't oxidize. Yeah.
Yeah. Okay. So let us move from there. And now we're going to take a look at our current and our voltage from our battery. Here's our battery. Plus, minus. There's our battery. It has a plus terminal and a minus terminal. How many volts, if this is a 12-volt battery, which is a car battery, by the way, a 12-volt battery, here's our 12-volt mark. How many volts does a 12-volt battery put out? Not a trick question. Not a trick question. I know, 13.8. We'll say nominally 12 volts. Does it ever change if the battery doesn't significantly discharge?
No.
No, it's 12 volts all the time. If we were to draw a circuit that had this battery in it, here's a resistor. Which direction would the current, not the electrons, but which direction would the current flow? It would flow this way, and it would always go that way. Everybody agree with that?
Yeah, I keep thinking about what you said before, and it's in my head going from negative. It screws me up.
Again, you're going to forget it from now on and just remember that it's there. Okay, so now we have our current which is always flowing in one direction. This is known as direct current. It's always flowing in one direction. But now what I'm going to do is I'm going to take this battery, and let's say that I'm really good at my job. And here's our circuit. And I am going to put a battery in like this. And I'm going to get current that flows that way. And then at some time, I'm going to take the battery and I'm going to flip it around. Which way is the current now going to flow?
Counterclockwise.
Counterclockwise. So I switched the battery this way and the current went the other way. And then I'm going to switch it back, and then I'm going to switch it back again.
Oh, you're talking about alternating current.
And this is, this is alternating current, because the direction of flow of the current changes based on how I'm setting up the battery.
But are we saying a battery is DC then? Is that just well, I'm thinking DC is a battery, not as an
right. But I'm using the battery to I'm manually flipping the battery around instantly. And so what I'm doing is I'm using a constant 12-volt source, but I'm changing the polarity so that sometimes it's plus and sometimes it's minus, sometimes it's plus and sometimes it's minus. I am generating this thing called alternating current, or AC.
Okay.
Now, this wave, because this is actually a wave, this has some characteristics. What does it have? Because it's a wave.
It has a peak. It has it rises, and then it's horizontal, and then it drops.
Well, that's a square wave, but what do you notice about it? It has a frequency.
Oh, okay, frequency.
Right. What else does it have?
It also has a polarity.
It has an amplitude.
Amplitude, yeah, okay.
Right. It doesn't really have a polarity. It's just, it's either one or the other. It has a frequency and an amplitude. If it has a frequency, it also has a period, which is how long it takes to make that change. So that means that the thing that I am putting into it by flipping it up and down changes at a certain frequency and a certain amplitude up and down. This is actually really, really profound, because this waveform, also known as a square wave, where do we find things like that?
Computers.
Computers. That is how digital logic works.
5-volt TTL.
5 volts. Yeah. And you could have a +5 and a -5. Sometimes this would actually go down to 0 instead of -5. Depends how you design it. There's also, however, if you're going to have a wave, what is a much easier wave to make than a square wave?
Sine wave.
A sine wave. Because a sine wave is made by rotary motion. Right? A sine wave is a picture of something going around in a circle. Remember how we started with that? Can you think of anything in, let's say, a dam that goes around and around in circles?
An eddy?
The generators.
Generators. Yes, generators. Generators go around and around in circles, and when they turn, guess what they make?
They make a cycle.
They make sine waves, yeah, which is really, really nice, because these have a frequency and these have an amplitude. And it turns out, because of something that we haven't covered yet, they can also have you can also convert their voltage, the amplitude. This is the voltage. That is a version of the amplitude. I don't know why it does that. There we go. The voltage and the amplitude are basically the same thing in this case. So it has an amplitude and a frequency, and that's a voltage. And that is made by a spinning generator, which is attached to a turbine, which is either run by steam or water power or something. And this is how we generate electricity. All right, so now we're going to move to something else, which is how resistors act when they're combined. All right, this is a resistor. And what is this?
Another resistor.
Another
Series
resistor. Okay. So
Yeah.
let's say that we have our battery. And by the way, I could actually redraw that battery. I could draw it like that instead. What do you think that would represent?
Generator?
That would be a generator or a sine wave generator.
Oh, okay, alternating.
Alternating current.
All
Okay.
right, gotcha. I'm
So
following.
but for the sake of this, we're just going to draw a battery. If it lets me, there we go. Okay, and we're going to connect the resistors in series. In series, because if you think of yourself as being an electron and riding through one of them, you go through one and then you go through the other one. It's like watching a series on TV. You go through one and then you have to go through the other one. Otherwise, you won't catch the whole thing. This resistor, R1, and this resistor, R2, the sum total of them is that the total resistance of a
CRT.
series combination is R1 plus R2. They add together. So if this is 3 ohms and this is 6 ohms, my total would be 9 ohms. Now, let's say that I have 9 volts right here, right? And I have a total resistance of 9 ohms. By Ohm's law, E is equal to I times R, E, I, R, like that. I don't know my current. I is equal to E divided by R,
One.
which is equal to 9 divided by 9, which is 1. So I have 1 amp flowing in this circuit. How much current is R1 going to experience going through it? How many amps?
1.
1 amp. How about R2?
1.
So this is in a series circuit, all devices experience the same amount of current flow. Okay, and this is important because now I can actually say, I can use Ohm's law to look at the voltage that I would measure across each of these resistors. So I would hook up this thing called a voltmeter, which goes in parallel to this. This is a voltmeter. And I could say for this particular resistor, Ohm's law says, everyone agree E is equal to I times R? Again, I can draw it like this, EIR, like that. What thing do I not know? I don't know the voltage that I would see across that resistor. So then I get I times R. E is equal to, I is 1 amp, and the R is 3 ohms. So I would get 3 volts for the first resistor. I would measure this as 3 volts. So even though I have a 9-volt battery, I would see a voltage drop. The voltage being consumed here would be 3 volts in the first resistor. How about in the second resistor?
Should also be 3 volts.
No, it will not. Because the formula says
Oh, the amp stayed the same. So voltage would drop by half.
6 volts.
E equals I times R. We're just going to go through Ohm's law again.
So
All
it'd be 9 divided by.
Nope. What's our current?
Current is
1 amp.
1 amp.
And what's our resistor?
6.
6 is.
Oh, you're just measuring that, that resistor, not both.
Yep.
Okay.
So our voltage on the second resistor would be 6 volts. Now, importantly, we can go around starting at any point, and this is called Kirchhoff's voltage law. We're going to start at this point down here at the lower left, and we're going to go, we can pick either direction. We're going to go up. How many volts do we get on from the battery? How many volts?
Should be 9.
9 volts. How many volts do we lose in the first resistor?
3.
How many volts do we lose in the second resistor?
6 volts.
6.
All right. And then we end up back where we are. And what's plus 9 minus 3 minus 6?
0.
0. That is Kirchhoff's voltage law that says that the sum of the voltages around any loop in a circuit must be 0.
Oh, what is that called?
That's KVL, Kirchhoff's voltage law.
Kirchhoff's. Is he Russian?
I think so. Okay, so that's Kirchhoff's voltage law. Now we will also define an arbitrary point in a lot of circuits, which is our 0-volt reference. In this particular case, we usually tie that to the minus terminal. We represent this like that. We call this our ground. That is our 0-volt reference. That is known as our ground. Grounding is very important. We're going to get to that too. Right? Otherwise, your circuit is floating. If it ever makes contact with something that you don't expect it to, you can have all kinds of weird things happen. So we usually tie a single point in our circuit to ground. And that's our 0-volt reference for the whole circuit. Okay. So now we're going to redraw this in a different way. Here's our battery. And now we have a resistor. Now we have in parallel another resistor. All right. Battery generates current. As it flows through the resistor, we call R1 and R2. So we're going to say that R1 is 1 ohm and R2 is 1,000,000 ohms. And we're going to call this 10 volts. All right. So now we're going to apply our Kirchhoff's voltage law, which we just did, which says that the amount of voltage around any loop must be what?
0.
0. Okay. So we go start at the 0 point. We're going to ground that. Plus 10 for the battery minus VR1 equals what? 0. Therefore, our voltage in that first resistor has to be how many volts?
10.
10 volts. So VR1 is equal to 10 volts. It experiences the full voltage from that battery. Now we're going to draw the other loop. We're going to go and we're going to ignore the first one, and we're just going to go around the second loop. Okay. So we have the same thing, except that we replace it with VR2. And what's VR2 then? It's also 10 volts. So in other words, both of these resistors experience full voltage of the battery. And that is important because depending on their resistances, they may or may not experience the same current. Everybody agree with that?
Yeah.
Because we can actually now calculate the current in each of these resistors, right? And what will we use to calculate that?
Ohm's law.
Ohm's law. What's Ohm's law?
The voltage is constant through a parallel circuit.
Yep. So these are parallel, as you just said, because they look like this as viewed from outside. Those are parallel lines. These resistors are in parallel because they are in parallel circuits. And now we're going to calculate our current through this resistor, IR1. What's Ohm's law, everybody?
I equals E over R.
No, give me the general form. E equals
I mean, equals I times R.
E equals I times R, and we're going to do this. We're always going to start there. That way you don't have to remember alternate forms. E equals I times R. And I can't apparently draw a letter R today. E equals I times R. And what don't we know?
Current.
Current. So we cross that out. I is equal to E divided by R is equal to, we get 10 volts divided by a million,
one.
or sorry, divided by 1 ohm
1.
is 10 amps. So through here, we get 10 amps. How about through this other one? We can do Ohm's law again.
So it'd be
Notice,
10 divided by a million.
yeah, it'd be 10 divided by a million. So E
Excuse me.
I R. Okay. Again, we don't know our current. I is equal to E divided by R is equal to 10 volts divided by a million is equal to 0.00001 amps. So if those are light bulbs, which one do you think is going to be brighter?
I think it's the first one.
It's the first one, yeah. But this is actually really important because if, for instance, I were to take this resistor completely out, and let's say that those are light bulbs, and I take this resistor completely out of the circuit, what's going to happen to that first light bulb? Nothing.
Increase.
Nothing.
no.
Absolutely nothing. It's not going to notice any difference. This is how your
Because
house
the
is
voltage is
wired.
parallel. Because the voltage is constant being in a parallel
Right.
circuit.
This is how your house is wired. If I were to draw this again in series,
Christmas lights.
this is Christmas tree lighting. If something happens and that bulb blows out, you now no longer have a circuit, and
You have it
both
open.
of them go dark.
Yeah.
Both of them go dark. That's Christmas tree lighting. Okay, so we have some names for things. So this right here, what kind of circuit is this?
Battery. With
This is called an open circuit. What is the resistance of an open circuit? How many ohms?
0.
It is not 0. Think about that.
Infinity.
Infinity
Infinite.
ohms.
Oh,
Yep.
yeah. Okay.
Okay. So the corollary to this, or corollary? Not really a corollary. The opposite of this would be, I then take this circuit and I do this with it. This is called a short circuit,
Oh, right. Okay.
which is how many ohms?
0.
Zero ohms. That is 0 ohms. Okay, so that's an open and a short. Okay, so now we're going to move on to the next thing. But before I do that, does anybody have any questions so far?
No. It's been a while since I've done
No
this. Like,
question.
Yep,
it's
go
been
ahead.
like 30 years.
Hold
since
on,
I've done-
Vladimir. Who had a
No, I
question?
said I have no questions. Thank you.
Okay, any questions before we move on?
Yeah, Scott,
Yes,
I'm gonna have to drop off here.
we'll
Uh,
miss
I-
you.
I'm sure you will. You only have 70 whatever other people here. This is recorded, right?
Yep.
And you're gonna send it out tonight, yeah?
Yep.
Okay, awesome. Okay, thank you. I will
But
see you tomorrow.
Jennifer, did you catch my Z axis?
Yes,
I did that just for you, you know.
just because I'm Canadian and just, better.
Well,
Okay,
yeah,
thank
and I actually I work with robotics sometimes, and it is the Z axis in Canada. I know that. I know that. We call it that.
Good for you. Then you also know about all the important things like Tim Hortons.
Mm.
Okay, I'm
Oh,
gonna
Tim
take
Hortons. Woo!
Tim's
Love
is
it.
the best.
Have in New Jersey, Tim Hortons.
Well, I love I love Timbits,
Oh yes,
Yeah.
you do.
and I also love the roll up the rim thing every February.
Oh my God. Yeah, Tim Hortons is in New Jersey.
Oh, okay. That's in New Jersey too. Yeah.
Yep,
Okay.
I just visited one. I'm in Maryland, but my mom and dad live there, and I just went to Tim Hortons. It was great.
Mm-hmm.
I was up in
Okay.
Nova Scotia and went to a Tim Hortons. It was
Love
fantastic.
Oh,
Tim's.
yeah. So I'm gonna drop off and then
Okay.
and I'll see you tomorrow. Okay,
Okay.
thank you.
All right. All right. So I'm going to draw the next thing. Okay. So we have our battery. Okay. So there's a couple different kinds of batteries that we can have. One is called a primary cell. A primary cell is a cell that is charged up once, and once okay, a battery stores energy in a chemical form. It's a chemical reaction. A primary cell is a non-reversible chemical reaction. So this is a non-reversible.
What does that
So
mean? Right? What does
that
mean?
means once it's done, it's done. If you've ever seen if you've ever seen an alkaline battery,
Oh, once it's done, once it's discharged, that's
once
it.
it's dead, it's dead.
Primary cell.
Right? You can't run it backwards and recharge it. So that's like an alkaline battery. This is like a lithium metal battery. If you've ever seen a lithium backup battery or something that lasts for 10 years, once it's dead, it's dead. This is also like the heavy duty battery, which is the old carbon battery, carbon zinc. These are primary cells. Then you also have rechargeable cell. A rechargeable cell stores energy the same way, except that it is a reversible thing. So here's your chemical reaction storage. And it exhausts itself by using its stored energy to generate power, converting potential energy in chemical form to electromotive force and moving electrons and doing work. And then once it is dead, what do we do with it?
Charge it.
We charge it. And the way we charge it is we hook it up to another battery, which has a plus and a minus. And this runs current back through it.
And what kind of battery is this called? The rechargeable? I mean, what
That's just a rechargeable.
Okay, just was what I was
It's a reversible chemical reaction.
Okay.
Examples of this: lithium ion, nickel metal hydride, nickel cadmium, lead acid. So those are all like LiFePO4. I have one of those. That's lithium iron phosphate. Those are all rechargeable batteries. Okay. Moving right along. What are some of the hazards of having a battery that is a car battery?
You have outgassing and could be explosive.
Yeah. And that is because what you have in there is water
and chemical
and H2SO4 and lead. H2SO4, anyone know what that is?
Sulfuric acid?
Sulfuric acid, exactly. And if you overcharge or discharge a battery too much, the water will dissociate, and water is made of H2O. You will end up with hydrogen gas being generated. And if let's say you go to charge up your battery and it's been discharged too much and there's a cloud of hydrogen gas floating around on the inside and outside of your battery, you hook up your charger to it, it generates a spark. Does anyone know what the Hindenburg did?
Hindenburg. You just took the words out of my mouth.
So what you end up with is, if you are lucky, you end up with an external hydrogen explosion, which is bad, but not that bad. Now, what's really bad is if inside the battery you end up with a little hydrogen explosion, then what do you get?
The battery explodes.
The battery explodes and showers you with what?
Sulfuric acid.
Sulfuric acid, that's right.
And then you burn, and then you go to the hospital.
Right, then you go to the hospital. So that is why we avoid recharging. That's why we avoid having to discharge and recharge lead acid batteries whenever we can. That's also why whenever you hook up another car or another battery to a lead acid battery, you try to hook up the negative to the ground terminal on the car instead of to the battery. So if it does generate a spark, it's hopefully far enough away from the battery that it doesn't ignite any cloud of hydrogen that might have existed. So
God.
I know somebody it
Yeah.
happened to.
It
So,
happened to me.
did it?
Yeah, except I was troubleshooting my engine making a funny noise. I took a spark plug wire off. I guess it was close enough to the battery and turned it on, and the thing blew right up.
Mm-hmm.
So yeah, I know about that.
Yeah. All right. So now that we've looked at batteries, we're going to add a couple of components here. Okay, so we have a resistor. What does a resistor do? It resists the flow of
Current.
electrons. We also have these devices. The first device is called an inductor,
Inductor and capacitor.
and this one is called a capacitor. Okay, and typically I will do the capacitor first. So we're going to do the capacitor first. A capacitor is exactly as it's drawn. That's physically what it looks like. It is two metal plates separated by a distance. So now what we're going to do is hook up a battery to it. The battery has a plus terminal and a minus terminal. So we hook up this uncharged capacitor to this battery. What will suddenly happen when we have a positive charge hooked up to the left-hand side is that you get a rush of positive charges to that terminal. You also get a rush of negative charges out of the way back to the battery. Similarly, you get a whole rush of negative charges out of this side that charge up the capacitor, and you get positive charges back to the battery. What's another name for the motion of electrons?
Motion electrons?
Yeah.
Energy?
No, what's a movement of
EMF?
electrons? It has a name. Nope.
Current.
Current, yes.
Oh, current.
So
I'm sorry,
basically,
current.
when you hook it up, you get a big current, which charges up the capacitor, but then the capacitor is full. Once the capacitor is full, how much current can flow?
All of it.
Nothing. It's full. You can't stick any more in there. Right? So your current is initially very large, and then it drops off to zero. This is a very boring circuit. Right? So now let's say that we take our battery and we disconnect it. What are we left with?
Stored energy in the capacitor.
Stored energy in the capacitor. Yeah. Okay. How long can it stay there?
Indefinitely.
It could, yeah. So what that means is if you find a capacitor that is of unknown origin, it may actually still be charged. Internally, this area in the middle is known as a dielectric. All right, so that's our dielectric. It is an area that does not allow current to flow. This could be polyethylene, it could be ceramic, it could be like a tantalum, it could be air.
Oh,
so once it charges up and then you discharge it, you are left with a net, a net extra charge on both sides.
Is the dielectric not the same as an insulator, I guess?
It is typically an insulator. Yeah, we just call it a dielectric.
Okay.
So the spacing, because if you think about it now, what do you know about pluses and minuses as far as those charges? What do they want to do?
They want to equalize themselves.
So what will they attempt to do in this case?
To jump.
Okay, what if they can't jump?
Then they
will attempt to smash those two things together.
Oh.
Their ability, their desire to do so generates something called an electric field. They store their energy in an electric field.
In electric field.
Right? So a capacitor stores its energy essentially by virtue of the fact that those electrons and lack of electrons or positive charges are being kept apart. Even though they're trying really hard, the capacitor is storing energy in an electric field. And that's actually measured in volts per meter. You could actually take a voltage across it.
When you say the electric field, I mean, you're talking about like the field that's around the capacitor,
No,
or
the
is
field that's on the inside,
it okay? In the inside,
between
okay.
those two plates. Those are
Right.
physical devices. Those are physical things that are being kept apart.
Scott, I have a
It's
question.
almost like it's almost like looks like a battery in a sense, in a weird way.
Yes, it does. Jack or Jim.
Jim. In the point in the engine, when the older ones had points and condenser.
Ah, we're not there yet. We're not there yet. We're getting there in like 5 seconds.
Oh, okay.
Okay. So now I'm going to take this battery and I'm going to do this with it. This is our plus and this is our minus. What's going to happen to the charges that are in the battery?
They're going to it's gonna migrate across the capacitor, I guess.
And the
right?
capacitor is going to flow back and forth because the capacitor's charged opposite to the battery now, right?
Right,
I
right.
reversed the battery. Well, what's that called? What is the movement of electrons called?
Current flow.
That's current. Okay. So now what's going to happen is that all of these are going to reverse. And eventually what's going to happen is that the capacitor is now completely charged up the other way, right? Capacitor will be completely charged up the other way. This will now be the positive side, and this will be the negative side. And as that's happening, as that's about done, I switch my battery again.
Oh, and it does the opposite.
If I switch my battery again, what happens?
When you say you switch, you mean you switch the polarity of the battery?
I switch the battery polarity.
Okay.
What happens now?
And then it does the exact opposite.
It just
it's
does it again.
the other way.
Yep. Okay.
Goes the opposite.
So what is this called if I switch my polarity back and forth?
Alternating.
That is AC. And since it looks like the current is always flowing, does it not? It doesn't stop. What is the name for a circuit that allows current to always flow without any resistance?
Short.
Short circuit. So if I have AC, a capacitor looks like a
Short circuit.
short circuit. If I have DC, the capacitor charges up and then
Stops
flowing current. There's no more current flow. That is an open circuit. So a capacitor blocks DC and allows AC to pass. This is actually really important because now we're going to do the inductor. Okay, what's an inductor? Take a look at it. That's physically what it is. It's a piece of wire that I did what with?
You coiled it and made it into a magnet.
I coiled it up. Okay. Everybody hold up your right hand again. Stick out your thumb and now wave. And now instead of waving, keep going with your fingers and curl them over.
That I can't do.
Yeah. Just curl them forward.
Arthritis. Sorry.
That is the direction of your fingers is the magnetic field that is generated by that current flow. So around any wire that is carrying current, you get a magnetic field. If I have a straight piece of wire, the magnetic field, let's say the current is flowing this way, magnetic field will be like this in loops around the wire. So if I were to take that wire instead and coil it up as we did in the drawing on top, what would happen is it would be the magnetic field would be like this, except when it got into that coil, what would happen is that certain things would cancel and you'd basically end up with something that looked like this. You'd end up with loops around the coil. Like that. So if the current never changes, how much resistance does a piece of wire have?
Yeah, it
Not,
has zero
not
resistance.
much. Yeah, not much. Okay. So what does it do if you run DC through it? Generates a magnetic field and what?
Short circuit.
Yeah. It just
Sure.
allows it to flow.
I mean, it's essentially just a wire with that's. I mean, I understand what you're saying. It's coiled around, but essentially, for all intents and purposes, it's a short circuit.
That's right. It's a short circuit. So for DC, an inductor, this is called an inductor. We reuse the letter L for it. For DC, this is a short circuit. It stores energy in a magnetic field. All right, but now it's happy. We have all that energy that's being stored. And now we're going to take that and we're going to switch it like this. And we're going to try to reverse the direction of the magnetic field. Well, that magnetic field energy is not just charges. It's actually a magnetic field. It's like magnetic field lines floating around in space. So what happens at that point is that for AC, it actually resists that current flow. If you switch it enough, you will get virtually you'll get very little current through it. This looks like an open circuit. Okay, so for AC, inductors become very unhappy. So you were asking about the points in your ignition, right?
Actually, I was asking about the condenser.
Well, okay, there's a capacitor that stores energy, right?
Okay, right.
But what's really important is the coil.
Right.
Because you have a coil that you would then use to generate a magnetic field.
So what they refer to as a condenser is really a capacitor.
That's a capacitor. Yeah.
Because I remember in shop, we could charge that up, lay it on the desk. Somebody pick it up and get a hell of a zap.
That's right. Yeah. It could be thousands of volts. Yeah. Not a lot of current, but a lot of voltage. Okay.
Just a lot of attention getter.
Yeah. So let's say that you have a DC, because cars run on DC.
Mhm.
You have DC, right? You generate a magnetic field, and then suddenly you disconnect the battery. What are you left with? What's there?
It's a short. Well,
you have a magnetic field. What is that magnetic field?
What is
potential energy?
It's energy. Yeah. And where's it going to go?
Well, if it's in a coil, it's going to go. Well, I kind of know how.
Yeah. Well,
I don't want to give it away.
It has to go somewhere, right?
Does it radiate as heat?
Nope. What happens is
it's inducted in both coils.
Yeah. What happens is that you end up with this coil reversing. It's basically creating a reverse current that tries to somehow dissipate the energy across that gap.
And this is DC we're talking, right?
This is DC. So what happens when it tries to generate a current across that gap? What is current?
It switches it's the
tries to jump.
Tries to jump. And
what's arc?
Yeah, what's jump
Arc.
across an air gap? Jump across an air gap looks like a spark. And it actually generates a spark. And this is how your car used to work. This is how ignition coils would work.
Oh.
You would intentionally break it. Those were called points. And then you would conduct the energy down to your cylinder into your spark plug, which was intentionally located inside a puddle of gasoline or vaporized gasoline, which would generate a spark, which would ignite the gas.
So is this essentially what you were talking about is inside a capacitor when you have an opening and distance, and this would be like air?
Yeah.
Okay.
Yeah. And in fact, what you have there is that gap in the spark plug, right?
Right.
And you have a high enough voltage, it's going to generate, let's say 50,000 volts, which is going to be enough to jump that gap and generate a spark. So your ignition system in your car is actually uses an inductor,
Which is the coil.
which is the coil, and a capacitor to make a spark. Okay, so this is measured, we call it our letter L. That's measured in henries, or letter H. This is our capacitor. This is measured in farads. We use the big letter F. And as it turns out, we are lucky in a way that when we said that we get, when we said that a capacitor, for instance, is an open circuit for DC and a short circuit for AC, and an inductor is a short for DC and an open for AC, open circuit, it is not exactly quite like that. It actually, we now have to introduce another term called impedance. Impedance is a measure of something's resistance to flow of AC current. What was resistance? R? Is the resistance of flow to DC current. So what this means is that we have two things at play here. The resistance is the resistance to DC current, and the impedance is the resistance of flow to AC current. In a resistor does not care whether it's AC or DC. It's just a block of carbon. It responds the same way. But capacitors and inductors, by virtue of this right here that we just proved, they have very, very different resistances and currents, resistances and impedances. And in fact, the tricky thing with those is that, and actually we're really quite fortunate, is that it's not completely black and white, even though this drawing may be. That the Z of a capacitor is -1/2 pi FC.
I see.
And for an inductor, it is +2 pi FL.
Now,
those are our impedances of our inductors and capacitors. And one thing that's important to note is that if we draw this on a chart, we're going to draw another circle. This is our resistance. And this is known as our reactance. Reactance and resistance together create impedance. And
how do you define reactance?
Reactance, this is actually the value of reactance, and it is kind of like impedance without the fact that it's 90 degrees shifted.
Okay.
Notice that those are 90 degrees apart. So this is where it gets a little bit tricky, for instance. So if you have 3 units of resistance and 4 units of reactance, how big is your resultant vector? Does everybody remember Pythagorean theorem?
25 or 5 ohms.
5 ohms. And more importantly, it's going to have an angle associated with it.
Shit.
Yeah, I know, right? I heard that. I heard that.
I just, it's been 45 years since I've done this.
Okay, so What that means is that what's Ohm's law again?
E equals I times R.
In fact, that's not quite true. E equals I times Z, where Z is actually complex and consists of R plus JX. But you don't have to remember this for this exam. What is important to remember is that this does exist. And when you go to take your extra class exam, you'll say, I remember when Scott showed me that. Aha. Okay. And why is this important? Because this is what we call a little bit of extra stuff. What's that formula again? E equals I times R, but we can rewrite it as E equals I times Z. And if the Z is actually like this, where it's 5 ohms with an angle of, let's say, 55 degrees, and we have a sine wave, we have our current that looks like this. This is our current. Our voltage will actually be shifted 55 degrees ahead.
Oh, interesting.
You'll actually have a phase shift of 55 degrees. And when you get to your extra class exam, that question will be on the test. I strongly recommend you all someday make it there, and this will hopefully demystify it. The other interesting thing about this is that we have the ability to do this, where this is J2 pi FL. We're going to get rid of the J just to be fun, because we don't need it there. And we have minus 1 over 2 pi FC. Well, these things are in series, are they not? Let's hook it up to a battery. The way I drew it, these are in series. We have ZC and ZL. Notice the only thing that we have here that's different between all of these. We have an F that's common to both, and we have a C and an L. So if we were to creatively pick our F and our C and our L, could we make these so that they were equal and opposite? And they were minus, balancing out a plus. What happens if they're equal and opposite?
They cancel each other out?
They cancel each other out. At one particular frequency, F, that we have chosen, this is known as resonance.
Oh, wow.
And what that allows us to do is if we pick our C value and we pick our L value, what that means is that for exactly one particular frequency F, we will have these completely cancel each other out. And as you get away from that frequency, the degree to which they cancel each other out disappears. So if we were to draw this on a graph, it would actually look like this. Where this is our frequency. And this is our impedance. What does that mean? If we build a circuit that looks like that, what does that allow us to do? What frequency gets through?
None.
No,
Just
there's
that
one. Just
Sorry.
that one.
Just that one, yeah.
Just that
Filter.
one. This
Is that
is
like
a
a notch? Is that they call it like a notch filter?
well, that would be a pass filter.
Or pass
You could also
filter?
flip it and it would be a notch filter. But this gives us the ability to build frequency dependent circuits. And this is the entire basis for radio. This is how radio works.
Wow.
Capacitors and inductors, creatively placed, make this stuff possible.
How about that? Oh, they do.
And if you put them in parallel, like that, they work one way. And if you put them in series, they work the other way. This would be called kind of like a band pass, and this would be like a band reject. And these have applications in every frequency dependent circuit. And sometimes, if you want it to be tunable, you can do that and make it adjustable. You can also have a resistor and have that be adjustable. This is called a potentiometer. You can also have an inductor and make it adjustable.
That's your tuner.
And that becomes a tuner. You can actually continuously change them, and that changes the resonant frequency of the circuit.
Tank circuit?
That's also known as a tank circuit.
Yeah, it's been a long time.
But you know what? The technology is still basically the same.
Wow.
Okay, so now what we're going to do is we're going to use these things creatively. So we're going to do this. This is another really important thing. Okay, what exists if we do AC? What exists around that first coil? What does current do through a coil make? Makes a magnetic field.
Yeah, magnetic field, and then it actually cuts through the other coil, it makes a current.
Well, we make a magnetic field that goes like this, and it's changing direction. Everybody agree with that?
Yeah.
Yes.
Changing direction, back and forth and back and forth. What do you notice about that second coil? Where is it physically located?
It's a distance from the first coil.
Right, but it's in the magnetic field.
Oh, okay, yeah, it's in the proximity of the magnetic field. Yes.
So if a wire with current makes a magnetic field, a coil or a wire that is in a changing magnetic field makes a current.
Gotcha.
And so what happens, this is called mutual inductance. And what we do is we take these coils and we wrap them around a core that's made of iron. Usually iron is a ferromagnetic material, and that means that it responds very well to magnetic fields. And what it does is it actually constrains most of the magnetic field energy, and it channels it through the second coil of wire to the tune of, let's say, 99% efficiency. So when you generate an AC magnetic field that's switching back and forth and pass the second coil through it, that generates an AC current coming through those wires. Now, why would we want to do that? The reason we would want to do that is there's another interesting thing about this, which is, let's say that we have 10 turns of wire over here, and we have 2 turns of wire over here. If we have a voltage, let's say 100 volts, the output voltage over here, so this is voltage in and this is voltage out, will be proportional to the number of turns of wire that the magnetic field is passing through. So if we have 100 volts with 10 turns, we have 2 turns over here. How much voltage will we get?
200 volts.
20 volts.
Or
Remember,
20 volts. I'm sorry.
remember, this is only AC. So this is 20 volts AC.
Is that a transformer?
This is known as a transformer. Now, interestingly, let's say that we measure that we get 1 amp of current over here. We get how many amps of current over here? We're going to assume that this transformer is 100% efficient. So if it's 100% efficient, that means that energy is neither what, everybody?
Lost.
Energy is neither created nor
it's not lost or destroyed.
Right. Energy is neither created nor destroyed. It just changes form. So we can figure out the power over here. What's the formula for power? Ohm's law again.
Equals I times E.
I times E,
voltage.
which is, yep, 1 times 100, which is how many watts? 100 watts.
100.
Okay. We already know that on the other side, we have 20 volts. We do the same thing. P is equal to I times E, but we already know that because we have a transformer that's 100% efficient, if we have 100 watts going in, how many watts do we have going out?
100.
100 watts. Can't go anywhere else. P, I, E, same thing. We know that this is 100 watts. We know that this is 20 volts. I is equal to 100 divided by 20 is equal
Right.
to 5 amps. So here's the other tricky thing. Well, if we assume that we have 5 amps and 20 volts, can we figure out what the resistance is that must be here?
Yes.
Sure, because we have what law again?
E equals I times R.
E equals I times R. We have
Got the
Ohm's
R.
law. Remember I said almost everything is solved by Ohm's law?
Yep.
E equals I times R. Well, if that's the case, R, E, I, R, we don't know R. R is equal to E divided by I is equal to 20 divided by 5 is 4 ohms. Okay, so it must be 4 ohms over there. So now we're going to do the same thing on the other side. Here we go. This is 20 volts AC. Looks at 4 ohms, 5 amps. Okay. Now let's look at the primary side, which is on the left.
Same thing.
Same thing. E is equal to I times R. E, I, R. Uh-oh.
So
Where'd it go? There we go. What? Why did I just lose it? Hold on. Oh, come on. Don't do that. Sorry, hold on a second. It just did something bad to me. Okay, can everybody still see that?
Yep.
God, I'm really starting to hate this. There we go. Okay, here we go. Let me erase that. I think I may be getting too close to the bottom. Okay. So by that same formula, R is equal to E divided by, no, it's the other way around. See, that's why I like doing I like doing the circle. E, I, R. R is equal to 100 divided
100
by
divided
1
by-
is
100.
100 ohms. Well, what was the resistance on the other side? Or the
4.
impedance? 4 ohms. And on this side, R is equal to 100 ohms. Okay, so what is the ratio of the turns on one side to turns on the other?
Ooh.
5 to 1.
4?
5 to 1. 10 to 2 is
5.
5 to 1. What happened to the resistance? It was 100 over here and 4 over here. The resistance
Way
changed
less.
by the square of the turns ratio.
How did you get 5 to 1 again? I'm sorry.
What's 10 turns versus 2 turns? What's the ratio? 10 to 2.
10 to 2, yeah. Okay.
Which is 5 to 1. The impedance on one side, or the resistance on one side, changed from 4 to 100, which
I
is
see.
5 squared. It's 25 times. So this actually not only can be used as a voltage changing device and a current changing device, but by definition, it also is a resistance or impedance changing device. Transformers are magic. We actually use this for impedance matching. If you've ever heard of a Ballon transformer, which you will, This is what a balun transformer is used for. It allows us to match one impedance to another. Okay.
Is
So
the
now-
balun used for antennas?
Yep.
Okay.
Okay, so that's a transformer. So now what we're going to do is we're going to draw 120 volts. And this is actually in the book, by the way. Let me look and see what page it is. Give me 1 second here. I don't know where it is. There it is. Okay, it's on page 29 of the book. Okay. So here is a transformer. And we're going to have a 5-to-1 turns ratio. That means we're going to have 1/5 as much voltage over here. So we go from 120 volts AC to 24 volts AC. Right now we're going to add another device, which we haven't done yet, which looks like this. This is known as a diode. If you physically look at one, it's usually a little black device that is built of a semiconductor material. Notice we had an inductor, notice we had an insulator and a conductor. This is made of a semiconductor, usually silicon, sometimes germanium. But for the most part, they're made of silicon because there's a lot of silicon in the world. And the way that this works is, notice that this has, notice this has an arrow essentially. This allows current to flow only in that direction. The way that it works is that you have a forward biasing voltage, typically of 0.7 of a volt for silicon.
Avalanche voltage.
So if you have more than, let's say, 0.7 of a volt like this from a battery, you will get current flow. If it drops below 0.7 of a volt, you will no longer have a one-way sign. If you reverse the battery, so it looks like this, you have a plus and a minus, that will also block its current. So what's nice about a diode is that it only allows current to flow in one direction. So there are two terminals. These are the anode and the cathode. The cathode is indicated by a little black stripe. When you draw it, it also gets the little stripe here on the right-hand side. And it is like a one-way street sign. Looks like that. It only allows current to flow in that one direction. The way that it's actually built internally is that you have two pieces of silicon. One of them has some extra extra positives in it. The other one has some extra negatives in it. And depending on the voltage that is connected to, this has to actually be able to overcome all the extra positives that exist in order to get electrons. And if you try to stuff it back the other way, it doesn't work. So this is actually made of doped silicon, which is silicon with intentionally added impurities to make it only action. These have been around since about, in solid state form since the 1940s. In vacuum tube form, these have been around a long time before that. They're called rectifiers. Okay, so we have our diode, which again looks like this, which allows current to flow in one way. Very importantly, we have a picture that we have to draw. What does AC look like? What do we usually have for AC?
Sine wave.
Sine wave. Okay. What happens at the top part if that middle line is at 0? What happens when it goes above? Are we in the plus or the minus?
In the plus.
In the plus. What do we know about a diode when it's plus and minus correct?
It'll allow current to flow.
It allows current
And
to
it
flow.
only starts at 0.7 volts.
Yeah, but let's just assume it's ideal and it always works. So
Okay.
it'll allow that to exist. What happens when the diode goes negative?
It stops it. It will not
stops
let it-
working.
Stops working, yeah.
So you get this that turns off, and when it goes up high, you get this again, and this
So you get
again,
kind of a sawtooth.
and this again. Well, it looks like this.
Ah, yeah, okay.
So that actually has a name. What's that called, everyone?
I know it, but I don't know it.
That is actually that is actually DC. It's
DC.
really
Oh,
ugly.
DC, yeah. It
It's really
rectifies.
ugly,
I mean,
but does it ever go the opposite direction?
No.
It never goes the other way. So we started with AC on that side, and what did we just make?
DC current.
We made DC.
AC to DC.
Wow, look at that. We turned AC into DC.
Woo woo.
That's pretty cool because now we can take this and we can do this with it. What happens when the voltage goes really high at the peak of that cycle? That capacitor does what?
Charges.
Charges up, right? But then what happens is we get down to the bottom. What happens at that point?
Discharges.
It discharges and puts its current back out to the world. So what does the net result look like? It never fully charges up, but it never completely discharges
Smooths
the
it out.
circuit either. And it smooths out the wave. That is known as filtering. We are filtering out the highs and the lows. Okay, so now we're going to add another thing here. A special kind of diode.
Light emitting.
That's a light emitting diode. We have them on the back of our phone. We also have this. What am I going to draw right there?
Have an LED light at some point, wouldn't you?
This is an LED, but how about down here? This is our ground. And why would I assign a ground? Because I want a reference point for my circuit. That's my 0 volts. All right, so here's my LED. Why would I put an LED in there?
To watch when the current is actually being filtered.
It's a visual
visually.
indicator.
Yep, visual indicator to show that my circuit is actually powered. Okay, now I'm going to add one more thing, which goes against something that I just said. Here we go. Let's get rid of the filtering. Because now we have something that looks kind of ugly. It looks like this.
Oh, I think I know what you're gonna do. I think.
Everybody
I'm gonna
see
hit
that?
Stone Bridge.
What? How happy would your computer be if it was fed power that looked
It
like
wouldn't
that?
like it. It act really erratic. It
Really
needs
weird.
solid 5 volts.
So what we're going to do is we're going to take a diode that's turned backwards. Like that. That's a Zener diode.
The Zener. Okay.
And that is a very
Rectifier?
Nope, we've already done the rectifier.
Oh, okay.
This right here, when we added the diode, that's actually the rectifier.
Rectifier. Okay.
Or known as rectification or fixing it. Okay.
You're
so
just
now,
kind of like you're kind of massaging even further. Well, go ahead. I'm sorry.
well, you need to, but without it, it's really ugly. So
Yeah,
what
you
we're
get
going to
your
do
ripple
is
at that point.
we're going to add a resistor right there that allows us to smooth out the voltage of the circuit, and current limiting. And then we're going to add this thing, which is our Zener diode. Notice that looks like a diode, doesn't it?
It does.
Yeah, except that it's turned backwards. And what did we just say? Which
Well,
way
it
does the
can't go one-
diode?
It
The
can only go one
diode,
way.
yeah, a diode flows that way, except that in this case, this is a very special diode that actually breaks down at a
Is that like
certain
a
voltage.
like a surge protection?
It functions as that sort of, but it's not it doesn't break down like continuously. I mean, it doesn't break down once and that's it. What happens is if the voltage, this is going to have a rating associated with it. Let's say
Oh, the
5
volt
volts.
voltage. Yes.
Let's say it's a
so-
5 volt Zener diode. What will happen is that this voltage coming in into the Zener diode, if it gets above a certain point, it will actually cause current to flow backwards through the diode above a certain voltage. That volt, that
modulator.
what will happen is it will actually allow us to get rid of all the hills, and then we get nice clean voltage, nice clean DC voltage. So essentially this Zener diode takes the abuse of all the extra voltage and it throws it to ground. It allows the extra voltage to generate current, enough current, which smooths it all out. And that's how a Zener diode works.
So anything above 5 volts goes directly to ground.
Well, it causes
5
current
volts.
to flow, which drops the Zener voltage to 5 volts.
Okay.
Okay, here we go. And it doesn't have to be 5 volts. You could get a 12-volt Zener. You could get a 42-volt Zener. They're built to operate at different voltages for voltage rectification. All right, here's another thing we're going to do. We're going to take that diode and we're going to make a sandwich. Kind of like a peanut butter and jelly.
Transistor.
Depending on how we do it, depending on which way we squeeze those things together, and then we add a terminal to the middle one, like that, that turns into a device known as a transistor. And in fact, it's a silicon transistor. This is actually known as a bipolar junction transistor, which makes all of your electronics possible today. Your computer would not exist without this, or if it was built with vacuum tubes, your laptop computer would be the size of your house. So, and it would operate at 1,000th the speed, and it would also consume all the power in the entire neighborhood. So, it's a really good thing that these exist. Notice we have our arrow, like there. So obviously this is a diode of some kind, and this is actually a PN because of the direction of the arrow. It's also an N. So this is known as an NPN bipolar junction transistor. What this does is when current flows in here, it allows a larger amount of current to flow that way. Essentially, it opens the gate. This is known as the base. And current flowing into the base allows a very large copy to go from a very large multiple of it to go from the collector terminal to the emitter terminal.
Can you sorry, there's some noise in the background. Could you say that one more time? Because the noise distracted me. I'm sorry.
Okay. So if current flows from the base to the emitter, because we have a positive voltage here and a negative voltage here, we get a very large multiple of the current that's allowed to flow from the collector to the emitter. And what's important about this is that there's 3 parts of this range of a transistor. This is known as cutoff. This is saturation. And this is the linear area. Okay, so because it makes a large multiple, right? This is the input, this is the output. What happens is that below a certain point, the transistor basically doesn't work. There's not enough voltage to turn it on and make stuff happen. Above a certain point, you can stuff more electrons into it, but it's already full. The collector to emitter channel is full. You can't get anything more out of it than it can carry. So this right here, the cutoff and saturation mode, this is how computers work. Using transistors as switching devices. Switching either 1 or 0. You don't want that in between stuff because it's ambiguous, right? You either want it to be on or off. Computers are digital, 0 and 1. The stuff in here, though, notice that that's basically a straight line where your input and output are related. This is known as the linear range, and we use that section for amplifiers where we want to make a big copy of something. So transistors find their way into computers as well as amplification devices. So what we're going to draw is a circuit that looks like this. Whoops, didn't want that. Okay, this is a bipolar junction transistor. Here's the base, collector, emitter. And we're going to connect this to a lamp and connect this to a battery and connect this to a switch. There's the base. Here's the switch. And I need to finish the battery here. Okay, so notice we have two batteries in this circuit.
Yeah, I was gonna say, yeah.
This is actually really important. You don't have to, but we have two completely separate circuits here. Essentially, the transistor is isolating the two
one battery
sides
together.
of the circuit. So we have this part of the circuit, which is controlling the base to emitter junction. That determines whether the transistor turns on or off. And then we have the other side, which allows current to flow from the collector to the emitter based on what's happening on the other side, which allows the light to turn on and off from this other power supply.
Wow.
This is using a transistor as a switch. Essentially, when you close this switch, it allows current to flow from the base of the emitter, which opens up the very large collector to emitter junction and allows a lot of current to flow. And because you now have this circuit goes around like that, the light turns
Almost
on.
like a solenoid almost.
It is. It's an electronic switch.
Yeah.
Right? A solenoid is similar, except that a solenoid does this. This is actually called a relay, where you have a current that flows through this coil. When it's energized, it creates a magnetic field which pulls a metal switch down and completes a circuit.
And it's a large amount of current flow through.
Yeah. So this would be a solenoid
That just
relay.
makes me think of that, so.
Yeah. But the other one on the left, that's a solid state circuit. Because it's transistors.
Yeah.
All right, and it's almost time for lunch. So what we're going to show you now is other applications for a transistor. So there's, again, a bipolar junction transistor, which looks like that. Or base, collector, emitter. This is a BJT, bipolar junction transistor. And the way to know, there are two different kinds of things. You can have a PNP or an NPN. The easy way to remember this, which way is that arrow pointing? In or out?
It's pointing out.
Would you say it's not pointing in?
Correct.
There you go. Not pointing in. NPN. That's how I've always remembered.
I see.
Not pointing in. Okay. The other one is something called a FET, or a field effect transistor. Okay, you have a gate and a drain and a source. All right, so very importantly, what does this thing in the middle that I'm going to surround in green, what does that look like?
Capacitor?
It looks like a capacitor.
Yeah, and in fact, it is a capacitor, which means that a bipolar junction transistor is a current device. It's operated by current. This is operated by voltage. So which one do you think uses less energy?
The FET.
The
Yeah.
FET.
Yeah, and in fact, the FET is the one that shows up in all our computers because it's like way more efficient. Like much more efficient. Okay, so what happens is that we put a voltage on the plate, on the left-hand plate, and that causes an opposite voltage to show up on the other side, which either opens the channel or closes the channel. And again, the same way with the bipolar junction transistor, we have the ability to operate it in cutoff and saturation or in linear mode. We can draw that same curve that looks like that. So here's off, and here's on, and here's linear, where you get a nice slopey. Okay, the next thing we're going to do is we're going to show this is actually on page, let's see. It's on page 31. Okay, page 31. It's a circuit that looks like this. Oops. Here we go. Okay, so here's our circuit. And this is variable. That means it's tapped. This is variable, and this is variable. Okay, so this on the right-hand side, this is an antenna. And this is where we start to do a lot of practical stuff. We did power supplies. Now we're actually starting to look at boxes that are useful for us. So this has an impedance, Z. This right here is what, everyone?
What's that? What is what?
I couldn't see where you pointed.
Oh, the arrow.
Oh.
Variable capacitor.
That's a variable capacitor.
Oh, okay, yeah, I'm sorry.
So this is an air variable capacitor. And the way we achieve this is like, here's a semicircular plate, and here's another semicircular plate that's spaced away from it. How meshed together are those plates? Not at all. So that has essentially no capacitance, almost no capacitance. However, we could draw that top plate, and if we were able to rotate it, we could make it go like this.
Oh, well, it's weird.
We could partially mesh them. We could do this and completely mesh them together so that they are completely parallel with each other and right next to each other. That maximizes our capacitance. So what we are able to do is, this is known as an air variable capacitor, and we're able to alter our capacitance based on a tuning knob, for instance. Okay, so now we have an antenna Z with a ZC2. We'll call this capacitor 2, call this capacitor 1, call that L. This over here, the Z with the antenna, is actually in series with the first capacitor, or sorry, capacitor 2. And then, because we're dealing with signals and things like that, you can actually view the antenna as sort of being at ground in a way, in which case you now have those two things in parallel with the inductor, which is then in series with the capacitor 1, and this gets fed into your radio. Which means that by creatively adjusting the frequencies, or sorry, by creatively adjusting the values of
C1, C2.
Those devices, C1, C2, and the inductor, what we are able to do is we are able to create an impedance matching network. And this you will find if you're on the air, you'll find them all over the place. And it looks like this. Let me share, make sure I share the page. Come on, where'd you go? Okay, can everyone see that?
Yeah.
Okay. hopefully. Okay, there we go.
Oh, wait a minute. Okay.
What do you see in there?
ABR meter.
I see a tuner there, and I see the.
Yeah, but what's the tuner? What we're focusing on is the tuner. What do you see
Right.
in there?
I see the coils. I see the capacitors. I see how they're rotational and
The variable inductor.
Yep, the
I see
variable
the inductor to
inductor
the left.
is actually hooked up. Notice all that bunch of wires that are connected to it?
Yeah.
That is actually connected to the inductor setting. Notice it is a 12 position rotary switch. So that's actually variable, but it's tapped. Instead of being continuously variable, because that's actually kind of hard to build and kind of expensive, it's much easier to build variable capacitors. And that's why we use those. So we can match our impedance of our unknown antenna to something that the radio is happy with.
I'm glad you showed me that because I got one of those back here that I actually use with my my little setups. That's
Yep.
awesome.
Yeah, I have a whole bunch of them because they're ubiquitous and they work very well. They're extremely important for impedance matching. Okay, let's see. Moving on, we did resonant and tuned circuits. Okay, so now we're just gonna do a couple of small things. Okay, a relay is an electronically controlled switch. An SPDT switch. Okay, so SPDT, that's single pole double throw. The number of poles is the number of contact pairs that you have. So single pole means that there's one circuit. Double throw means it can go either one way or the other way. A double pole double throw would have two parallel circuits that you would operate at the same time. A device that displays an electrical quantity in a way that you can read is called a meter. An integrated circuit is a package of a bunch of small components all built onto a chip. A regulator is something that controls the voltage out of a power supply. And since we built a power supply, that makes sense. Okay, a fuse. We didn't do a fuse yet. Okay, a fuse is, okay, new whiteboard. Okay, yes, I know. Please move on. Okay, so we have a circuit that looks like this. Here's a switch, so we can turn it on and off. And then we put something right here. This is a fuse, which connects to a resistor, which connects to nothing. Okay, so this is going to be, let's say, 100 volts DC. This is going to be our R. And we have sized everything so that our R is going to be, let's say, 5 ohms. Okay, Ohm's law. P equals I times E equals I times R. So by this, we know that we get 20 amps going through there. We know that we get 2,000 watts. This is dissipating 2,000 watts. And what is this known as? This is a space heater. Right? 2,000 watt space heater. Okay. So we now have a 2,000 watt space heater. We close the switch, the space heater turns on. But something bad happens and we end up with a partial short circuit, which changes this space heater, because this is now carrying 20 amps. It's been designed to carry 20 amps. And something happens, and this now suddenly becomes 2 ohms. It used to be 5. So now we're going to recalculate our circuit and find that we are now carrying, instead, we are now carrying 50 amps, and we are now dissipating 5,000 watts. And we are dissipating 5,000 watts over here. Okay. In addition, this wire is now carrying 50 amps. Okay, what are some of the risks of this happening? What are the things that would happen?
Overheating.
Okay,
Overheating the conductor.
Yeah. Okay. Which thing is going to happen first?
First, you catch the
It's gonna
furniture on
blow.
fire.
Right. Potentially, but not
It'll-
necessarily. What
it'll
else could
disintegrate.
happen?
Melt the wires.
Melt the wires.
Have a thermal. It'd be a thermal meltdown.
Right. What happens if they're underneath it? What happens if it's under a rug?
Well, that causes fire. The energy's got to go
You
someplace.
set the rug on fire. That's right. Okay. What happens if the rug doesn't catch fire, but this is plugged into the wall somewhere?
It'll blow a fuse
What if
on the breaker
Melt
box.
wires inside
are
the
you
wall.
right? Are you sure?
Well,
No, we're not sure.
We'll hope.
Exactly.
First thing would start a fire.
Right. Okay. So basically, you're going to end up with a fire somewhere. But the question is where? Is it going to be in the heater itself? Is it going to be in the switch? Is it going to be in the wire because it's now carrying more current than it's designed to? Is the power system gonna catch fire? Something's gonna catch fire. So what you're going to do at this point is you're going to add a fuse right here. A fuse is an intentional weak link in a circuit that is going to melt on purpose before everything else.
It's a sacrifice.
It's a sacrificial element. That's what a fuse is. It has a rating of volts, operated up to a certain voltage, and amps, as well as an interrupting rating. That once it blows, it's going to be, it's going to be able to withstand certain voltages that exist. Because if it blows, but it turns into like a carbon track or something that conducts electricity, that's not good either. So the idea is that you pick a fuse that is going to protect everything in the circuit downstream, so that if something goes wrong in this circuit, it's going to be the first thing that fails. The fuse is going to blow, and it'll hopefully keep your house from burning down, which is why you never replace, unless you really know what you're doing, you never replace a fuse with one of a bigger value, because it might allow certain things that you didn't expect to happen or didn't want to happen.
Well, if you do that, then you definitely don't know what you're doing.
Well, unless you did it on purpose. I mean, I've occasionally done that, but it was for testing, not in my house. So, okay, a reason to use shielded wire. If you have two wires that are running in parallel with each other, why would you shield one from another? And that's because every wire that carries a current makes a what?
Magnetic field.
Okay, and any wire that's in a magnetic field can have what happen to it?
Interference.
Yeah, if current makes a magnetic field makes a
voltage.
No, it makes it and a current.
Yeah, it
right?
becomes a live wire.
Right. Essentially, any wire can function as a transmitting antenna and a receiving antenna. So if you have two wires that are right next to each other and they're not shielded, you end up with crosstalk between the wires. They're magnetically coupled together. Okay, radio wave characteristics. I think that's going to be after lunch. Because, yeah, propagation modes, antennas. All right, what do y'all say? It's time for lunch.
Yeah, how long do we go today? I wondered. I mean, I know it's West Coast on your time.
We go till 4 o'clock West Coast time. So
Okay.
So how about we come back in 22 minutes.
22 minutes.
22 minutes, 1 o'clock our time. And come back with your questions.
Sounds good. See you in a bit.
And as it turned out, I think we peaked at 80 people, so I guess I didn't need to spend that $50 anyway. But then, it's buying myself a little peace of mind, right?
That's right.
And you know what's crazy? I had 150 people on the roster. So
Crazy.
I hope this isn't, too high level. I hope you guys are enjoying it. I hope it's, palatable. So
It's working out good.
It's not too high level for me.
yeah, it's a lot of material. That's why you gotta that's why there's a lot of studying involved too. And the studying brings questions, and going through the material will hopefully get you to understand some of the reasons why some of the questions are not obvious. All right, see you in, okay, 21 minutes.
Okay.
All right, let's hear questions if anyone's back and has questions.
Can you talk a little bit more about the FET and the FET and how it is, what's the doping there and the capacitance? I didn't catch all that.
Well, I mean, if the FET is actually it's either an N channel or a P channel. The construction is considerably different than a bipolar junction. If you let me see if I can find a good picture of one. Da, 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 da. Let me see if I can find it. Okay, so there's you see the photo there?
Yeah.
Yep.
So I mean the construction is considerably different, whereas it's typically, you're going to have a sandwich with a bipolar junction transistor.
Yeah.
In this case, it's literally that the gate is kind of like acts like a capacitor.
Okay.
And
I got you now.
I guess as it's operating, this is what it looks like. I'm not an expert in semiconductor physics. I like semiconductor physics, but
All right. Well, I'll just look it up on my own. Thank you very much.
yeah, I gotta leave more of some of that more complicated stuff to the guys who actually did, semiconductor physics and got their PhDs and.
Okay.
Scott, are you in the robotics? Is that what you do in your full-time job, or?
Factory automation.
Oh, cool. Very cool.
That has nothing to do with RF.
You seem like you're pretty knowledgeable, like you've been doing this for a while.
I've been doing this for a while.
Yeah.
So, actually, when we get back, I can give a quick chat about that.
Yeah, my question was going to be, I certainly enjoy physics and everything that you're going over, but of course, I want to make sure I pass this test tomorrow. And I'm wondering how much of the in-depth stuff, because I've done a number of sample tests and I'm doing pretty good on those. But it seems like a lot of the stuff you've been going over today gives us all the very underlying stuff that might be more for the extra or general class.
Most of it's for the most. I mean, most of it's just applicable to radio theory.
Hmm.
It's one of those things that there's a lot of stuff that you really can't explain adequately without really explaining it.
Hmm.
So
I
either
had this stuff and
either I gloss over it and just mention it with 3 words, or I spend 5 minutes and and
Yeah, no,
go
I think it's
into
been
it.
great seeing how some of these items are actually made. We see a diode and it's just a thing, right?
Yeah.
With a stripe on it. We don't see what's inside unless we crush it and
Mhm.
kill ourselves.
Right.
Now, I had this stuff like back in 1980 when I was in radio and TV repair class. We had to do the super heterodyne circuit. And all that it's been so long since I've done this. It's like my brain is like getting the cobwebs out. That's good stuff, though.
I like I'm sorry. I like the fact that you actually brought up the antenna tuner so that we could visualize exactly all the components. And like I said, I have one behind me, basically the same model, and I use that with my unit in Bearcat with an 18-foot vertical. And I learned how to use it through a friend of mine who just said, okay, use your audio, find the clearest, and then start tuning.
Right.
And then you check your meter and you get the as close to one-to-one match.
Right.
But I don't know the principle and theory behind it.
Mm-hmm.
So that was very helpful.
It's all mathematics. So if you really want to understand it, it's all about the math.
Yeah, my next door neighbor is a ham, and up until very recently, I didn't have that much interest in what he was doing or even getting my own license. He's been trying to create an antenna underneath the eaves of the house for HOA reasons.
Yep.
And he says he's running into trouble with it. Of course, I didn't. Maybe after today and tomorrow, I will have a better knowledge. Go over there and I'll solve his problems.
Well,
one thing I was going to say, talking about the HOA thing, there's a guy out there on YouTube that did a dish antenna modification using slots for 70 centimeter and 2 meter. So
there
give that a
are
look if you're interested.
So here's the thing about antennas, which we're going to do pretty very shortly. Antennas are the most flexible, most interesting place that you can make a significant difference and not have to spend a lot of money doing it, because we're talking with things that are macroscopic. They're construction projects, essentially. They're you solder stuff together, weld stuff together, cut and measure with a tape measure. And they don't have to be expensive. I mean, you can go and put up a tower and, spend $50,000 pouring the foundation and getting all the plans drawn up and have a, 75-foot freestanding tower and put all the antennas on it and bring out a crane to do it. But you don't have to, you'll do quite well just putting up a fiberglass pole or throwing a ball up in a tree over a branch, pulling up a rope, and just using a piece of wire that you soldered to something and made into an antenna because your calculations show that this is the right length to do something. And the biggest, okay, if you really want to get a superb antenna system, then you should go and spend that. But 90% of the contacts that you would make with that, you will still make with something less. You know what I mean? Because really the ultimate decider on, if you're talking about high frequency, the ultimate decider on whether or not you're going to make contacts is what the atmosphere, what the ionosphere is allowing you to make. You're not going to make your own propagation. Now, you might be able to operate when there's less of it, but you're not going to make your own propagation. So you might be the first one that's heard instead of the 25th person that's heard, but it's still going to work. So, all right, everybody ready to go?
I have a quick question about the test, if you don't mind.
Questions are good.
I've never done a test like this over the internet. So how exactly does that process work?
Okay, are you ready for, have you done practice tests? Are you ready for that?
I have.
Okay. So the process of taking an exam online is actually quite easy. You have two cameras, one of them on your computer, one of them on a phone or an iPad. And when you're preparing for the exam, everyone will basically look around the room, do a quick scan the floor, scan the walls, scan the ceiling, make sure there's nothing on your desk, and they'll direct you to a website, and the computer will look at your face, and the phone or iPad or whatever will look at your hands and the computer screen, and that's it.
All righty. That's
It's very easy, actually. It works very well. And it was actually, the process was developed by the Anchorage group a long time ago, because I've never been to Alaska, but I know Alaska is pretty big and very sparsely populated. So it was it was very impractical, especially for people who live out in the far reaches, to go somewhere, actually like take an airplane trip to a city to take an exam. So they petitioned for approval to be able to give exams remotely. But it just made more sense, and the FCC was good with it. And then, of course, with COVID, everybody wanted to stay apart, and it just made complete sense that would be, how things would go. So most VECs actually do that now. All right, so very quickly, we're going to talk about a little bit more math, just because we got to do more math, because everything is math. Okay, so prefixes. So we have, starting at very large, we have T for tera, G for giga, M for mega, K for kilo, and then units, and then little m for milli, and micro, and nano, and pico. Okay, so it's important to note, if everybody is not quite comfortable with powers of 10 are very important, because they allow us to remove, like going from 300 million to 3 times 10 to the 8th, right? We collect 1, 2, 3, 4, 5, 6, 7, 8, and we say that's 10 to the 8th. 10 to the 8th is 10 times 10 times 10 times 10, 8 times, equals 100 million. So that allows us to basically roll up a whole bunch of zeros that we didn't really need to see anyway. The other nice thing about that's going to come into play is 10 to the 8th times 10 to the 8th is 10 to the 16th. If the base is the same, the exponents just add. That's actually going to be very important when in about 2 minutes we roll into decibels. So this is a shorthand notation that allows us to make a whole bunch of zeros disappear. Really important. Okay, so with regard to that, tera means trillion, 10 to the 12th power, 10 to the 9th, 10 to the 6th, 10 to the 3rd, 10 to the minus 3rd, which is 1 over 1,000, which is 1 over 10 to the 3rd. So another way to write that is 10 to the minus 3rd, 10 to the minus 6th, 10 to the minus 9th, 10 to the minus 12th. If we have a negative power, let's say we have 10 to the minus 3rd is 0.001. If we want to prove that, we can go right with our decimal point. 1, 2, 3 spaces is equal to 1. And then we have 0, 0, 0 times 10 to the minus 3rd. And that's how we do that. Another thing we can do is, because another important reason that we do this is because a lot of things that we work with are not, like 6 or 14. They are very big numbers and very small numbers. Okay, so we deal with megahertz all the time. We could write 6482904 hertz or 6.483 megahertz. The way we do that is we just say, here's our decimal point, 1, 2, 3, 4, 5, 6. We now have 10 to the 6th. We can replace 10 to the 6th with the big letter M, and that creates a prefix. We use this to convert small things like 22 picofarads. If we really wanted to write this out, we could replace pico with 10 to the minus 12th. We go 22 and we go, because it's negative, 1, 2, 3, 4, 5, 6. But that's a good reason why we don't do that. A lot of unnecessary zeros. So now that we have established the whole concept of powers of 10, we're going to go and just do decibels. Decibels are very important. Decibels are how we measure one thing compared to another. So for instance, if we were to compare the number 10 to the number 1, we could say that it is 10 times bigger. I think everyone will agree with that. If we were to compare the number 10 to the number 4, we'd say it's 2.5 times bigger. If we were to compare 1,000 to 1, we would say it's 1,000 times bigger. Well, we know for a fact that the powers of 10 can get really useful because let's say we're not comparing 1,000 to 1, we're comparing I could write that that's, a trillion times bigger. I don't really want to do that. I can say that that's 10 to the 12th times as big, which I think if I did it right, I got to add one more zero. So I could write that's 10 to the 12th times as big, right? And if I multiplied that again, I wanted to compare that result to something even bigger, I could do that. And then I'd have like, let's say another 10 to the 6th. Well, I'd know through scientific notation, because I can add the exponents, that's 10 to the 18th. Well, as I see it, and as I think a lot of people see it, the fact that 10 really isn't all that important because we know that it's there. That's the base that we use for everything. Alexander Graham Bell tend to agree with us, I think, because he came up with a system for comparing the strength of things or the bigness of things. He used it, I think, a lot on audio signals. We use bells all the time in audio. A bell is the logarithm base 10 of something divided by something else. So this is the original thing that you're comparing it to, and this is the new thing that you're comparing it to. This is saying how many times bigger is something, and say what power would 10 have to be raised to get that. So if we were to, let's say, do log base 10 of 1,000,000 divided by 1, well, this is obviously 1,000,000. So what would 10 have to be raised to get 1,000,000? 10 to the what power?
The 6 power.
Yep. Well, yeah, it'd be 6. So that would be 6 bells. By Alexander Graham Bell's definition, that would be 6 bells.
Oh, that's his standard unit that measures bells?
It's a bell. Okay, but it turned out that a bell was kind of small. So they said, let's make it a bigger value. So we're going to say that it's 1/10 of a bell. That's the thing. And that's how we get a decibel. Deci meaning 1/10. So then we have now we have to multiply it by 10 log base 10 of P2 over P1 is equal to 10 log base 10 of 1,000,000, which we already said that that's 6, but now it's 10 times 6 is equal to 60 dB. This is just a shorthand way of saying how many times would we have to, what would the power have to be to get to that value? We have to take the base 10 and raise it to some power to get a representation of how big something is with respect to something else. because they're powers of 10, and we are actually looking at the exponents, one thing that's really cool about this is that let's say we have a transmitter compared to a milliwatt is, let's say it's a 100-watt transmitter. Okay. So 100 compared to 0.001, 10 log base 10 of that. Well, that's what, 100,000 times? That would be 5. So that would be 50 dBm. We then go through a piece of cable, which has a loss, because if you have gain is positive, it's bigger, you also have loss. So for instance, if I have the P2 is smaller than the original, the signal is now smaller than it started, that would be negative. That would be a loss of 10 decibels. Like I would actually have to say 10 to the -1 power to get -10. Okay, it now goes to an antenna, which has a gain of 15 dB, goes through space with a path loss of 180 dB. That actually means 10 to the -18th power. Remember that. We're talking very big and very small things, which goes to an antenna, which has a gain of, let's say, 15 dB, which goes down into the cable of 10 dB loss. Okay, which goes down to our receiver, which has a sensitivity of question mark. Okay, so what we're going to do now is, using all this shorthand that we just did, we're going to see how sensitive our receiver needs to be. And I need a volunteer who's going to start at the left-hand side and tell me what to write as far as pluses and minuses go. Somebody take it away. Come on, somebody be brave.
From the left to the right, it start out, you got 50 dB and you got
Right.
10.
So you got a plus 50 and a minus 10. Well, just give me the numbers. Plus 50, then minus 10.
40 dB.
Yep.
And then from there you got 15 dB. So then add 15 dB.
Right, because it's positive, because it's gain. Yep.
All right, now you're going up. Now you're losing 180 dB.
Yep.
And then you are gaining 15 dB.
Yep.
And then from there you are subtracting 10 dB.
Okay. And
which
what
is
do
a
I end
total
up
of
with?
50, 60, 75, 75 plus 80, 180. 75.
Remember, we got pluses and minuses. So 50, 40, and 65, 80, 70. So minus 110. Do you get minus 110?
I didn't get that. I didn't do that in my head. So I just, yeah.
Okay, I'm adding the pluses. So that's plus 80, 60. Nope, I get minus 120. Anyone else get that?
Yep.
Somebody want to double check? Okay.
How do you arrive at 120 dB as far as the pluses and it threw me off? I'm not sure.
You just add the pluses and minuses together.
Okay.
You just go through and don't make any mistakes.
Okay, I got it.
So if I wanted to say what this really means is, compared to a milliwatt that was transmitted at the beginning, my resulting signal is 120 decibels worse than the original signal.
Yeah.
And what does 120 decibels worse mean? It means 10 to the minus 12th power, or 0.00000000001 of the original milliwatt signal that got through to the other side. Now you see why we'd use decibels. So that means that if my receiver on the other end right there has a sensitivity of greater than negative 120 dBm, that means that I will hear the other station. If it has a sensitivity of less than minus 120 dBm, I will not hear the other station.
Oh, I see what you're saying.
That's literally what this means. This is system design. This is an understanding of when you need an antenna, or a bigger antenna, or a piece of cable, or a less lossy cable, or a shorter cable. Because this is the stuff that makes a radio system work. And that's how we, go ahead.
So is decibel loss based on length or quality of cable, or both?
Both, and frequency of use, and the frequency of the energy going through it. We're going to get to that too.
Okay.
Okay, so there are really only two things that you need to know from all of this, other than, you know, what decibels are and how to use them. 10 dB is exactly equal to 10 times. 3 dB is approximately equal to 2 times. That's it. That's all you need to know. You can get very, very close on almost any calculation with those two things. So if I let's say start at 5 watts and I have an amplifier and I go up to 50 watts, what's my gain in decibels?
10 dB.
10 dB. I have a 10 dB amplifier. If I have, let's say, looking at my antenna, I have 1 watt being received at the antenna. By the time it gets down to my cable, I have half a watt. What's my loss?
Is that minus 3 dB?
It's minus 3 dB. Exactly.
How did you get 3 dB? I missed that.
Right here. 3 dB is 2 times.
Just working it in the opposite direction.
Yep.
Since
It's a
1
loss.
watt and it's a half of a watt now. So
Right. It's a loss of half of your power.
Oh,
and
okay.
and it cascades. When I say it cascades, let's say that we start at 1 watt and we end up with 0.125 watts. How do you go from 1 to 0.125? This is also, I'll give you a hint. This is an
Well, it's
eighth.
a loss for one. It's an eighth.
Right?
Yeah.
It's an eighth. Okay.
Right.
So how many dB would that be?
minus 9.
Minus 9, because you go from 1 to a half to a quarter to an eighth. Every time you go down by a factor of 2, it's 3 dB.
Oh, wow.
They add. It makes it much easier to work with.
Yeah, this part I'm a little confused. This is I'm not.
This is just arithmetic.
Yeah, no, I get it. I'm just trying to get the not the concept down. That's all.
Okay, so let's start at 10 watts. We go through an amplifier that goes to 800 watts. Okay, Michael, tell me how to get from 10 to 800 by factors of 2 and factors of 10.
Let's see. So 10 dB equals 10x.
No. Just give me multipliers. 2 times and 10 times. Just give me steps. You start at 10. What's your first step?
10 times 8.
Okay. Well, yeah, but go even simpler. Either 2s or 10s.
10 times 2 is
20. Okay.
20.
Keep going.
20 times 2, I guess.
Sure.
Is 40.
Okay, keep going.
40 times 2 is 80.
Yep. Okay. And then how do I get to 800?
80 times 10.
Okay. Okay. So this is 2 times. This is 2 times. This is 2 times and a 10. So every time I have a doubling, what's the only thing you need to know? 2 times is 3 dB. 10 times is 10 dB. All right. So 2 times, how many decibels is that?
That's
3.
3
And then another 2 times?
is 3.
Yeah. And then another one?
3.
Oh, come on. Come
Two,
on.
two,
Stop
two.
moving. There we go. Why is it doing this? Hold on.
I think there's some
There
kind
we
of
go.
automatic zoom feature in there.
Uh-huh. Okay. And then the 10 times?
That's come on, Mike. I'm
10
not
times
sure.
is 10 times is how many dB? It's right there.
It's sorry,
These-
man.
These are the only things you need to write down. This is the only things you need to remember. 2 times is 3 dB. You can write it down 10 times if you want. 10 times is 10 dB. So we're going to take this 10 times. We just wrote down. How many dB is that?
That's 10.
Yep. Add them together.
Oh, it's 333. It's 9. It's 18 or 19.
That's it. You have a 19 dB gain in your amplifier.
Damn.
That's it.
That's
what.
If that's, I'm sorry. I wanted to ask with that
Yeah.
same, using those same numbers, do you have to start at 2x or can you start from 10x?
Do anything you want. The number, I mean, it's just going to shift where these show up in the math.
Oh, so it'll be just basically reverse.
Yeah.
Okay. Thank you.
Yep. Decibels make it very easy to work with systems of
I
things.
see it now. I see it now. It just I don't know why I was having trouble with it, man.
All right. So that's decibels. All right. So now we're going to move on to, before we do that, any other questions on that?
No, I got it now. It's just
All
that concept.
Anyone? Speak now. Okay. Moving on. Okay, so you guys can already answer these, I bet. The 2 components of a radio wave, electric and magnetic fields. We're on page 35, by the way. The electric and magnetic fields are at right angles to each other. Radio waves travel at speed of light. See, look how much you guys have learned already in one day, right? Speed of radio wave is
300,000
300 million meters per second. We already know this one, converting frequency to wavelength. Remember, we did the circle. Relationship.
Hey,
yeah.
I'm sorry, but I'm gonna have to get going. This will all be emails that we can look at it later, right?
Yep.
All right, great. Thank you very much.
Yep. Okay. Converting frequency to wavelength. We already did that. So if the wavelength and frequency are related, they are inversely related. So if the frequency goes up, the wavelength goes down and vice versa. Okay, so we actually call our bands, the frequency bands that we have access to, very frequently by the wavelength. And here's an example of that. Everybody see this?
Yeah.
Okay. So notice we have frequencies. We also call them, I'm going to go down to 15. 15 doesn't mean 15 megahertz. 15 means 15 meters. Colloquially, we call them by the approximate wavelength of the band. So the 2 meter band, if we do the math, what would 300 divided by 2 be?
150.
150, yeah.
Notice 150 is not a ham band, but we colloquially call 2 meters. 144 to 148, we call it 2 meters. Sometimes it does fall within the band, but for instance, 15 meter band, what's 300 divided by 15?
5.
Do that again.
300 divided by 15. I'm sorry.
Yeah.
Sorry.
300 divided by 15?
20?
That'd be 20. Although 15 meter band, you would expect 20 megahertz, except that our 15 meter band goes from 21.0 to 21.45. So it's approximate. We do approximate wavelengths. Okay, high frequency is 3 to 30 megahertz. VHF is 30 to 300. UHF is 300 to 3000. RF is radio frequency. And now we are into propagation and antennas. And I'm going to do antennas and feed lines first. Okay, because I think it's a little important. So we're going to scoot to antennas and feed lines, which is on page 46. Okay. Because you can't really explain what propagation is. I mean, I guess you can, but it's easier to explain it once you actually have an antenna. Okay, there we go. I'm going to clear this. Boop. All right. So this is actually a very important discussion because this is a fundamental of radio. It's very hard to have a functioning radio without a functioning antenna. So the first thing I'm going to do is draw this piece of wire. Okay, there's a piece of wire. I hope everyone can see it. All right, so looking at this piece of wire, what is the current at the left end of the wire?
What is the current at the left hand of the wire?
What is the current at the left end? Come on, everyone.
Zero.
It has to be zero. Okay.
It has to be, yeah.
What's the current at the right end?
Zero.
It has to be zero. That's right. Okay. So we're going to draw a wave. Okay. So this wave shows us what our current distribution looks like. When it's positive, right here, it's at its peak. When it's negative, it's at another peak.
Right.
So now my question is, where do we have zeros?
Where they intersect, where
Yep.
the
So there's an intersection right there. That's a zero.
Right. Zero. There's 3 zeros.
There's 3 zeros. Yep. But this one on the right is actually the same as the one on the left. But
right.
How about if we continue the wave in both directions? We're going to see zeros all over the place, right?
Well, yeah, it's
Okay.
constantly continuing that.
Right. Okay. So we have a couple of waves that we can draw on this antenna that meet what we call our boundary conditions. Our boundary condition is really one thing. What's our boundary condition? The current at the end has to be what?
Zero.
Zero. So we could do this. Everybody agree with that?
Say that one more time. What is that again? I'm sorry.
The current at the end has to be zero. So
yes, that's correct. Yes, that's correct.
So we could draw that, and it would meet the requirement, right?
Yep.
We could draw this, and it would meet the requirement.
Yes.
Yes. Okay.
Right.
How about this one?
yes.
Yes.
Yep.
Yes.
Okay. How about something that looked like this?
No. Yes.
Yeah.
Yeah,
Notice
yes, it's-
that it was on its way up to something and it got stopped, didn't it? Well, the only requirement is that the current has to be zero at the ends. Well, remember I was saying that, so long as the antenna is longer than 1/10 of a wavelength, it's still going to sort of function. It's sort of going to kind of do okay. This one right here, that brown one, is what 1/10 of a wavelength antenna might look like. Whereas if you were to draw it, it would peak way above that. And the thing that makes a radio wave is the current flow through a piece of wire. So in order to meet and maintain the laws of physics, you're never going to get the kind of current that you would expect, which is why it does not make a very good antenna. It can still work, but it doesn't work very well. So because of that, you look at the other ones where we're actually able to draw a complete wavelength or a half a wavelength or 3/2 of a wave or any number of multiples. Like the green one, that's actually, let's see, 1, 2, that's actually 3 full waves. Actually, 1, 2, it's 3.5 waves on that piece of wire. And it allows you to get up to the peak. So what this means is that there are certain lengths of antennas that obviously work better than others, right? Just looking at this, it has to meet the laws of physics, and the higher the current you can get to, the better it is. So certain antennas will work better than others. The simplest antenna that is out there is 1/2 of a wavelength long. Okay, so what's the requirement of the current at the ends? Everybody?
Zero.
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 Okay, if I draw a half of a wave that looks like this, everyone agree with that?
Yes.
Yep.
That's a half of
Yes.
a wave, right? This is known as a half wave dipole. This is the fundamental antenna in all of nature, right? This is also like, for instance, if you're doing a musical instrument, this is the first length that you'll get a resonance on. Half wave. Anything shorter doesn't work real well. Anything longer can work fine, except that you get lots of you get harmonics, and you get some array effects, which may be desirable and may not. This is the fundamental antenna that we're going to start with. All right, this is a half wave dipole. It's 1/2 wave long. And if I were to draw a picture of the radiated pattern that comes off of this, so let's get rid of all this. The pattern that goes off this into space goes perpendicular in every direction.
Wow.
So this is in a 3D view. It would basically form a donut.
Wow.
The radiation pattern looks like a donut.
Radiation patterns.
So the energy goes perpendicular to the axis of the wire. So that means that some of it goes up and some of it goes down. So if you were trying to talk to somebody far away, the stuff that goes straight up into the air doesn't do you a whole lot of good, right? Because it just shoots up into space. Stuff that goes straight into the ground doesn't do you a whole lot of good. It's the stuff that goes this way along horizontal or parallel to the earth in both directions. So because it's shaped like a donut, how much of it goes this way in the direction of the wire?
It doesn't.
None.
Nothing. Yes. So this is actually a somewhat directional antenna.
I'd say bidirectional, maybe, or
yeah, it favors perpendicular to it. So
a
in order to
dipole antenna will be better in a horizontal position.
yes, well, not always. If it's rotatable or you have multiple ones, yes. So the next step, of course, is we can take this antenna and instead we can do this with it. If we can feed it, we can make a half wave long. What direction will that radiate if it's vertical now?
Oh, it's going to be horizontal.
Yeah, it's going to be horizontal. And that actually is going to be very beneficial for signals traveling along the horizon. Now, the difficulty here, of course, is that you somehow have to put energy into it. So there is, now that we've established that this is a good antenna, the dipole is a good antenna, we have to worry about how we get energy into it. This brings in something called a feed line. So what is the current at the end of the antenna, everyone?
Zero.
Okay, what if I tried to put current and energy in at the end of the antenna? And I know that the current at the end is practically zero. It's going to fight really hard against me doing that, isn't it?
Right.
Okay. This is actually known as an end-fed antenna.
So you're saying if you put current at the end of the antenna on the left-hand side, as I'm looking at it, you're saying that
its impedance, at this point is going to be very, 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 very high because there's not supposed to be current at the end. And if you're somehow managing to go a little bit away from the end, your curve looks like this. So you're trying to stuff current into the antenna at that point, so close to the end. And what's the Ohm's law again?
E equals I times R.
Yeah, or in this case Z, because we're dealing with impedance. And if the Z is very high because you're trying to feed it toward the end, and you have, well, you don't actually have low current, you have modest current. you're actually going to have a really high voltage at that point.
So
you
when you
have to
say
have,
you're going to try to feed it towards the end, and the end meaning, just so I understand what you mean by the end.
like literally the end of the antenna. It's a half wavelength long.
Okay.
You're trying to feed power into it where the current has to be really low. And the way to do that is that your voltage has to be really high.
I got you.
Power is power, right? P is equal to I times E.
I see.
I mean, we can't violate the laws of physics, unfortunately. So what that
Okay,
means
so here's
is,
a question.
yeah,
If you move that feed to the middle of the line,
yes,
that means that it's lower. Okay. I
yes.
just wanted
And
to
in
make
fact,
sure I was thinking right.
that is the easy way to feed this antenna. The impedance at the center, because of the voltage and the current, is approximately 72 ohms. That makes it very easy to feed. And in fact, you can hook that up to 75 ohm coax. You could actually hook it up to 50 ohm coaxial cable and be able to feed power into it. And
So
that
you're saying
becomes
it should put the feed physically in the center of the antenna as opposed to the end. Is that correct?
Yep.
Oh, that's
Now,
interesting.
that is not saying that some people don't build end-fed antennas. There's lots of end-fed antennas. But the problem then becomes, if you're going to do that, how do you get power into it? Because if you don't get power into it, it can't get radiated, right? Because current flowing back and forth is how an antenna radiates energy into the world. If you can't get power into it, if you can't transfer power in, you can't get power out. So what this typically is this is about 2000 ohms right here. If you were to hook up, and we're getting to SWR in a little while, if you were to try to hook up a 50 ohm coaxial cable to it, you would have a severe mismatch right there, and you would transfer almost no energy into it. That being said, there is a way to do this. Instead of using that directly, you would actually do this. Tell me if you recognize this.
Transformer.
Is that your Ballon transformer?
That is actually an impedance matching transformer, which is functioning as a Ballon also, and it's attached very close to the end.
So
and
question.
the turns ratio is such that you'd have like 50 ohms in and 2500 ohms out
Wow.
because of the turns ratio. Yeah, go ahead.
Thank you. So I have a tram 18-foot vertical antenna, and it has the adjusting rings down on the bottom. Am I to assume then that that is a end fed, and that the adjusting rings are acting
It
to
depends
tune
what
the
when
antenna?
you say I mean, what frequency is it designed for?
It's a design for 11 meter and 10 meter.
Okay. Okay, well, you tell me. Here we go. Let's figure out what it is. It's how long?
18 foot.
Okay. So let's assume that it's cut for 28 megahertz. Okay. Let's do our calculations. 300 F lambda. Okay. Our frequency is 28. 300 divided by 28 gives us about 10.5 meters. Okay. Multiply that by 3.3 to get feet. That gives us about 35 feet. Okay. So here's the other thing. When you're building an antenna, you have to intentionally shorten it by 5% to make it work in the real world. The theoretical calculation will always be too long. So that would mean that it is roughly 17.5 feet for a half wave, because we just calculated a full wave at 28 megahertz. And this now becomes 17.5 feet for a half wave. And we want to take 95% of it. So that would be about 17 feet long. And that would be a half wave at 28 megahertz. So you're basically taking a vertical that is roughly a half wave long and you're feeding it at the end. So, Misael, what do you
Yes.
think?
Well, the math is matching. I
Yep.
mean,
That's the math.
definitely that.
You can't argue with the math. The math
but
is
now,
saying
with your previous illustration with regards to the tuning, since this is an end-fed antenna,
yep.
The tram model that I have has adjusting rings so that you could, I guess, fine tune at the antenna base.
I would think so, yeah. And there's also probably an impedance matching network right here in the base, which is, I assume it hooks up to 50 ohm coax.
50 ohms, yes.
Right. The feed point of this antenna is going to be like, probably 2K ohms. So that's how they achieve that. And then the fact that it's adjustable is just for fine tuning of what you may need. It but may add a little capacitance to it, or may add a little length to it, just for fine tuning.
Thank you for taking the time to show me that. I appreciate it.
So, all right. So now actually this brings up the quarter wave. So we now have a half wave antenna, right? This is a half wave dipole. And again, the way to calculate this is figure out theoretical length, and then figure out a half wave, and then take 95% of it, and that gives you the length. And again, the 95% is because of the real world. It couples with things, it couples with itself, it couples with trees. It's always a little bit too long. And the other thing is, if it's PVC coated wire, it actually ends up being a little bit shorter than if it's just metal. The PVC actually slows down the travel of radio frequency energy. It changes the wavelength by a few percent. So, okay, so now this is a half wave dipole. And what we're going to do is we're going to take this half wave dipole and we're going to cut it in half. Remember, we said the feed point at a half wave dipole was about 72 ohms. Now we're going to cut it in half and take this bottom part and make it disappear. But instead, what we're going to do is this. Ooh, don't know what happened there. Oh, come on. Didn't like what I did, I guess. There we go. We're going to take this and mount that to a plate, for instance.
Okay.
And this other one is going to be on a magnet or something, and we're going to feed our coax, or feed our cable right there. And now this is now a quarter wave antenna. This is a quarter wavelength long. And we've now, let's say, put a magnet on the roof of our car. The bottom side of the antenna, the other half of the antenna, is actually, there's actually a little piece of rubber or plastic or something there. The energy is capacitively coupled to the roof of the car. The other half of the antenna is actually a projection of the top half. So if this thing on top is a quarter wave, what's the other part that's a projection of it?
Quarter wave?
Quarter wave. Well, what does that look like now?
Half wave?
That looks like a half wave center fed antenna. Except that the feed point impedance is now only 36 ohms because the other part isn't actually real. But here's what's really cool about this. Let's say that I'm way over here and I'm looking at this antenna, and I don't know that this is a perfectly reflective ground plane, right? I don't see it. So I'm going to erase it. Okay, as far as I'm concerned, if I'm looking from far away, what do I see?
Just the top part of the antenna, which is a quarter wave.
No, I see the reflection.
Dipole antenna.
I see the reflection in the bottom.
Oh.
So like a mirrored reflection, like visually, like it's
Except that it's a radio reflection.
Gotcha.
But it looks to the rest of the world like the whole antenna is actually there. That's
wow.
That's a ground plane, and that's a quarter wave ground plane antenna.
So
So
you're basically illustrating this here, which is my GMRS
yes,
mono.
yeah. So now that we have a quarter wave ground plane antenna, the question is, why does everybody use a quarter wave ground plane antenna if it's really only half a dipole? What do you think?
Convenience?
What do you think? Yeah, very convenient. What else?
Mobility.
Yep, mobility. That goes into convenience. What else?
Cheaper.
A little bit, but what else? Something that's really important.
The angular radiation.
Very good. What else?
Propagation.
Height restriction.
Wait, I heard propagation. What about it?
I'm not sure. It's kind of a guess because I'm just a little bit over my head here, but I'm assuming it's propagation because.
Which direction does it go?
Well, it's going downward, I think, right?
No,
No,
remember this is a dipole.
I mean, the one you,
Radiates
I'm sorry.
horizontally.
It's like a degree of about 45 or
Radiates
upward?
horizontally. In what direction is preferred?
Oh, okay. It's going out. It's going out.
It's omni. It's an omnidirectional antenna.
Oh, crap.
When viewed from above, if I were looking at the roof of a car and here's the antenna, which direction is it going to be preferred? Which direction is going to work best?
It's going in both directions.
It's going in all directions.
All directions.
Which means that it doesn't matter where I am or how the car is oriented. It's going to have equal performance in all directions. And since most VHF, UHF repeater stations are on top of towers, looking at them from above, they look like this. Here's the tower with an antenna on top. Which direction do those send out signals?
Everywhere.
Everywhere. Omnidirectional, which means that these are ideal for one mobile station talking to another or one mobile station talking to a repeater station somewhere. That's the big reason that we use vertical antennas on cars. The quarter wave just makes it really, really convenient because it's really short. So what we're going to do now is figure out what a quarter wave 2-meter antenna is, how long it's supposed to be. So we're going to cut it for 146 megahertz. Okay, what's the formula? Where do I start? Somebody tell me, what do I start?
6 over 300.
300.
300
Divided by 46.
F and lambda.
Yeah.
Okay.
So
And I want to know my wavelength. So what is it? 300 divided by 146?
146.
Which is?
2.5.
Yeah, 2.0 something.
2.05.
2.05 meters. Okay, and we want a quarter wave. How long is a quarter wave?
Half that.
So a quarter of that, so 0.51 meters. And then we want to shorten it by 5%. That's about 0.49 meters. And we want to convert that to inches so we can use it in the United States. And that's about 19.5 inches tall. That's how big our quarter wave antenna is. It's about 19.5 inches. I built a whole bunch of them in my life.
Wow.
There you go. So now what we've done is we have actually converted. Remember where we started today? We started on this, right? Waves traveling through space. And where have we now gotten? We are cutting antennas to length to work at a particular frequency. Neela. Neela, your hand's up.
Hi, thanks. I had to find the unmute. So if I'm going to use this on my bike instead of my car, it needs to be twice as long because I don't have a reflective plane.
No, what's the bike made of? Aluminum
Metal,
or steel?
but it's not flat.
It doesn't have to be. So okay, here's a really interesting thing. All right. So what is it steel or aluminum?
Steel.
Steel frame? Okay. That means if you have any spot that's kind of flat, you could actually use a mag mount or you could clamp something to it because the mag mount is going to capacitively couple by the design of the base. And it's going to use the bicycle as the ground plane. I know lots of
Oh, so
people
it
who've done
doesn't
that.
have to actually be a plane.
No. It's here. Okay, so ready? I'm going to show you an antenna here. Has everybody ever seen a handheld radio?
Yes.
Yes.
That looks like this. I'm holding it up to on my picture. Okay. So this has ideally how long on, let's say, the 2-meter band. On the 2-meter band, how long is a quarter wave antenna going to be?
19.
19 inches and change. Okay. How long is the quarter wave antenna on my radio?
Less
This
than
is
half.
that's 7 inches long.
Yeah.
Okay. How do they do that?
A coil base.
Can everybody see this?
The attenuators or something? No.
No, it's coiled up.
Oh, coiled up.
Coiled
Okay, I'm
base.
sorry.
Yeah.
This is loaded, and the entire length of the antenna is wire that's 19 inches long, but it's wound in a big coil.
Oh, I see.
Which means that at some point there has to be some capacitance added to compensate for it, which there probably is to cancel it out at a given frequency. But instead of 19 inches long, it's now physically only 7 inches long. So what do you
We
give
cannot
up?
actually see you because the whiteboard is on.
Oh, okay. Let's see. There we go. Okay, I'm going to hold it up. Okay, everybody see?
Yep.
Okay, so there's my radio there's probably a capacitor added somewhere in there to cancel out some of the inductance because the entire length of this is actually coiled up. So what you gain by doing that is flexibility because it's all a big coil. It's not a straight piece of wire. It's also not 19 inches long, so you don't jab yourself in the armpit. What do you lose by doing that?
Oh, I'm sorry. What do you lose by doing what? I'm sorry.
By having it coiled up. What do you lose?
Distance.
Sensitivity.
You lose gain.
Oh,
Your gain goes down considerably. So why do we do that? What's the benefit in doing this?
Matching?
No, it's 50 ohms. That's fine.
Shortens the antenna.
Yeah, it makes it a lot more convenient, right? Like you can take that antenna and if you want to coil it up tighter, you can coil it up like this. So it's only 3 inches long. It's not going to work very well, but let's say that the station you're trying to talk to is like a half a mile away. And compared to a 19-inch antenna, your gain is -6 dB, and this one is -12 dB. Well, there's still probably plenty of signal available to get heard, in which case it becomes a trade-off. If you go out into the woods, probably neither of those antennas is going to work anymore because you're now far away from the people you're trying to talk to. And maybe even the original antenna doesn't work. So you remove this and instead you hook it up to a piece of cable and you bring along a handheld 5-element Yagi antenna, which has a gain instead of being 0 dB of, let's say, 10 dB. And your handheld radio now can talk to somebody 20 miles away in one direction because of the antenna that you pick. That's why you're taking this class, everybody. This is about learning how radio systems work.
You talk a little bit about how a home antenna of a vertical work.
Well, it depends on the vertical. I mean, like
let's say a 40-meter vertical. Well, that'd be a pretty tall antenna. If it was,
that's a pretty tall antenna.
Yeah.
We'll go with this. We'll just go with this 2-meter vertical. That's what I have on my roof.
And about how far will that broadcast?
Depends where you are. And by the way, we don't broadcast.
Transmit.
Yeah,
Fair
we
enough.
transmit. Yeah.
How many miles can you transmit from your house to
It
whatever?
depends where you are.
Right where you're at right now.
40 miles.
That sounds good.
Of course, I live 450 feet up on a hill.
As
right?
opposed to down in a ravine.
As opposed to down in a ravine or down in the flats, or I mean, Elevation is king when dealing with line of sight. Elevation is king. That's
What
why
if you
people,
want to talk to another country?
well, then it's still, you still can't beat it.
Oh,
Being up higher is always better.
yeah, that's what Art said.
Always. So, all right. So now we've designed and built antennas. Isn't that cool? We've actually designed and built antennas.
Hmm.
Okay. How do you lower the resonant frequency of an antenna? How do you lower the frequency of something? What do you do to it?
Increase in length.
You make it bigger. Yep. Okay. So how do you raise the frequency of something?
Shorten it.
Smaller.
Okay. So when you're building an antenna for the first time, what do you always do?
Start longer.
Start longer because
You have to find, you gotta adjust for the frequency.
it's a
You
lot
can always
easier.
trim. You
That's
can always
right.
trim off, but you can't put on.
You can put on, but it's challenging. You might end up soldering something on. It's a lot easier to cut it shorter. Much easier. Okay, a beam antenna. A beam antenna is a directional antenna that looks like this, that puts out a signal in that favors one direction. So this feed on a Yagi antenna right there. Can anybody guess what kind of antenna this is right there in the middle of the Yagi antenna?
A
Dipole?
Yeah, I bet it's a half wave dipole. And in fact, it is. That's the driven element of a Yagi antenna. This is known as the reflector, which is slightly longer, usually 5% or so. And these are known as directors. The more directors you add, the better the gain. And what is gain? How do you measure it?
Decibels.
What units?
Decibels.
In decibels, exactly. Okay. And in fact, the more gain you have in the forward direction, this is actually measured with regard usually to what a dipole will do. And since a dipole makes a bidirectional pattern that goes in the shape of a donut, what you typically do is you look at this pattern and compare its peak to the dipole's peak. That gives you the gain. There's also something called half power points. This defines what the antenna's beam width is. And half power, how many decibels is half power?
2. I mean 3.
3 decibels. So if we assume that this is our peak, this is our 0 dB mark, we look for the point that our signal is 3 decibels lower and 3 decibels lower, and this gives us our antenna beam width. See, I told you decibels were going to be really important. And then we also have something called front to back ratio. So here's our peak front power. And we also have a little signal that still comes off the back. What do you think the front to back ratio is, and what's it measured in?
3 dB.
No, what is it? I mean, what's it a measure of? Front to back. What do you think?
Reflection?
Yeah, amount of power going forward versus
The amount of power going
the amount of power going backwards, and it's measured in what units? Come on, what units?
Watts.
No, everything's measured if it's a one thing compared to another. It's always measured in
ratio. dB.
decibels. Everything is decibels.
Decibels.
There's also something called a front to side ratio, because there's a little signal that comes off the sides. Any idea what units that's measured in?
Decibels.
Notice I'm asking you the same thing over and over. There's a reason for that. It's measured in decibels. Everything is measured in decibels. And in fact, let's go to an antenna manufacturer's page. 13B2. Okay, let's take a look at this. Here we go. I'm gonna share this instead. We're gonna take a look at a sample Yagi antenna. Notice this 2-meter broadband boomer beam antenna. That's a 13 element antenna. And let's take a look at specifications. Okay, everybody. So what do we have? We have our peak power rating and somewhere in here. Oh, look at this. Beam antenna gain. What's it measured in?
Decibels.
And in fact, it's dBi, which is compared to an isotropic radiator. To get compared to a dipole, you actually have to subtract 2.15. Just because there's no such thing as an isotropic radiator. It's a way that manufacturers can make their antennas look better. Front to back ratio?
Decibels.
Decibels. And what does it mean if it's 26 dB? How do we convert that to something useful? Here we go.
With our.
Here we go. Hopefully. Okay, we're going to erase this.
Would that give you the length of the radials?
No. But what we're going to do is say it's 26 dB. That's our front to back ratio, right? Okay. Split that into tens and threes.
So
Oh.
10.
10 plus
20, a 10
plus
3 and
Yep.
3.
Okay. So every 10 dB, we have 10 times.
10.
And every 3 dB, we get how many times?
2.5.
2.
Or is it 2? Sorry.
Okay. So what's 10 times 10 times 2 times 2?
It says 100. 100 times 2 is 200. 200 times 400.
Okay. So that means if we get 400 watts in the forward direction, how much power is going in the backward direction?
400 watts?
No, we have 400 times. If we have 400 watts in the forward direction, how much do we get going backward?
What does it say?
1 watt.
Oh, I'm
It's a really good antenna, isn't it? That's a really good antenna. In other words, if we put in 400 watts going forward, if we manage to put in 401, we'll get 400 going forward and 1 watt going backward. And remember, what was the base antenna? What's the basic antenna that's in that design?
The dipole.
It's just a dipole, which puts out half its power forward and half its power backward. Just by doing what they did and adding all those elements, they made it, instead of 1 to 1, it's now 400 to 1. It's a pretty good design.
So question.
Yep.
Let's say we have a 10-meter radio that's putting in the output of 5 watts.
Okay.
And 50 ohm cable. So at the dipole, it's getting 5 watts. So then from 5 watts, then I use that math that you showed us, and now tell me what the true forward output would be.
Mm-hmm.
Okay.
And actually that's called EIRP.
EARP?
EIRP. Or or ERP, effective radiated power.
Effective radiated power.
So yeah, let's say that let's say that you have an antenna, and we're spending a lot of time on antennas, but I'm good with that. I love antennas. Because you know what's cool about antennas? You can build this stuff out of your junk box. I'm serious. It's just aluminum bar stock. You can build all this stuff. This is physical construction projects.
Like my friend had his father, they had an antenna that was like it was like a 50 or 100 foot tower. And I guess they were talking people all around the world, but they had it super high.
I built my own dipoles. They've been up in my trees. So, okay. So now let's say that you have like that same antenna and you have, let's say it's a 400 to 1, right? Actually that was front to back. And the gain was the gain was what was it, 15 dB? But that was 2.15 less than that is 13. It was 15.6. So it's roughly 13 dB compared to a dipole. All right. So it's roughly 13 dB. So that's 10 plus 3. The 10 gives you 10 times. The 3 dB gives you 2 times. Is 20 times. Everyone agree with that?
Yep.
Okay. So that means if I hook this up to a 5-watt radio, what is my effective radiated power in the forward direction? It's 5 watts times 20.
125.
100 watts.
Oh.
So it's better to have a good antenna than having to spend the money on a amplifier.
Hell yeah. I tell that to everybody. This is your amplifier is the last thing you ever do. It requires more power. It requires better feed line. It requires bigger antennas. Sometimes it requires you change your electrical service in your room.
Wow.
I mean, amplifier is the absolute last thing you do after you've done everything else.
Wow. Okay.
Last thing. Okay. Next thing. Let's see. I think we've beaten antennas to death. Okay. Disadvantage for using a handheld transceiver inside a car. Why would you not want to do that?
Because the frame of the car acts like a Faraday
Because
cage.
you're getting a shielding from the car itself, but
That's right.
And, you know,
Basically, it's a metal box.
yeah, you don't want that.
Now a 5/8 wave antenna, typically a longer antenna is going to do better than a shorter one. So a 5/8 wave antenna is better than a quarter wave antenna. It's a lot longer, but it has a lower angle of radiation and it's more efficient. Okay, feed lines. Feed lines are really important because once you've designed an antenna, once you've installed an antenna, what do you have to do with it?
Well, you gotta match it.
You got to get power to it, right? If you don't get power to it, you can't do anything. So, okay, so we have to figure out a way to get our power up to it. So feed lines and connectors. So coaxial cable is really nice because it's everywhere. It's really pretty cheap. It's really easy to handle. So long as it's UV resistant, you can put it outside. If it's water resistant, you can bury it.
If you could, I mean, I used to work for some programs where we use bias T connectors and stuff like that.
I do not know.
Okay.
I think it's probably impedance matching, but I'm not sure.
Yeah.
Okay, we did impedance. That's AC. It's measured in ohms. Most common impedance of cable used in radio is 50 ohms. Some people use 75 ohms just because there's so much TV cable out there, and that's all 75 ohms. I know people because you can very often get it for free, and it works just about as well. Okay, this is a very important thing to note. What happens as the frequency of a signal in coaxial cable is increased, the loss goes up. The bigger the cable, the lower the loss. And as a general rule, teeny tiny cable is going to be much lossier than big cable at a given frequency. And as frequency goes up, the problem gets worse and worse. So let's say that you have, this is, for instance, this is RG58. This is your standard stuff that I'm able to slam in my car door. And I'm going to stop sharing. Everybody see that RG58?
Yep.
Okay. Cable loss chart. Okay. These kinds of things will answer all your questions. It is really important to know that these things exist. Let me open this up. Hope that it works. Come on. Give me 1 second here. Okay, there we go. Let me go there. Stack Exchange. Come on. Just when you think you're in the right spot, you're not. Sorry, give me a second here. Okay, there we go. coming up. Okay, here we go. There's our table. Okay. Everybody see that?
Yep.
I hope.
Yes.
Okay. RG58 is the stuff that you're able to slam in your car door, right? Notice that at 3.5 megahertz, which is our 80-meter band, the loss measured per 100 feet is less than a decibel. Okay. Really important to note. What is 3 dB? How much of your power?
It's 2.
50%. That's right. Okay. So if I were to go to, let's say, RG58 and go to 50 megahertz, what is my loss at that frequency?
Half.
I'd lose, in other words, half my power in 100 feet of cable. If I go up to 2 meters, the 144 megahertz band, how much power gets lost? 5.5 dB. Which means 3 dB is how much?
Half.
2x.
Okay, 3 dB is half. And then I have another 2.5 dB, which is almost 3 dB. So of the half that I lost, then I lose a half of what's left because it's a 5.5 dB loss. So how much power have I now lost?
3/4.
3/4 of it. In other words, I put in 10 watts. I have 2.5 watts coming out in 100 feet of cable. Where's the rest of it go? Where'd the rest of it go?
The cable?
It's lost in impedance.
Nope. Impedance doesn't exist. Impedance has no impact on that. Where did
Okay.
where did it go?
Heat.
Heat. It turns into heat. So basically, I'm using that other 7.5 watts to heat my cable.
Huh.
Right? It's not putting out any power at all. Okay,
Well,
so
at least it
now,
won't freeze.
oh, hopefully. So now let's go and change that to LMR 400, LMR 200, which is a bigger cable. What is my loss now at 144 megahertz at 2.95? Or sorry, at 144 megs, it's right around 3 dB. So by changing to a different cable, I went from 25% power transmission to about 50. That's a lot better. If I go to LMR 400, I'm now down to 1.5 dB. That's a lot better. Notice that it gets even worse if you're at 440 megahertz, right? So that's squarely in the UHF band. RG58, you'll lose 10 dB of your signal in 100 feet. 10 dB is what?
10 times.
10 times or 1/10. So I will lose 90% of my signal as heat in 100 feet of cable if I use RG58. If I go to LMR 400, it's down to 3 dB, which is not great, but it's a heck of a lot better. So these problems, the higher the frequency you go, become worse and worse and worse and worse. The problem is really exacerbated. So if I have, let's say, a 10-foot run, I don't care what I'm using. It's going to be fine. But when you start getting long cable runs, you start getting into trouble. For instance, like I could do 100 feet at 3 megahertz with anything, and it will still be pretty much okay. If I change that from 3 megahertz to something a lot higher, then my problem becomes a lot more severe. So that's why.
Is there a time that you're restricted to using a smaller cable, and is there a way of getting around that by using amplifiers in between or something like that?
You could. What if I want to slam it in my car door?
Yeah.
I can't use a big cable in between.
Well, that's true. Yeah.
You know, what if I want and actually I can transition from a big cable to a small cable. I mean, if you're talking a power amplifier, no, you typically don't want to include a power amplifier. I mean, you could use a mast mounted power amplifier, like way up on the tower, but then it's got to be waterproof. So everything's a compromise.
Yeah, that's a good point.
Everything is a compromise. Okay, let's see what's next.
Quick question.
Yes.
So I have a GMRS radio operating at the 462 and 467 megahertz.
Yep.
I'm using KMR 400 cable 100 feet.
That's probably like an LMR 400.
Okay. So can we
That's decent
calculate
cable.
to see what my loss would be, just so that I could have a real life example?
Well, I'm not sure what KMR 400 is, and you'd really just KMR 400 versus LMR. KMR 400 is similar to an LMR 400. So they are similar, and when you buy the cable, it will typically tell you what you are getting loss wise. Let's see if this does. KMR 400. Ultra low loss. Yeah, it's similar to LMR 400. So you could safely use the LMR 400 loss calculations on that. You could get away with that. And it's going to be about 3 dB.
So a 3 dB gain, let's say on my output is 50 watts.
Yep.
50 watts, and I have a 3 dB loss on the cable.
Mm-hmm. So your ERP is going to be half of the 50.
So I'm putting out 25.
You're putting out 25 watts.
Wow.
Which is actually not bad. That's actually not bad. I mean, that's good. Without going with hardline, that's the best stuff you could use.
That's interesting.
Yeah, that's
yeah, and I'm using a Unity antenna, a tram Unity antenna for the GMRS, but I'm thinking now, well, maybe I should get something with a higher decibel.
A little bit of gain. Yeah, you could use a little bit of gain.
Yeah. Wow.
Again,
okay, I'm learning.
everything's a compromise.
Yep.
Yep. Okay. Let's see. RG58 and RG213. 213 is better cable, has lower loss. Hardline, air insulated hardline is literally so I'm going to draw a coaxial cable here. This is actually really important for those who haven't seen it before.
Is that Heliax cable? I guess
It's a Heliax is a type of air insulated line. Yeah.
Yeah.
Okay.
Right.
So this is a transmission line right here. That's a feed line or transmission line. 2 parallel wires. They have space in between them. And each one is a conductor, which means they have inductance. They have self-inductance. They have mutual inductance. Because they're parallel wires, they have capacitance. Well, as it turns out, you can actually draw and model a piece of cable like this, a transmission line. An infinite string of these. And each section has a characteristic impedance associated with it. So that is altered by the distance and the type of wire that's used and the gauge of wire that's used and the proportions of everything. So you can have a cable that's this big, for instance, a coaxial cable that has a shield right here and a center conductor. And this has a characteristic impedance of 50 ohms, or you can have one that looks like this. So long as the proportions are the same, this can also be 50 ohms. Now, of those two that I just drew, which one do you think is going to be less lossy and more efficient?
The larger one.
The big one. The big one is always better than the small one. And what's interesting is that they both have a characteristic impedance of 50 ohms. Notice I didn't say an impedance. It's a characteristic impedance. That doesn't cause power losses. What causes power losses, I mean, that does cause power losses at higher frequencies. But what causes power losses are ohmic losses. The ohmic losses are resistive losses that are caused by the gauges of the wire that are used. So a fat wire is going to have less ohmic loss than a narrow wire, which means it's going to be less lossy. You're going to lose less energy as heat. That's why we do that. Okay. So let's see. Okay, air insulated hardline, that space in between the conductors is just air. What destroys hardline? What destroys cable? Water. Water causes corrosion. Corrosion makes essentially a rusted coaxial cable, and it doesn't work anymore. If you get water intrusion because you didn't seal it properly, that'll destroy your cable and it won't work anymore. If you have connectors that aren't waterproof properly, same thing. You have cable that is buried but isn't water resistant, same thing. You have cable that isn't ultraviolet resistant and you strap it to the side of your house, it cracks. Once it cracks, you get water. Water destroys the cable. The answer to everything is water in coaxial cable, very, very bad.
Yeah.
That's one of the issues with air insulated stuff, because it doesn't have like nylon or polyethylene to fill the space. It's filled with air. So because it's filled with air, there's room for moist air to get in, especially if you live in some place with a lot of humidity.
So how do you protect the connectors and things of that nature from corrosion?
Lots and lots of rubber mastic and sealing tape.
Oh, I see.
In fact, I once did a connector on the back of my car, and after 11 years of riding around in the rain and the snow and salted roads and everything, when I took it all apart, that was the cleanest part of the whole installation, was what was under the tape. So it pays to really waterproof it.
Question about with the connections, can you pack them with dielectric grease to prevent moisture intrusion?
I mean, I typically don't.
Okay.
But I mean, it depends. It depends. I guess you could, but at the same point, you don't want to, make it so that it's not, not a solid connection anymore.
Okay, understood.
So,
Thank you.
Yeah. Typically, I use like 3M makes a whole line of self-vulcanizing mastic tape.
Yeah, I've used that before. That's good stuff.
It works very well.
Yeah.
Let's see. Air core, you typically have to pressurize it with dry nitrogen to make sure it doesn't leak. But let's say you've got 1,000-foot tower and your transmitter is most people don't have 1,000-foot tower, but if you run a repeater, you might. And your antenna is way at the top and your transmitter is way at the bottom, and you have let's say 100-watt transmitter and you really don't want to waste your power. Maybe you do go out and get coaxial cable that's 4 inches in diameter that has really, really low loss. But then you also have to pressurize it with dry nitrogen to make sure you don't get any leaks. Okay, a PL259 connector. So I'm gonna bring up some connectors. PL259 is part of the UHF series. It was designed originally for use at UHF, except it turns out that it's not really very good for UHF. It's good for HF, and it looks kind of like, let me bring it up. It looks kind of like this. So this is a PL259 connector. Everybody who's done RF recognizes this. These have been around for 80 years or so. I believe they came out of like World War II. And these are, before there was a lot of really, really high frequency stuff, this is what everybody used. We still use it for HF and a little bit of VHF. For anything above that, we use N connectors.
Yep.
Or SMA connectors. An N connector, notice it's got a rubber gasket.
Yeah.
So that rubber gasket in there makes it water resistant, if not waterproof. It's also 2 shields. You've got the internal shield and the external shield, which is threaded. So it's a truly 50 ohm connector. Notice we also have this thing called an SMA connector, which is used at up to a couple of gigahertz. Yeah. Oh, I thought somebody got my attention there. Okay.
I gotta excuse myself for just 2 minutes. I gotta run downstairs a minute.
Okay. So, let's see. Actually, you know what? That's a good time to take a 5-minute break.
Hey, Scott,
Yes.
I really appreciate, I'm enjoying this class that you're throwing. I gotta get going.
Okay.
Um, look
Well-
forward to your email and the rest of it.
Yeah, it'll be out. It'll be out tonight. And
And then pick up again tomorrow. Is that what you're saying?
yep,
What time tomorrow?
9 o'clock. Well, same time as today.
Same time as today. All right. Thank you, sir.
But it's
Scott,
only a half day. So
Okay.
Scott, I got just one question real quick.
yeah.
I wanted to see what this is. What type of antenna is this? It's a flat one.
That is I think it's like it's sold under the name Abri.
A Brie, yeah, exactly.
And they I don't know why they call it this. They call it a tactical antenna, which it's really not. I mean, essentially it's a tape measure that's wrapped in like a heat shrink.
Yeah, it's not coiled. There's no way it could be coiled in there.
Right, but you do fold it and then you can unfold it. And
Yeah.
it's about 40 inches long, unfolded, if which makes it a roughly 5/8 wave antenna, which has a little bit more gain than a quarter wave.
Okay, so in the military, so I'm still in the military with the Florida State Guard. The small antenna that we had couldn't during the last hurricane. We couldn't talk to each other even on an open field. It was difficult, so they had us revert to this one, and that was where it doesn't seem like it's doing any better, not even with this game. So
Well, it depends. I mean, what distance you're trying to use simplex and over what kind of range and what kind of power levels.
well, just whatever we have 2 to 5 watts, so it's a small handheld. Um, it basically the antennas that we have, or the hurricane did damages to them to the areas around here, so we were just going basically bandwidth with the handhelds with the power that they've got on there. I mean, I think it's 5 watts. I don't know.
Well, I mean, part of it is that should have a lower angle of radiation,
Okay.
a little bit of gain, a little bit of extra gain. But a lot of it depends on terrain.
Okay. Yeah.
Depends on buildings in between you. I mean, it's
Okay.
that's why we try to use repeaters, because repeaters are typically going to be depending on where they are, they're going to
That's what
provide you
they
line of
said.
sight.
That's what they said. We should hook up to a repeater, but you need a technician license to get into that, right? To use a repeater.
Well, there are some GMRS repeaters, but beyond that, yeah.
Okay. All right. Thank you. Appreciate it.
All right, 5-minute break. We'll see you all in a couple. Other questions? Questions?
Regarding tactical antennas, the reason they call those Abri antennas tactical is because that was the standard antenna that was provided on the old backpack
Okay.
radios from the 60s into the 90s before Singars came out. So they were foldable, they were easily hideable. They didn't stick in your face unless you didn't fold them up with the right rubber band.
And I think you can actually use them kind of in a folded position.
You can, but yeah, they improve if you can pop them up. But obviously, when you're getting shot at, having an antenna sticking up out of the weeds is not your best plan.
Mm-hmm. All right, everybody ready to go? Anyone have any concerns? Questions? Okay, we're into standing wave ratio. Okay, we are into standing wave ratio and matching. Matching is like super important. Let's clear this whiteboard. Okay. So we start looking at an antenna. An antenna is that's going to look like this, is measured with an impedance in ohms. This is actually real ohms. So a dipole antenna is going to, let's say, be 72 ohms. And that's actually ideally something called radiation resistance, not impedance. The impedance is the same thing, but it's going to be real. If it's resistance, that means it's actually going to use power and use it to convert power that's running up the feed line into radiated power. Ideally, in order to do this, you're going to match your radiation resistance of your antenna or your impedance of your antenna with your cable impedance, your characteristic impedance. That optimizes your power transfer. Anytime you have a mismatch in the impedance between the two, what's going to happen is that, let's say that this is 50 ohms. You get up to a point where it's 72, you're going to have some power going out, and then you're going to have some that's reflected back. Well, what happens is that eventually the power that comes back gets back into your transmitter, and it has to go somewhere. Power has to go somewhere, right? So if your power is being transmitted right here, all that power that bounces back gets turned into heat, which causes your transmitter to get hot, which causes your transmitter to die, which you don't want to have happen. So what ends up happening at that point is that modern transmitters, in order to protect themselves, will do something called foldback, which is something that if they sense that there is an antenna mismatch somewhere in the system and there's power being sent back, they will reduce the amount of transmitted power so that the transmitter itself is not killed by the extra power that's bounced back. One thing that we can do to improve this is we can include a matching network somewhere. So we could put it right up here, something that would be a matching network that would match our whatever our antenna is to our feed line. So we can do that. We could also, if we don't so much care, we could include a little box down here. And this is an antenna tuner, which we drew before. And internally, it looks like this. Which is an adjustable impedance matching network that allows whatever is out in the world to look like 50 ohms. 50 ohms is your standard impedance that virtually all transmitters that are built look for. So the combination of what's outside, it makes it look like 50 ohms so that the transmitter is happy. Internally, there might be a really bad mismatch, which causes power to flow up and down the line many, many times. And every time it passes through that transmission line, what do you think happens to the transmission line?
Heats up.
It heats up. So if it's a really bad mismatch, you might be transmitting 5% of your transmitted power and burning off the other 95% as heat. But at least your transmitter will be happy, right? Your transmitter won't commit suicide. Essentially, all you're doing at that point is heating up your cable. So it pays to do your best to have a well-matched antenna system. Okay. The measure of how well matched our antenna system is known as standing wave ratio, or SWR. Standing wave ratio, ideally, if it's perfectly matched, is known as 1-to-1 because it's a ratio. So 1-to-1 match is a perfect match. If it gets up to 4-to-1, that could be, for instance, your feed line is 50 ohms and your antenna is 200 ohms. That would be a 4-to-1 mismatch. Similarly, a 50 ohm transmitter with a 12.5 ohm or 50 ohm feed line with a 12.5 ohm antenna would be a 4-to-1 mismatch. So either way, whether it's up or down, you basically divide the bigger one by the smaller one, and that tells you how bad your mismatch is. Ideally, you're aiming for 1-to-1. If you get up to 4-to-1, you have serious problems in your system and should probably take a look at them. A benefit of low SWR, reduced signal loss on transmit and receive. Transmit power that gets up into a feed line and bounces up and down and up and down and up and down turns into heat. Transmitters reduce power through something called foldback to protect the output amplifiers. And when you buy an SWR meter, you need to make sure that it can handle, let's say you're running a kilowatt, you don't want to use a 200 watt meter on it, a 200 watt antenna tuner, because it will fry. So it needs to be suitable for the power level and the frequency at which you're using it. SWR, a directional watt meter, that is how SWR is actually calculated. So you could actually use a directional watt meter and do the calculations yourself. It could, an RF power meter goes in line between the transmitter and the antenna. You want to know how much power is going out.
Excuse me.
You can use an antenna analyzer. An antenna analyzer, okay, for those of you who are going to join radio clubs, which I really hope is most everybody, what will happen is you will get to a point where you're not really sure what to do, let's say, on an antenna. And you will get to say, okay, well, I've got this antenna and I don't really know what's going on and I don't really understand it. Can anybody help? And somebody will bring along something like this. Come on. Somebody will bring along something like this because a lot of hams have these. If you're interested in RF, especially if you're interested in cables and building antennas, you have something like this. So this is an antenna analyzer, and what it allows you to do is, if you think about all the frequencies that we are allowed to use, there's a lot of frequencies that we're not allowed to use. But it may turn out that the antenna that you just built is actually working, but not where you expect it to, because you built it wrong. What this does, this is like a 1 milliwatt transmitter with a very sensitive receiver. It measures the amount of power going out and measures the amount of power going back. And because it's so low power, it allows you to sweep a huge range of frequencies legally. And what that allows you to do is basically get a big picture of what your antenna is doing at a wide range of frequencies and figure out how to fix it. You can also do cool stuff like figuring out if you've got a bad cable, it tells you where the break in your cable is through time delay reflectometry. So let's see, other stuff. So that's an antenna analyzer, incredibly useful tool. The major function of an antenna tuner is to match the antenna system impedance to the transceiver output impedance. All right, let's see how well everybody remembers. What's the typical output impedance of a transmitter today when you go and set something up?
75 ohm?
50 ohms.
Yeah.
50 ohms. Okay, the purpose of a dummy load, A dummy load is a phony antenna that is designed to convert RF energy into heat on purpose. The reason that you would do this is, let's say you built an amplifier and you just want to see what's happening when you're transmitting at 500 watts. You don't want to put it out on the air. Essentially, it's a non-inductive resistor. So like a carbon resistor. The reason it's non-inductive is because then it won't be 50 ohms anymore. It'll change the impedance. So it's a 50 ohm resistor mounted on a heat sink or in an oil bath, so that when you transmit into it, it just gets hot, and then everything else around it gets hot. I've actually got a kilowatt unit myself, which I've never come close to using up its capacity. Okay, so that is feed lines. All right, so we're going to skip amateur radio signals, and now we're going to see what they do when you actually shoot them off into the air. So let me make sure that we're on the right page. We're doing radio wave characteristics. Okay, we already know a lot of this stuff. And how it goes out into, okay, does everybody remember what the limits for HF are? I'm going to ask you this over and over.
300.
3 to 30.
3 to 30.
30.
VHF?
30 to 300.
And UHF?
300.
300, 3,000.
Yep, very good. Okay, I'm going to keep asking too. Okay, propagation modes. Here we go. Propagation is how radio frequency energy travels through space. So it could be along the ground, it could be up in the sky, it could be bounced around by the troposphere where we live through ducting. It could be bounced off the E layer, bounced off the F layer, and all these things probably don't mean a whole lot right now, right? So what we're going to do first is I'm going to share this whiteboard, and we're going to talk about a little bit of solar terrestrial physics. Okay, so there's this big, depending on where you live, this big glowing orb in the sky. Anyone know what it's called?
Sun.
The sun. Okay. No, it's the sun. Okay, it's the sun. All right. Name all of the things that are flying out of the sun.
X-ray, gamma ray.
Yep. Keep going.
UV.
UV. Anything else? IR. That's heat.
Solar flares.
Yep. Okay. So we have particles. Anything else? I'll give you a hint.
What is that?
Your
radiation.
color signals.
All the colors.
Visible light.
Yeah, visible light.
Oh, yeah.
RF. What does RF stand for again?
Radio
frequency.
frequency.
The sun is a big emitter of radio waves. Okay, so all this stuff is being blasted at us all the time by the sun. Well, that has good things and bad things about it. So we're going to get rid of the colors because we don't care. We're going to get rid of the gamma rays because we don't care. Infrared is great because it keeps us warm, but we don't care right now. The particles, that's great. They can make the aurora, but we're going to get rid of that. RF, we don't so much care about. So all we're going to leave is the ultraviolet and the X-rays. So we're going to put poor little Earth down here. There's our Earth. Okay. And around the Earth, we are surrounded by what?
Atmospheres.
Atmosphere. And what is the atmosphere largely made of?
Ion particles.
Nope.
And gases.
What kind of gases? Two main constituents.
Nitrogen.
Nitrogen and
oxygen.
Oxygen. Okay. Those make up 99% of our atmosphere. 78% nitrogen, 21% oxygen. So what happens is that we are really fortunate in a lot of ways, because all the X-rays and all the UV rays that come out of the sun that are directed toward Earth, of all of those, most of them never make it to the surface, which is really good that most of them never make it to the surface, because if they did, they would sterilize our planet and we would cease to exist. So be happy about that. They don't make it down to Earth for the most part. In order to do that, what happens is they penetrate a certain distance into the atmosphere, And on their path, what happens is that you end up with the nucleus of atoms and the electrons. And if we are lucky, what happens is that you get an X-ray or a gamma ray or a UV ray that strikes one of these electrons in one of these atoms and causes it to ionize by stripping off an electron and transferring its energy. So then we end up with a positively charged ion and a negatively charged electron, and we have done away, at least temporarily, with the damaging ultraviolet or X-rays. So our atmosphere works as a filter for us and keeps us alive. As a happy side note, we are also treated to the fact that we end up with all this ionization that takes place throughout the atmosphere. We have essentially 3.5 layers of atmosphere in the ionosphere. So we have the troposphere where we live, and we have the stratosphere where we fly airplanes. And then above that, we basically have the ionosphere. And at about 50 miles up, we have a layer called the D layer. And then about 100 miles up, we have the E layer. And then we have the F1 and F2 layers. And that extends from about 250 miles up to the edge of space at about 600 miles. The D layer is a very dense layer because it's really, really low. It's only 50 miles up. What happens is that layer builds up very, very thickly during the day. And what happens then is that the radio waves up to about 10 megahertz that are aimed at space hit that layer and are absorbed, which basically means that those frequencies up to about 10 megahertz are absorbed during the daylight hours. So if you ever wondered why you couldn't hear your distant AM radio stations in your car during the day, that's why. Because the waves that would normally go up into the higher atmospheric layers at night, they're not able to make it through the D layer during the day.
Wow.
The E layer is largely it gives us something called sporadic E, which is useful for VHF frequencies. It's very sporadic. It's still unclear as to exactly why it even happens. So we kind of ignore the E layer, although it makes for some very interesting propagation. The F layers are where the long distance communications take place. We have something called the maximum usable frequency. And what ends up happening is that we end up with because the atmosphere up there is really thin, we end up with electrons floating around up there. And because the atmosphere is so thin and the density of atoms is very, very, very low, we end up with electrons that get stripped off of atoms, and then we end up with like an oxygen atom that's ionized, and another one. And during the day, when we're exposed to direct sunlight, we get a higher concentration of them. At night, they occasionally will bump into each other, so we get a collapsing of that layer. And what ends up happening is that during the day, the higher concentration it leads to a higher ability for us to bounce higher frequencies and refract them down to Earth. At night, as that layer dissipates, the frequencies at which we can use that particular mode tend to go lower. So higher frequencies. So if we were to share that, let me see if I still have it up. I do. So for instance, during the day, 10 meters, 12 meters, 15 meters, 17 meters work really well. But when the sun goes down, then you're in the realm of 20, 30, 40. During the winter, 80 meters, 160 meters, because we don't have as much ionizing radiation coming in because of the seasonal effects. So we get a change from day to night, and we get a change from season to season. We also go through this thing called the sunspot cycle. And was anyone lucky enough to see the aurora back in May?
No, I wish I did.
It was really cool. Well, the aurora was caused by an incredibly high amount of solar activity. and the Earth was basically blasted by a lot of particles, which came out of the peak of the 11-year sunspot cycle. We as hams are very interested in this because when we get to the peak, we get a lot of ionizing radiation during the day. We also, unfortunately, get a lot of solar storms, a lot of geomagnetic storms, which make things kind of a nightmare to deal with. So it makes for some very interesting times. Okay, so what we end up with is we have a thing called skywave. Skywave is a signal that goes up into the sky and refracts back down. The highest frequency that we can use at any given time is known as the MUF, or maximum usable frequency. And again, that's going to be higher during the daytime and higher during sunspot peaks, and lower at night and lower during sunspot lulls. And that's an 11-year cycle. And those are typically on the HF bands. Above that, for instance, we end up with on VHF and UHF, for the most part, those signals will pass straight through into space. The atmosphere is largely transparent to those. So this is for VHF and UHF. So what do you think we use those for? If they pass
in the space program.
Space program. Yep. Satellites. Because actually, and as it turns out, VHF and UHF, because there's so much more bandwidth available up there, we can put up some very high bandwidth satellites too. And it passes right through. So if you want to talk to the International Space Station, that's how you talk to the ISS. I did that about 2 years ago. It was very exciting. Let's see. Down on Earth, so we're going to erase this one. Down on the surface of the Earth, we have an antenna system, for instance, and I'm going to hold up a beam. Look, it looks like that. And here's my handheld radio, and I'm talking through it. Eventually, what's going to happen is that unless you believe in the flat Earth, the Earth is curved. And what will happen is that our radio signals will hug the Earth slightly, because the Earth looks a little bit less curved to radio waves than it does to light, because its wavelength is so much longer. So they will follow along the radio horizon out to a certain distance, at which point they will no longer be able to follow. We can also aim them up at the sky, again, talking to astronauts. Once in a while, we'll get enhancement in the E layer, at which point the E layer will become refractive and bounce signals back down. And that will, instead of being 2,000 miles, that could be 500 miles. We also, once in a while, will get an aurora, and the aurora borealis or aurora australis, either one, basically acts like a big shimmering mirror, and we can send our signal into the aurora and it bounces back.
Oh, wow.
And I actually made 3 contacts during that aurora that we had. And this is typically on 6 meters. The 6-meter band is also used because in order to refract signals back to Earth, you need an ionization area that makes it look reflective. This actually can be caused by meteor trails. So as those meteor trails are made, you can send a signal up. It hits off of what's left of a meteor as it shoots as it shoots across the sky, and bounces back to Earth.
Oh, I see.
So that's known as meteor scatter. Down on this, even closer to the surface of the Earth, we end up with this thing in the troposphere where we live, where you can get a temperature inversion in the atmosphere, where you get, normally as you go up, you get colder, but then you could get a cold and a hot and a cold and a hot and a hot, and you can actually end up with a duct. And what ends up happening is you get a different refractive index in between those temperature layers, and your radio wave, which goes up, can actually become trapped in that duct.
Huh.
and be bounced back and forth. And this is known as tropoducting, and this is very common on 2 meters and 70 centimeters. And when I say very common, it's not all that common, but it could be it could cover over, you know, a distance of 200 or 300 miles when you would normally just hear line of sight. Other things we can do, for instance, there's something called knife edge diffraction. Let's say you're looking at a hilltop. Knife edge diffraction, normally we're talking line of sight. If this is a sharp peak, for instance, on a mountaintop, your signal will hit the mountaintop and diffract. And some part of it can actually come down on the other side. It's not common, but it does happen. Another thing we can do is intentionally bounce signals off of hills. So there was one of our club members who was, if you know the terrain of Oregon, he was up around Mount Hood, which looks like that. Big mountain. He was here, and our repeater was way down here, and there were a couple other hills in the way that he couldn't get over. Our repeater was way down here, about 90 miles away. He actually intentionally, using a beam antenna, went like that, transmitted his signal at Mount Hood, which bounced off and was actually able to get over that hilltop. So he aimed the wrong direction and intentionally and was able to get a signal going backwards.
Wow.
So you can actually bounce signals off of things like mountains and buildings and stuff like that on purpose.
That's really cool. It's good stuff.
There's all kinds of stuff you can do with this that you never really think to do until you see, oh, you know, I think I'm going to try this. Okay, let's see what next. See, and a lot of people think we're just a bunch of geeks, which we are, but you know.
Yeah, partially right.
Yeah. Okay. Now, another one we do, another problem that we get into sometimes is that we get we get interference. And what in the world makes interference? Okay, so this is let me share this whiteboard. Okay, so we are taught, if anyone has taken a physics class and you have, for instance, a light that you're shining at 2 slits, you do something called the double slit experiment, where you get areas of enhancement of light and areas of dark bands on a wall, for instance, because each of these ends up acting as though it were a separate transmitter and they interfere with each other. This is known as an interference pattern. On the radio, we can actually get something that is, instead of being microscopic, you know, like a millimeter in between the bands, because our signals, you know, our wavelengths are so much bigger, they become macroscopic issues. What we end up with is, for instance, we have a signal that's being transmitted like this, and another one that it's the same signal, but our signals go a lot of different directions. Let's say there's a truck parked over here, and it follows that path. It's still going same speed, except what do you notice about the different paths?
Well, they kind of meet up at the end there, it looks like.
Yeah, but which one had to travel further?
Well,
they get out of sync.
They get out of phase with each other, or they could be in phase with each other because you had a length here and you had a length plus delta, some change that was caused by the extra path length. So let's say we're on the 2 meter band. How long is one wave on the 2 meter band?
2 meters.
2 meters. What if this path is an extra 1 meter? What if it's an extra 3 meters or 5 meters? That first signal comes in like this. The other one gets there a half a wave late. What happens?
You get delay. You get
cancellation. They cancel each other out. It might not be the same amplitude, but you get cancellation. What if it's an even number? What if this is 2 meters or 4 meters or 6 meters?
Signals enhanced.
Yep.
Double strength.
Maybe not doubled, but maybe you get
Is
a
that
little bit of that.
called I'm not sure. I'm just throwing this out. Is that called multiplexing where it gets the signals get-
Multipath.
Multipath. I meant multipath. Thank you.
Constructive and destructive interference. But because we're talking about macroscopic things, I can actually take my handheld radio, be in the lower level of my house, and be listening to a repeater, and it sounds really noisy, and I move the radio 2 feet across, 2 feet across the table, and it sounds perfectly fine. It's physically moving from one spot to another on a macroscopic scale that causes it to go from an area of destructive interference to an area of constructive interference. And it's really cool to see it like in real size, something that you can actually like understand.
I kind of remember we had this antenna where I used to work on the base, and it was a choke ring antenna, had the ground plane had concentric rings, and then it was a GPS antenna, like a hockey puck, and it was supposed to prevent multipathing.
Did it? Maybe.
They claim it did.
Yeah. Well, multipath, the problem with multipath is that multipath, again, is inconsistent. Sometimes it can help and sometimes it gets in the way.
Yeah.
So picket fencing. Picket fencing is a rapid change from weak to strong to weak to strong, typically when you're driving a car, because you're moving at 30 meters per second, and you're going from areas of destructive to constructive to destructive to constructive, back and forth, back and forth. So that's called picket fencing. If you have multipath on data transmissions, you're likely to have a high error rate. There's knife edge. Okay, vegetation. If you are aiming a signal and it's going through trees, depending on the frequency that you're on, it might be absorbing some of your signals. The reason being that the leaves, for instance, they contain water, and depending on the frequency that you're on, the water could actually impede your ability to send a signal through. So does anybody know what the resonant frequency of water is?
It must be in the 5 gigahertz range.
2.45 gigs.
Oh.
That is the resonant frequency of water. A microwave oven operates at 2.4 gigahertz. Any idea why?
It's water. It's stimulating water molecules.
Stimulating energy into water molecules. Yep. It puts energy into water molecules. Energy is heat, heats up your food. Okay, so if anyone's ever noticed that your Wi-Fi tends to go down when the microwave's on, that's because you have a little bit of RF leakage. A microwave oven is 1 kilowatt of RF at 2.4 gigahertz. Most of it is contained inside the oven. Hopefully all of it is contained inside the oven.
Yeah.
Yeah. Okay, but that's why at VHF and UHF, at UHF frequencies, even at 430 megahertz or 902, 1296, that's why you get some degree of signal path loss if you're trying to aim through trees.
Does that also account for like if it's raining outside?
It can. That's why certain satellite systems don't really work well in the rain.
Yep, I know that.
Mm-hmm.
Especially GPS in a car, especially in a big city with big skyscrapers and stuff like that.
Well, that's different. That's just shadowing. Hillside will do that too.
Yeah.
Yeah, I get that. We get that a lot. Out in the canyons.
Oh, I bet. Yeah.
Okay. Any other questions before we go to signal types? All this makes sense, I hope?
Yeah, it does. It's good stuff.
Making sense.
Making sense. Okay, good. That's all I can hope. Okay. Let's see. I want to go back to here. Make sure that I share that. Okay, so modulation modes and signal bandwidth. Here's where we really get into the meat. Remember when we just did this morning and we were talking about bandwidth a little bit and it was all new? Well, it's not new anymore. You guys have been experts at it for 3.5 hours already. So kudos to all of you. And by the way, I don't know if anyone's noticed, but we're down to 52 people, which is still pretty freaking awesome.
What did we start with?
78.
Oh wow.
I guess I didn't really have to worry about going over 100 and paying the extra $50. But you can never tell. You can never tell. You never know what's going to happen. Okay. Amateur radio signals, modulation modes, and signal bandwidth. Okay. So VHF and UHF voice repeaters. Let's just talk about a repeater. A repeater is a station that listens on one frequency and retransmits the signal that it's listening in for and hearing on a different frequency. That is what a repeater does. A simplex repeater is something that waits until it finishes hearing something and then retransmits it on the same. Most repeaters do not do that. Most repeaters will translate a signal from one frequency to another. Most of them use FM, which is frequency modulation, or PM, which is phase modulation. It kind of looks like FM. We're going to get to that in a little bit. The same thing for VHF packet. Packet is data that's being sent over FM handheld radios. So that's packet. Packet is essentially, it's been around for 35 years. And it's typically kind of slow, but it really works. Amplitude modulation. All right, so what we need to do to understand all of this is discuss what modulation is and why we would do it. And notice that we're getting into digital modes and things like that. So, okay. Here we go. We're going to draw a whiteboard. Yeah. Okay, here we go. So I'm going to draw a wave. Give me some characteristics about this wave. Tell me some things about it. What does it have?
Well, it's got, I guess, it's a sine wave for one. And
right. Okay.
It's obviously, it's got positive, negative, if you want to look at it that way.
Okay. Tell me something else about it. That has a frequency. There we go.
Has a frequency.
It has a frequency.
It has an amplitude.
Has an amplitude. What else?
X and Y axis.
Yeah. Well, it's got an X and a Y. Yeah. Okay. It's got a definite direction of travel. Something else about it.
It's not modulated.
Right. It has a phase. And it's unmodulated. Okay. It's a pure sine wave.
That's
true. It's got a frequency. It's got an amplitude. Okay. What's the frequency? What is frequency?
Well, we need to know the units.
Well, I mean, no, what is
cycles per second?
Cycles per second, right? Okay, so what is amplitude?
The height of the wave.
How big it is, right? What is the phase?
Positive or negative?
Time. It's how far
the offset.
Yeah, how far shifted it is with respect to something else.
To respect to the no one knows shit.
And it can be shifted anywhere between minus 180 and plus 180, or it can be shifted between 0 and 360. That would be a phase, right? Because a phase is essentially the spot at which it's anchored around the circle. So you could have one that's starting here and another one that's starting here. That angle in between them is the phase differential between the two. And that is represented by what you see on the graph in time. So there's the phase, and these are all things that we can selectively change if we want to. We can alter a wave's phase, we can alter its amplitude, we can alter its frequency. We can do multiple ones at the same time. Why do we do this? What's the point of doing this?
To avoid interference.
Well,
mean-
if you're adjusting phase, it could be for like frequency modulation.
Right. I mean, what is the purpose of modulating anything? Why do we do it?
Is to put is actually
To encode
is to
information.
encode the wave.
Information. Yes, to put information on it.
I was gonna say intelligence, but same thing, I guess.
Yeah. So another thing we can do is it even there?
Amplitude modulation.
Right? We did amplitude right there. So one thing we can do is we can look at things that are analog. We can look at things that are digital. What can we do with the frequency? We can go from this to this to this. We can encode it in a way that actually means something.
Right.
Essentially, that's what modulation is. It's doing something meaningful to it that makes it actually mean something. We can do this. What is this? What's that known as?
Square waves.
Those aren't square waves. On,
There-
off,
Continuous
keying.
wave?
On,
Morse
off
code.
keying, also known as CW, which is
Morse code. Continuous
Morse
wave.
code. That's what we do. That's how we do Morse code. We turn a single frequency on and off. That's all we do. Okay. How about if we do this? We have this.
Hey, we were just talking about how cold you are sending our dog to training camp.
Oh my God, here we go.
Just kidding. What's up?
Do you want me to order pizza?
There we go. I can do that. Okay. So we can also do this. What did we instantaneously do right there?
Added something. I mean, added.
We did a jump in phase. I threw a phase shift in. I just went from this point to a different point in the same cycle. That's a phase shift. That would be phase shift modulation. I could do a signal where I have this. I have two different frequencies where I go like this, and I alternate between them. That would be known as FSK. Anyone have any idea what FSK is used
I know
for?
what it means. I just can't think of it.
Frequency shift.
Frequency shift keying.
Yep.
We use that for radio teletype, right? That's an analog. Essentially, it's a digital mode for sending ASCII text, right? That's FSK. We can do 8 FSK if we wanted, where instead of having two different frequencies, we can shift to one of 8. That means we can send more data by indicating the frequency that we shift to.
Like a fax.
Yep. We can send, again, another one, which is phase shift keying. We can send PSK31, send PSK63, and something, and so on and so forth. That determines how fast we do the shift. That determines not only how fast we shift, but how much information we can carry.
Is PSK the same thing I see in my wireless ISP radios for encryption?
Doubtful. We're not allowed to encrypt anything. It may
No,
be part of it.
PSK is pre-shared key. Different.
Oh yeah.
Okay. So we can change lots of different things. We can change frequency, phase, amplitude, whether a signal is even present or not. Does anyone know what this word means?
What's that? Modem?
Modulate, demodulate.
A modulator, demodulator. It's basically an encoder, then a decoder. It does both things. That's why we get the name modem. It's essentially taking a signal, modulating it, and also demodulating another one to get the information back out. Okay, so all of these things that we do, the intent is to put information into a signal that can be stripped out by somebody else. So if you think about it, a single tone, a single sine wave tone, the only thing you know about it is whether it's there or not. If it's there all the time, you know that it's there. It has no information. By turning it on and off, that tells you that there is some information being sent.
Some intelligence.
Some intelligence, exactly. Amplitude modulation. Amplitude modulation means intentionally making a signal bigger or smaller. The reason we would do that is because we most commonly send a copy of our voice. So we might do a signal that looks like this. Same frequency, but we make it bigger and smaller. We might also have a constant amplitude and change the frequency of it. That would be frequency modulation. And again, the reason we do this is that we have a scripted way of encoding information on it. Now, we're going to do a little bit of a change right now. And the change is that we're going to shift from the time domain to the frequency domain. So frequency goes from 0 to infinity, and it has an amplitude. We're going to mark our center frequency. This is our carrier frequency, or a frequency of interest. When we have an unmodulated carrier, it looks like this, that contains no information whatsoever. Right? It's completely boring, other than to know that it's there or not. So the purpose of doing an unmodulated carrier is just as a marker, like, hey, I'm here. As soon as we modulate this carrier, we have a plus side and a minus side. When we do an amplitude modulation, we essentially make it look like this, where the left side is the minus and the plus side is the right, but they are mirror images of each other. This is known as amplitude modulation. Well, we already know that the carrier has no information. It's just saying, hey, I'm here, right? That's kind of boring. It doesn't really add any information other than being a marker. And if we can, in our receiver, add it back, then we don't need to transmit it. It saves a lot of energy too. This is double sideband suppressed carrier. Well, we also know that those two sides are exactly identical, which means that we could actually do this and get rid of one of them. That would be
single sideband.
Single sideband. And in fact, because this is on the upper side, this would be upper sideband. We could also change it so that it's only the lower side. This would be lower sideband. By convention, whether we use upper sideband or lower sideband is defined by the frequency band on which we are using at the time. Fundamentally, there's no real good reason to pick one over the other with today's technology. There's absolutely no reason to pick one over the other. They both work equally well. Okay, so let me see if let's see, mute. Okay, so we're going to now erase that, and we're going to make an FM signal, and an FM signal is going to look something totally different. So an FM signal is going to look like this. It's going to have a largely uniform amplitude, and it's going to fill in a block of frequencies that is plus delta F and minus delta F. So the delta means a change. And essentially, this is typically between 10 to 15 kilohertz wide. And the reason that we use FM is because it is largely immune to noise. The big advantage there, of course, is that if there's like static lightning, that causes static crashes and things like that, we're not going to be affected by that using FM. It's typically also relatively high fidelity. So we like using FM for voice. Let's see something here. So that's a roughly 10 to 15 kilohertz wide. The other nice thing about FM is that in order to transmit it, we don't need a whole lot of, in order to receive it, you can actually have a signal that's kind of like rough and bumpy because we cap it in the first place. We run it through something called a limiter, which chops off the top and evens everything out. So even if it's uneven, it doesn't really matter. If we do AM, amplitude modulation looks something like this. And this is going to have, if we do one sideband, it's about 3 kilohertz wide. So now we're just talking about band packing and using bandwidth, using the space available to us. If we look at a single sideband signal, 3 kilohertz wide. If we look at an FM signal, it's, let's say, 15 kilohertz wide. We can use, this is real space, 5 of these for every 1 of these.
Wow.
So that's where we start to deal with availability and looking at bandwidth as a resource, right? The wider your signal is, the more you use it up. That's also why sometimes if we're using digital radio, DMR, we time slice this 15 kilohertz so that group A uses this part and group B uses this part, and A and B. So we're actually able to essentially cut it in half. It makes it a more efficient use of the bandwidth. Okay, so now we're going to move into more efficient uses of the signal, of the bandwidth. So we've got our, come on. Here's our SSB. Here's our FM. And now we're going to look at Morse code. And the reason that Morse code is popular is because, well, first of all, it's a lot of fun. It's my favorite. I happen to like it a lot. I use it all the time. I teach it. But on top of that, it's also relatively efficient, a very good use of space.
It's good. I'm sorry, I have to sign off. I have to leave already. I have to go home.
Okay.
Have a wonderful day, everybody. See you guys tomorrow.
9 a.m. tomorrow. Same time tomorrow. Vladimir.
Yeah, see you tomorrow at 9 a.m. Definitely.
Yep. Okay.
Sorry.
Thanks, man.
I gotta go.
Yep.
Bye.
Thanks. Okay, so I want to also bring something up for everybody to see and hear, hopefully. Okay, this is what I was attempting to bring up. Okay, so has anybody ever dealt with web SDRs?
No.
This is essentially a software-defined receiver that's on the web. And what's cool about it is that it allows you to go and listen to other systems around the world and listen to other people's antennas, receivers. And
it's mainly listening to by shortwave listeners, isn't it?
Okay, well, but it's also really useful for looking at bandwidths, signal bandwidths.
Oh, okay.
Yeah, I'll do this for JS8 call.
So this is, so that's a 3 kilohertz wide signal, right? Okay, so we're going to go down to the CW band and see if there's any significant activity today. You never know. There's one. Let's go down to 40. Notice that I left that bandwidth alone, and notice how much narrower Morse code is. Can everybody see that and hear it?
I don't think so. No.
Not in the least. Nope.
Yeah.
Can't hear anything.
You can't hear anything. Okay, let me make sure that it's shared with audio.
I heard it.
Yeah, I could hear it fine.
I could hear it.
Okay.
All the beeping.
Yeah, I was able to hear it just fine.
Okay. So the advantage, of course, that you see is that the bandwidth is about 50 hertz, maybe up, 50 hertz if it's really narrow, 150 hertz if it's wide. So the advantage, of course, is that if it's only 150 hertz wide and a single sideband signal is 3000 hertz wide, you can fit 20 of them where you can fit one single sideband signal. Now, what's the trade-off? First of all, you need to know Morse code, but what else? What else do you think is a trade-off?
Even if you know it, somebody else, the receiving party has to know it as well.
Assume they know it. Assume you know it. What's the big trade-off?
Dashes.
No. What's the big trade-off?
Everybody.
Communication speed.
Yeah.
The baud rate is really low compared to voice, right? So
I see. Okay.
there's something really important about this, which is the fact that things that have a high amount of information translate to a lot of bandwidth. Information requires space to send it, right? The less the information, the less space it takes to send it. If anyone's ever done FT8, this is FT8. The bandwidth is really low. The data rate is super slow. It's also very resilient. This is actually about 25 or 30 signals in one place. Like that's one signal.
I'm sorry, I don't hear anything.
You have to be focused on his screen share.
So anyway, FT8 is a very narrow bandwidth mode. It's used for very weak signal work because it's so narrow. Another thing that's important.
Your sound dropped out.
You muted again.
Oh, really? Can you hear me now?
Yeah,
we can hear you.
Okay. So basically what you end up doing is if you have a transmitter with a certain amount of power and you want it to be evenly distributed, you take a look at the size of the bucket that you have to fill, and your transmitter only has a certain amount of power. So your signal for FM might be that deep, if you want to think of it this way. For that same amount of power, your single sideband signal might be able to be filled this deep. Your Morse code signal might be able to be filled this deep if you have, let's say, 100 watts. So what ends up happening is that your peak for this may be 13 decibels higher. Well, if you're looking at receiver strength and you assume that everything else is the same, if you start off with a signal that's 13 decibels louder than the other one, by the time it gets to the other end, if this one is a few decibels below the receivability threshold, this one up here might be above. And that's why narrow bandwidth modes are sometimes a lot more popular than wide bandwidth modes. What you trade is not only data rate, but also the ability to get heard when signals are, when conditions are lousy.
I see what you're saying now.
So for reference, one S unit is 6 dB. So if I have an improvement of 13 dB, that is 2 S units on my receiver. That can actually be very significant. That goes from audibility to, to really from being inaudible to really popping out. Also, given the fact that the bandwidth is really, really narrow in the first place, means that at the other end, it can also be filtered very tightly, and other adjacent noise can be ignored. So anyway, that's just how all these different modulation modes can be used to your benefit.
Quick question. I glanced over to my SDR and I see like CW has been split to CW upper, CW lower.
Yep.
And then I see FM is BC-FM, narrow FM, and wide FM.
Mm-hmm.
Could you just go over the differences on the BC, FM, narrow and wide?
BC is going to be broadcast, I think. That's got a bandwidth of 200 kilohertz.
Wow.
Yeah, well, that's why it's where it is, and it takes up a lot of room. It's also super high fidelity. Narrow is 12.5, I think, and there's also a 25 kilohertz. Depending on which one you go for, depending on which one you listen to, there's a modulation index or deviation. The deviation determines how far from the center frequency the signal is going to spread out. So if you're over deviating, for instance, then you will extend beyond what the receiving station can hear, and some of your signal gets lost.
Interesting. Yeah, it's neat because I'm using what's the name of this software here? The RTL Dongo USB, and
Yep,
it's
probably SDR Sharp.
No, actually, I'm using SDR Console version 3.
Okay. And by the way, what's really cool about SDRs is that a home-based SDR, it's typically just a USB dongle that plugs into your computer, and it costs like $30. And it gives you a big wide picture of the whole band, or 2 megahertz of the band. It's really amazing.
And it's great because for me, I don't, I could listen and learn and not require a license, because there's no license needed if you're just listening.
Right. Okay, let's see. Which sideband is usually used for 10-meter HF, VHF, and UHF single sideband? That would be upper sideband. Single sideband compared to FM has a narrower bandwidth. And again, that means you can fill up your signals deeper, with essentially use your power more effectively. The approximate bandwidth of a single sideband signal we covered is about 3 kilohertz. VHF FM is between 10 and 15 kilohertz. FM has a nasty, kind of a nasty effect called the capture effect. So if you have 2 signals, one is a lot stronger than the other one, only the one that's stronger will get heard. That is largely why aircraft have not gone to FM for air traffic control. Because if that were the case and there were 2 aircraft on the same frequency, they would obliterate each other and you'd only hear one. Or you'd hear none at all. We actually do fast scan transmissions. The NTSC is our old school analog fast scan TV. So if a signal takes 6 megahertz of bandwidth, where do you think we would see that? Remembering that it takes 6 megahertz to transmit a TV signal. Pick a band where you're going to find that. So 2 meters, the whole band is only 144 to 148. Is that big enough to hold a 6 megahertz TV signal?
No.
Nope. 420 to 450. Well, actually look at that. 420 to 426, that's channel 1. 426 to 432, that's channel 2. 2 TV channels that we can use. Up on 33 centimeters, 1, 2, 3 TV channels. We actually have access. Notice this says amateur TV fast scan. Same thing on 1296. 1, 2, 3, 4, 5 channels. We actually have 5 TV channels up there because we have more space.
Is any of that used anymore?
Yeah. Yeah. People use ATV. There are actually ATV repeaters in Southern Cal. There used to be, at least in Southern California. And I think there's actually, I don't know for sure if there's amateur digital TV yet. I think there is, but I'm not 100% sure. CW, 150 hertz. An electronic keyer is a device that assists in sending of manual Morse code. I have one right here on my table. Digital modes, packet, PSK31, etc. A digital mode sends 1s and 0s. So packet radio, IEEE 802.11, that's also known as Wi-Fi. FT8 are all digital, sending 1s and 0s. Packet radio transmissions include a checksum, essentially looking for something wrong by detecting errors. A header containing the destination station, and an automatic repeat request. For instance, if anyone, did anyone hear that? Would anyone like to ask for me to say it again?
Yes.
Okay, I said, can anybody hear what I'm saying? So that is automatic repeat request. In other words, I didn't hear what you said. Please just send it again. That's actually encoded into the system. That's ARQ, automatic repeat request. APRS. APRS is the automated packet reporting system. APRS is really fun to use because it's used for real-time communications and GPS locating. Essentially, it's a GPS receiver tied to a packet radio that allows a signal to then be sent from place to place and put on a map. And why would that be fun? Well, because it is. It's just kind of fun to do. And in fact, this is what an APRS map looks like. This is the local Eugene area. Occasionally you'll see a track. That was somebody driving a car. Notice it shows where they were, sometimes what their speed was, what their altitude was. Can be used for high altitude ballooning, weather reporting. Anywhere you see a WX, that's a weather station. A D is a digipeater, which is used to retransmit signals. This right here, this I, that's an I gate, which is an internet gateway for taking signals that are out in the world and transmitting them over the internet. So this is a hybrid system known as APRS, which allows integration. Oh, there's another mobile track, NH6Z-9. Drove from like down here and up to Lebanon. So anyway, hybridization of packet radio, which doesn't require an internet connection, to with GPS, to mapping to the internet.
Hey, Scott, are you showing something on the whiteboard right now, or?
No, I'm showing something on my screen. I'm sharing a screen.
I'm not getting it. Why am I not getting it? I'm seeing the whiteboard.
Well, make that I don't know. I can unshare
It
the
has
whiteboard.
tabs across the top, Michael. Do you see them where it says one's the whiteboard and one's the
There,
screen?
I just
Now I see
unshared
it. Now I see it.
Okay.
Okay. I'm sorry. You were going on. I was like, I just didn't see that.
Yeah, no. So this is APRS, and notice that there's APRS stuff all over the place. This is just Northwestern Oregon.
Wow.
So
that is cool.
Yep.
Okay, now I'm seeing it.
Okay, let's see. Going back to here. Okay. So that's APRS. You can send position data, text messages, weather data. PSK is phase shift keying, which we talked about. DMR is digital mobile radio. It allows two digital voice signals, like literally voice translated into ones and zeros, streams of ones and zeros, to be sent using time slices on a single repeater channel. So it makes really good use of your available space and bandwidth. WSJTX, this is FT8, JS, JT9, etc. This is a very good weak signal system used for meteor scatter, weak signal propagation, Earth, which is also known as moon bounce. It's good for terrestrial stuff too. And the other cool thing about it is that it allows people, because it's a web tied application. I can go here, for instance, and I go to pskreporter.info, and here's a map display of everything that is being received. I don't remember where I left my radio today. I guess we'll find out. Not a lot. Okay, but we're going to look at grid square where we live, CN84. All the signals that have been received by people who live where I live over the last 15 minutes. And so this is just using digital modes and connecting of software to the internet. And guess what? You get a pictorial view.
That is awesome.
Of what the world looks like and the bands that are working from place to place on the surface of the globe. So I could also look at, let's say QF22. I'm pretty sure that's Sydney. And what you'll probably see is that it looks a little bit different.
Is what
Oh.
we're seeing still produced by the dongle?
No, this is produced by WSJTX.
How do you visualize that? How do I look at that?
pskreporter.info. So if I go to the chat and I put it in there, there you go. And you can play with that. And you need to know something about where you're looking. So let's see, JO65, I think is another one. That should be probably Germany. Okay, so notice our color scheme looks a lot different there. It's a lot darker colors.
Why is that?
That's because it's nighttime.
Oh.
And remember I said that the bands that are working well, the propagation changes from band to band during the day and night. These are lower frequency bands. And because it's the middle of the night there, the higher frequency bands are not working, the lower frequency bands are. And people go where the contacts are. So there you go. Pretty cool real-time visualization, right?
Oh, that's really neat. That's cool.
Hey, let's see, moving on. Mesh networking. Mesh networking, also known as ARDN, AREDN, that's a version of it, is you take Wi-Fi routers and you repurpose them and you put new firmware in them, and they turn into self-healing amateur radio frequency mesh systems. Because they're on Wi-Fi, they have very high bandwidths. They operate around 5 gigahertz. You hook them up to a dish. You can create a link up to 30 miles using like a ubiquity router. We do that to connect as kind of like an emergency backbone from here to the coast, from here and then all the way up to Portland. And it's something called ARDN, AREDN, if anyone's curious. Okay, we're into amateur radio station safety. Health hazard prevented by electrical current flowing through the body. We're just going to whiz through this just so you hear it all. We are basically electric. All of our signals running through us are electrical signals. If you get current going through the body, it can disrupt your heart. It can burn you, RF burns and stuff, lightning strikes. It can also cause involuntary muscle contractions, disrupt the electrical functions of cells, and basically kill you and make you feel really lousy. You have 3 wires in a 120-volt circuit in the United States. Black is the hot wire, white is the neutral, green is the ground. Green is always ground. A good way to guard against electrical shock, 3-wire cords that are grounded. Everything goes through a common safety ground, and install mechanical interlocks. Every so often there's somebody who has a 1500 watt amplifier and they want to test something and they violate the interlock and bypass it and stick their hand in and get a 3000 volt shock and die. Some of your equipment can actually kill you. Purpose of a fuse in a circuit is to remove power in case of overload. A fuse or breaker should be installed in series with the hot conductor. Why should you replace a 5 amp fuse with only another 5 amp fuse? Because if you go to a different one, you could actually start a fire, which we talked about. In a power supply, you turn it off. You might have some big capacitors. Who was it that was playing with their friends by giving them a little electric shock in the shop? Who was doing that? Yeah, my dad used to work on on televisions and color.
I was gonna say, radio and TV repair shop.
Yeah, color TV, because the TV tube, a cathode ray tube, is essentially a big capacitor between the front and the back of the tube. You could have 25,000 volts even on like a 5 or 10-year-old TV tube, if it kept a good vacuum. So before you ever work on it, you take a screwdriver and stick it up under the boot and short it out.
Yep, I know that. I learned that a long time ago.
Yeah.
I used to work in 1 hour photo and all of those disposable 35 millimeter cameras.
Mm-hmm.
all had a
Oh, for the
capacitor, and then for the flash.
Yeah.
Oh, wow. I
If
never
you
thought of
were
that.
if you weren't careful when you're popping them open, you'd short that capacitor and get a nice spark going.
Yeah, and it would sting, I bet.
Probably like how those tasers work, I would think too.
Yeah, it's high voltage. So I learned something about that when I was a kid. How much energy can be stored in a capacitor? My dad brought me once a 500,000 microfarad capacitor from a mini computer. He said, "Here, play with this." So I was like 9, and like, "Oh, cool. Well, I wonder what would happen if I hooked it up to a 9-volt battery." So I did. I'm like, well, I guess I better discharge it. So I'm looking around and thinking. I grabbed some of his really good Craftsman screwdrivers, and I stuck one in one hole and one in the other hole, and then I touched them together, and there was a very, very large spark.
Wow.
And then I looked at the screwdrivers, and there were melted spots.
Jeez.
So that was when I learned that 9 volts could be used for arc welding. I was 9 years old.
Oh my gosh.
Like-
You
I had
learned,
an
you learned early.
instructor when he was in class.
And he wasn't even mad at me.
Wow. Well, that's a good dad. You learned. He taught you. You learned.
Mm-hmm.
That's great.
Play with this.
Yeah, that's cool. Well, man, you learned.
Yeah. Okay. Discharging a battery or charging it too quickly can cause outgassing. Then you can get a hydrogen explosion. Okay. Antennas and tower safety. Don't ever climb a tower by yourself, even if it's only for a little while. You get stung by a bee, you get hung up there, you can't get down. You break an arm, you get stuck up on the tower. If no one's there to hear you screaming, then you're there for a while. You don't want that to happen. You never want to accidentally touch any electrical overhead wires. You need to make sure that everything that is a part of what you're doing, even if it falls, is at least 10 feet from any power line. Anybody know what the overhead power lines carry? How much voltage?
I really don't know.
Any guesses?
5,000.
How much?
400.
No, that's not nearly enough. That's not nearly enough.
13,480.
13, at least 13. Most of them are at least 12 kV.
Yeah.
Some of them are as low as 7,200 volts.
Man.
So here's the other thing. This is also why if you ever are in a thunderstorm and your power goes out, why you should never backfeed the system with a generator, because there's a transformer on the pole. If you're backfeeding the system, you're generating 120 volts. That transformer that would normally step you down is now stepping up your 120 volts and energizing those lines with 13,000 volts.
Oh my God.
And then somebody comes along and thinks they have a dead power line, and it's actually not.
That's. I mean, you're saying you're not talking about putting up a tower. You're talking about those high tension towers.
I'm talking about the one running up and down your street.
Right.
Those are 12 kV.
Jeez. Yeah. I've seen them. Yeah. God.
Telephone poles.
Telephone poles. Yeah, power poles. The ones that are way up on the high tension lines, those are.
That's what I'm thinking. Honestly, that's what I thought you're talking. Yeah.
Those are 600, 700,000 volts.
My God, man, I didn't know that.
But there's a reason for that. Comes down to conservation of energy. Because if you can raise the voltage, you don't have to transmit as much current. And because of Ohm's law, E equals IR and P equals IE, it reduces heating losses. Which means you can get away with smaller cables and they don't sag in the heat. That's why they want to raise. Some of them are up to about 1 million volts, because if they can keep them far enough apart, there's no reason to not do it.
Wow.
Put your cell phone next to it, it charges in 4 seconds.
Yeah.
Inductive charging.
Yeah. Okay, let's see. Why should you avoid touching a power and a utility pole? Again, high voltage power lines. Don't touch an antenna that's transmitting. You can get an RF burn. It makes a nice little puncture wound. That's a lot of fun. When climbing a tower, Always have training, use appropriate tie-offs to the tower, and wear an approved climbing harness. Typically a fall arrest harness, so that when you hit or when you fall, it stretches and doesn't break your back. When should you ever climb a tower without a helper or an observer? Never. Important safety rule to remember when using a crank up, you either have to pin it in place or you have to retract it completely. Vibrations, a turnbuckle is something that allows you to tension guy lines. Guy lines are what is used to keep a tower vertical. When the wind blows, if you don't have a safety wire going through it, it will start to vibrate and loosen, at which point you then have a slack tower which can fall.
Jeez.
Grounding requirements are done by local electric code. Always got to look through that. Proper grounding method for a tower. If you have a 3-leg tower, you need a separate 8-foot ground log for each tower leg. Then you bond them together and bond them to the tower. Essentially, you want to give lightning a nice, easy way to get down to the ground.
Yeah.
When installing ground wires on a tower, ensure that all connections are short and direct. Avoid sharp bends because lightning doesn't go around bends. If you have external ground rods, you bond them together with a heavy wire or conductive strap. Why should you use a lightning arrestor and coax? Where should it be? It should be close to the building and attached to the ground. And all of the lightning arrestors should be tied together. Okay, now something that doesn't always get talked about is that we have to, and we're almost done, by the way, for today. We have to actually go through and figure out whether or not our system that we put up is safe for the rest of the world. The rest of the world consists of 2 groups. Those people who we know, who we've told what's going on, and everybody else. So radio signals are non-ionizing radiation. Remember, they fall in the same family as X-rays, and X-rays are definitely ionizing radiation. They cause damage to the DNA. Radio frequency waves can cause localized heating, but won't damage your cells. They don't have enough energy to knock electrons off. Who is responsible for ensuring that nobody is exposed to RF energy above FCC exposure limits? That would be the station licensee. It's my station. I have to go through and run something called an RF exposure limit. Now, if I put up a station, the easiest way to do it is that there is something called an RF exposure calculator out there in the world, and I'm going to put a link to it right now. There's an RF exposure limit calculator. What this allows you to do is say, okay, I'm running 100 watts average, which is impossible for me to run, 2.2 dBi for a dipole. I'm 3 meters from it, and I'm operating at 14 megahertz. Am I safe? Yes or no? And look at that. I can be 10 feet from the antenna at 100 watts and still be under the maximum limits for controlled environment. The controlled environment means I know what's going on. Uncontrolled environment means that I'm just walking through the neighborhood.
Oh, really?
So it's close, but it's safe. So now if I go through and I set it to, let's say I'm running, I bought a kilowatt amplifier and I replaced my dipole with a Yagi, and it's got 9 dB or 11 dB of gain, and I want to be 10 meters away and I'm going to run it again. Guess what? Not safe for the general public. So how would I fix this? Well, I could put a fence around it and increase the distance to 20 meters. And now it's safe. I could also put it back, and I could reduce my power to, let's say, 400 watts. And we're really close. So remember, this is average power. So 325, let's say 325 watts, which is average, now we're safe. So there's, this is really done to protect people who you know and people who you don't know from injury due to RF energy.
Wow.
And you have to do this. Okay, next.
Is that like for something if you have a large tower, like a 100-foot tower in your yard or something like that?
That's if you even have a dipole.
Oh, okay.
That's a requirement of having a station.
Oh, station, okay.
Yep. Okay, a duty cycle. What is duty cycle? Is the percentage of time that a transmitter is transmitting. Duty cycle affects the average exposure to radiation. If you drop from 100% duty cycle to 50% duty cycle, that means you can increase your power by a factor of 2 and maintain the same levels of exposure. It is true that the human body, the reason that, notice it asks what band are you on? It matters because our body is more sensitive to RF at certain frequencies than others. We have the lowest exposure limits at 50 megahertz. I don't know exactly why, but tests have shown that's true. What factors affect RF exposure? Frequency and power level, distance from the antenna, and the radiation pattern. So if you have a dish antenna, being behind the dish is very different than being in front of the dish. So how do you reduce exposure to radiation? You can relocate the antennas. And finally, anytime you get something new and change your station configuration, you have to run a new parameter check. And we're going to stop with that for the day. And kudos to you guys who are still here. I'm sorry, this is a lot of material. Tell me how you're feeling. Other than, well, and if it's overwhelmed, you can say overwhelmed, but okay.
Well, I'll admit, it's just, a lot of this stuff, some of it I know, some of it I don't know, I'm not that familiar with, but I don't think it's really, I'm overwhelmed with this amount of information coming at me continuously. And so I've got to really sit back and let this digest a little bit. That's to be honest.
Yep.
Could you give me that
information via fire hose
calculator information?
I put that on the chat.
Oh, it's on the test. Okay.
No, I put it out in the chat. The meeting chat.
I feel like I just got a bunch of information via fire hose.
Yes, it is. But that's at the same time, that's why I said when I sent out notes, I said, it's a good idea to start studying in advance.
Yeah.
Because this stuff will mean a lot more.
Yeah, I agree with that. You're right about that.
I will say that you describing some of the things that I have been studying has been making it a lot easier to wrap my head around it. So
good. That's what I'm hoping. That's what I was hoping.
I appreciate your efforts. It's a lot of effort on your part to do all this. Thank you very much.
Right. And I signed up for the exam initially for tomorrow, but I've definitely rescheduled because I am going to need more time. But no, you're doing a great job, and I appreciate that.
Thank you.
It's an excellent class.
Thank you. It's fantastic.
Scott, I have a question.
Go ahead, Sue.
I have a question. You sent us a link in the email of hamstudy.org and also the Ham Radio Prep app. Do you have a favorite for?
Well, I like a Ham Radio Exam -tech. That app should be the one that I sent.
Hamstudy.org or something?
Well, there's hamstudy.org, which is, that's where hamstudy.org is actually it's a variant of the place where most of the online exams are given.
Okay.
They also have a lot of practice utilities. They also provide a lot of the ability to go search for exams on hamstudy.org. I mean, I'm okay with here, in case anyone's curious, I'll bring it up.
If there's a different one that you like better.
Well, I like the web app that I sent out, and unfortunately it's not so easy to show you, but this is Ham Study.
That one. Right.
And part of this is, notice it says find a session. And I mean, there's so many options. If you don't feel like taking the one that we have tomorrow, nobody is going to be offended. You can, pick remote, and you pick all VECs, and this is just, this is just 1 day's worth. That's 1 day. And actually that's Labor Day. I think there's even one on, let's see if anyone's doing, yeah, these are Labor Day. So there's even groups doing them on Labor Day. This is Tuesday, Wednesday, Thursday.
I don't think they restrict you. If we take the test tomorrow and do not pass, we'll just take it again, right?
Yeah, they'll actually, most of them, if you're close, will just say, you know what, just take it again. They'll give you another exam
Got it.
in the same session. There are some VEs that don't like to do that. They like to charge you again. The Anchorage group, yeah, they don't do that usually.
Yeah, Scott, I
Yep.
used to
If you're close, they'll just give you another one.
Okay, thank you.
Well, okay, but as far as the app goes, I want to
Yeah.
unshare this. And this, I hope, is the app that you guys have seen. And it looks like that.
Yeah, that's the one that you linked.
I really like
or
this
you gave
one.
the name of.
Yeah, I really like it because it has this thing right there called Take a Section Quiz. And I'm a big fan of that because you can take a section quiz and just study one section of like 10 or 15, between 10 and 15 questions 100 times if you want. Do it until you're really, really solid and then move on to the next one.
That's the ham radio prep.
No.
Right?
No.
I have no idea where you got
Ham
that
radio
one.
exam tech.
Ham
Thank
radio
you.
exam tech by
you.
Roy Watson. It's free.
Yep.
So I believe in free.
And it's really good. I
Thank you.
really appreciate you sharing this because I've already done like the first 4 sections on it, going over just the sections.
Yeah.
And then I was like, well, let me take a sample test. Yeah, I only scored 57%. So I was like, well, that gives me indication I really got to study.
Right. Oh no. And my wife used it. My wife used it for the tech. My son used it for the tech and the general. My daughter used it for the tech, general, and extra.
Perfect.
And they're free, and I know it works. And I've used it to study and see what the new exams are like every time new exams come out. So I like them too. So
I'm glad I asked. Thank you so much.
yeah. And again, it's free. And if it's not the Roy Watson version, it's not the right one. Any other questions? And yes, it does exist for Google Play as well. It's good. It exists for iOS and Android both.
Yeah,
Can you
I
send that
can't
out
find the
on chat,
iOS link,
please?
but the Google one's in there. I put it in
Yeah.
the chat.
Yeah, I'll put it out. I'll put the name.
How long is the license good for?
10 years.
Got
And then you can renew it. So
Is that for all 3?
they're all good for 10 years, and then you renew.
And if I remember correctly, you have up to 2 years to renew, but you can't transmit until you got the renewal showing in the database.
Right. It goes into grace period, and then you have 2 years.
I have a question for you, Scott. What's the difference between the technician versus the extra? Like, how much different is it? Like,
Well, technician or general? Are we going the general first?
well, just go from each one. I'm just curious to see like what is the application of study there and an extra. I'm just curious.
So the technician and the general, if you crush the if you're doing really well on the technician, I would also spend some time on the general and just knock them both out at the same time.
But you have to go to each one successfully. You can't just go from
Correct.
technician. Oh,
Correct.
Okay. All right. Gotcha.
But the extra is, I mean, what you do is it's like it's light years of difference between the general and the extra. The tech and general are both 35 questions. The general is a little more involved. The extra is the really technical exam.
Okay.
And I mean, personally, I thought the extra was easier than the general, but only because I have a master's in electrical engineering. And so all that stuff was, it kind of came second nature because it was a really technical exam.
Yep. I get it. Yeah.
All right. I saw some other hands, I thought, but I can't remember who.
Scott, I was asking if the chat and the video or recorded video are going to be available to us.
They will as well as soon as it finishes converting when we're done.
Okay.
Oh, thank you. Thank you so much.
Other questions? There's got to be more.
What do you need if you want to talk to countries like other countries like over Europe? What do you need to do that?
Get your general.
Okay, your general.
Yeah, because I mean, if you unless you do a lot of Morse code, and even so, you know, on CW you're going to have access to. Let me bring it up. So your CW is, notice the red. So you're as a technician, notice the little star here. That little splat. So you'll have access to 80, 40, 15, and 10. You get phone privileges on 10, but you know, you're not going to really be chasing a lot because you're going to be limited band-wise.
I understand.
And you never know who's going to show up on what band when. I mean, if you really want to start chasing DX, you get your general.
Gotcha.
Because you never know where they're going to be. And that's another reason that's actually another reason to pass your extra too, because you never know where they're going to be banned again. And you notice that as a general, you're in the, come on, the blue section right there. Right. And because of our incentive licensing, notice what you don't have access to. 21 to 21,275, 14 to 225. I tell you what, somebody shows up there and you can't get them, you're going to be pissed. So,
yeah, I see what you're saying.
So that's, you know, the other thing is if you travel, an extra class license, in addition to allowing you to be an examiner for any class license, it also translates to full privileges anywhere in the world when you go for if you do a reciprocal license.
Wow.
So, and I've operated in 7, 8, 9 different countries around the world. So.
Oh, wow. Cool. That's really neat. That's awesome, dude. That's great. Oh, that's just good stuff. I some of the stuff I haven't taken in like since the early 80s in radio TV repair class. Ohm's law and all that kind of stuff. It's 2 pi FL, 2 pi, you know, it's
yes, 1 over 2 pi FC.
Yeah, it's been a while. It's been a long time. And it's like and it's still in my head, but it's been a while. But thank you so much. Been fantastic.
Other questions? As far as like the mechanics of exams or anything?
Do you teach the extras and the general and all that?
I get more bang for my buck teaching the technician.
Okay.
But I have taught general classes. I've never taught an extra class because there's so much material, and it doesn't do it justice to, it doesn't do it justice to do it in a weekend. I don't even think it would be really proud. I don't think it would be possible.
I understand.
The general, yes, the general I can do in a weekend.
Is there a lot of questions on the extra? I mean, is
it's 50. It's 50 questions.
Okay, gotcha.
And the question pool is really big and it's very technical. So.
Gotcha. Okay.
So when I last May, I actually I was told by hold on, let me stop.